And welcome back to Backspace Academy. In this lab, we're going to be creating a server on EC2 that will be running Node.js web applications for us. And also we'll be connecting into that server using a terminal and also using SFTP to upload our application and different versions of that application to this server. Now, one thing I'd like to say is that if you're going to be doing Node.js development or any other sort of development on AWS, in my honest opinion, the best way to do that is by using the AWS Cloud9 IDE, because it's going to have everything set up for you out of the box, and it's going to have a great IDE to use that will be fully integrated with all of those AWS services for you. But that said, you need to have access to the AWS Management Console to use the Cloud9 IDE. But if you set up on EC2, like we're going to do in this lab, you can give someone programmatic access only, and they'll only be able to access it through the command line interface or through a software development kit. And so that's going to reduce any training that is required on the management console, and it's going to reduce any possibility of the developer doing something that they probably shouldn't be doing or didn't mean to do. We'll start off by creating an IAM user with limited privileges that will only allow them to have programmatic access. We'll put them in a group called developers, and we're also going to create a role that will allow that EC2 server to access other services within AWS. Then we'll set up a security group specifically for Node.js. Then we're going to bootstrap this EC2 instance with a bash script. So what will happen is that when this EC2 instance is launched, it will automatically run this bash script, which will set up the Linux operating system for us and a number of firewall settings. Next, we'll look at installing the Node.js software and the AWS software development kit on this instance. Then we'll look at using the secure file transfer protocol to transfer our application, our Node.js application, onto this Node.js server, and also with other versions of our application as well. Then finally, we'll look at creating an Amazon machine image of this server so that we can launch other servers like that in the future without having to go through all of this process of installing the software. And starting off in the IAM Management Console, we're going to first off create a user. We go to Users and Add User. We'll give this user a name. Backspace Lab EC2 will be fine. We're going to give this user programmatic access only. And that means that they can access this server remotely through the AWS command line interface or through an AWS software development kit. We're not going to give them management console access, but that said, if this developer required access to the AWS Cloud9 IDE, then you would also need to have management console access as well. But for this lab, we're just going to be doing programmatic access only. Click on Next Permissions. What we need to do now is that we need to add this user to a group, because that is good practices to keep track of your users and to have your user inherit the permissions of that group, then add that user to a group. We can see here we've got a group for administrators, and we don't want to add our user to that group. So we're going to create a specific group for our developers. So we click on Create Group. We'll call this group Developers. And create group. So now we've created that group for our developers. It doesn't have an attached policy yet. We're going to do that later on. And we've added our user to that group automatically. We'll click on Next Tags, and we're not going to worry about adding any tags to this user. And Next Review, and create that user. Okay, so now that we've created that user, very important for this user to have programmatic access to this server, they need to have credentials. And so they need to have this access key ID and this secret access key. So we need to download that. So we'll just download that now and save that somewhere safe. So once we've got that, we can close out of here. Okay, so now that we've created that user and we've created a group, we need to assign permissions for that user, because right now that user can't do anything. They've got no permissions to do anything. So the best way to get the right permissions to start with, and then we can work from that and refine those permissions, is to start off with an AWS managed policy for a specific job function. So I'm just going to open up a web page here. And here we have our AWS managed policies for job functions. So they are policies that AWS regularly update, and they're policies that AWS believe that a certain job function should have. So we have policies for administrators, billing, database, data scientists, and we've also got there for a developer power user. So we're going to give this user, or this group of users, developer power user policy. And so here we can see it has a link to the AWS managed policy there. So we'll click on that, and that'll take us to the IAM management console specifically for that policy. And there we can see that it has a number of permissions there. We won't worry about that too much, but we can refine that later on if we would like to. And it's certainly a very good idea to do that because you want to limit access as much as possible. What we need to do now is we need to associate this policy with our developers group, and then our user will inherit the permissions assigned within this policy. So we go to policy usage, and we're going to attach this policy to an entity. So we're going to search for our developers group. We could also attach this policy to a user, but it's far better to attach the policy to a group and have all of those users inherit the policy of that group. So we select developers and we attach that policy now. And there we can see we have our developers there are attached to this policy. Okay, so the next thing that we need to do is that we need to create a role for our EC2 server to access AWS resources. So we go to roles and create role. It's an AWS service. We're going to be allowing or associating this role to the EC2 server. So it's AWS EC2. We select EC2 here, which will allow EC2 instances to call AWS services on our behalf. We click on next for permissions. So we're going to give this server access to Amazon S3. So it might want to create buckets or do whatever. So we're just going to give this server Amazon S3 full access. But that said, we could also do an Amazon S3 endpoint, a VPC endpoint in our VPC, and that would also allow access to S3. And that's probably a better way of doing it. But for now, I'm just creating a role here to show you how you can create access permissions for a specific server. So this could be access to EC2, for example, if you wanted this EC2 server to be able to create other EC2 servers. So you could actually search here for EC2 as well. But we just stick now with Amazon S3, click on next tags and next review. We'll give this role a name. We'll leave the description as it is. And that looks pretty good. And we'll create this role. Okay, so now that we've created a user and we've added that user to a group and we've assigned permissions to that group for that group of users, and we've also created a role and assigned a policy with permissions to that role, and that role can be associated to our EC2 server. The next thing we need to do is to create a security group that we can associate to this server that will allow traffic from the wider internet and also allow traffic for secure access for us so that we can run terminal commands remotely to this EC2 server. So we need to receive on port 80 for HTTP, but we also need to receive traffic on port 3000 because Node.js won't receive traffic on port 80. It won't let you do that. So what you need to do is receive it on port 80 and then forward it over to port 3000. And further on in the lab, we'll look at how we're going to do that using the Linux operating system. And we also need to have access on port 22 for secure shell, or SSH. And that will allow us to remotely connect into this server and issue commands to this server. And also it will allow us to upload files using secure file transfer protocol directly to that server. So starting off, we need to scroll down to Network and Security in the EC2 Management Console. Go to Security Groups and create Security Group. And we'll give this security group a name and a description. We're going to leave it with the default VPC, and we'll add our inbound rules. So the first one is to receive traffic for the wider internet on port 80 for HTTP. So we'll scroll down, the type will be HTTP. And there we go, port 80, and that will be from anywhere. So all traffic from the wider internet on port 80 will come in. We also need to allow traffic, which will be a custom TCP, on port 3000. And that is to receive traffic for the Node.js server. And that will be from anywhere as well. And the final rule that we need to create is for SSH. So we'll scroll down to SSH, which will give us secure shell access remotely to our server. Now, normally you would select, and I suggest that you select my IP. I can't do that here because where I operate from, I've set up multiple internet connections through a load balancer. And so my IP can be run of 3 or 4 different IP addresses. So I have to use anywhere, but please, if you've got a static IP address, make sure that you select my IP. It's going to give you much better security. So I'm just going to select anywhere for now. And then I'll create that security group. And there we go. Okay, so now that we've created our security group, we need to associate it with an EC2 instance. So first of all, we need to create that EC2 instance. So let's go to Instances and Launch Instance. We'll select the Amazon Linux 2 AMI, which is a CentOS AMI. And we'll select the T2 micro. And next, for configure instance details, we'll leave it with the default VPC. Make sure that you auto assign a public IP address, because without that, you're not going to be able to receive traffic, or you won't be found on the wider internet. We'll select that IAM role for this EC2 service that we created, which was backspace-lab-EC2-S3. And then we're going to scroll down to this area of advanced details. Now that might be minimized like this, or if it's not there, just click on the caret here and it'll open it up for you. Now what we need to do is that we need to create a bash script, a Linux bash script. And what that will do is that will be invoked when the instance is launched. And it will set up, first of all, it will do a update of our Linux operating system, a yum update. Then it's going to set up our firewall rules within the Linux operating system, and is going to direct traffic that comes in on port 80 that cannot be received by Node.js directly, and it's going to forward that traffic over to port 3000 where the Node.js system can actually accept that. Now this is firewall rules that are set up in the Linux operating system, and this is one thing to remember, is that yes, you have security groups, but you also have other layers of security as well. And your Linux firewall rules, don't forget about them, because if you're using Linux, you can also take advantage of those as well as another layer of security. So we've got that set up now. We just paste that in, and we can see there, we're doing a yum update, and then we're directing traffic for port 80, redirecting over to port 3000. So click on Next, Add Storage. We'll leave storage as it is. Add tags. We're going to add a tag, and we're just going to add a name tag. Now, when you put the name tag, make sure that you use a capital N in front of the name, otherwise it won't come up correctly. And the value is just going to be Node.js. So next we configure our security group. So we select the security group. So select an existing security group, which will be down here somewhere. There it is. So there's our Node.js security group. We can see there that it has traffic coming in on port 80, port 22, and port 3000. That looks fine. We'll review and launch. Looking good. And launch. So we need to choose an existing key pair. So I've already got a key pair here. If you haven't, create a new one. So just acknowledge that and launch the instances. And view instances. And we'll let that chug away for now. Okay, so now that we've launched our instance, it doesn't really do anything. It won't receive any, or it won't respond to any traffic coming in. It'll receive the traffic, but it won't do anything with it because we haven't set up Node.js. There's no software on there. We don't have the AWS software development kit either, so we can't access anything like S3 with our software development kit. So what we need to do is add those. So the way that we do that is that we need to connect into this EC2 instance using SSH and run a secure shell and run commands to install that. So the way we do that is we select our server and we click on connect. And we'll get this connection string down here and we're just going to copy that. Just copy that. And what we need to do now is go to where we downloaded our PEM file just recently. So when we created this EC2 instance, we downloaded a PEM file. So I've got the one here that I downloaded. So we just go into where it is, and provided we've got Git for Windows installed on our PC, we just right click on the folder area. If you don't right click on the actual file itself because it won't come up, just right click on the folder area here on the empty space and just do git bash here. And that will get up a Git, or not a Git screen, a bash screen for us that we can issue commands. And the first command that we're going to issue will be to connect to that server. Okay, so I'm just going to paste that command in now. So just right click and select paste and enter. Yes, to accept that fingerprint. And there we go. So we now have secure access to that EC2 server. So what we need to do now is that we need to run through and install the Node.js software on our server. So the first thing we need to do is that we need to install the Node version manager, and from there we can use the Node version manager to install Node. So first of all, do a curl command to bring that into our server. And all this is in the lab notes. Just copy and paste it from the lab notes like I am doing here. And that will bring that in. And now we just need to invoke the Node version manager so we can run it. And just copy and paste over again. And now we can use NVM. Now that it's set up and invoked, we can use it to install Node.js. So we just do NVM install Node. And again, I'm just copying this from the lab notes. Okay, so that worked fine. We're just going to check that it actually works by doing node -- version. If it's installed, it'll send us back what the version of Node is. And there we go. So it's version 13.11 of Node. So that worked fine. Node.js is installed. The next thing we need to install is the AWS software development kit. And so we can install that using the Node package manager now that Node.js is set up. So we just do npm install AWS-SDK. So again, I'll just copy that over from the lab notes, make life easier. So npm install AWS software development kit. And that looks fine. And we'll just check that it has installed by doing, again, AWS -- version. So again, I'll just copy and paste that over from the lab notes. And there we go. So we've got the AWS software development kit has been set up there fine. Okay, so we've installed Node.js and the AWS software development kit for Node.js. What we need to do now is that we need to upload our application code to our server using secure FTP, or SFTP for short. And what we're going to do is that we're going to use a software called CyberDuck, and we're going to connect in using that. So the first thing that we need to do is that we need to grab our public IP address and copy that, and then open up CyberDuck. So there's CyberDuck, and we need to open a connection. And it's going to be SFTP. So it won't be FTP, it will be SFTP for SSH, File Transfer Protocol. And the server will be that public IP address. Port will be 22. And then we're going to choose our private key. So normally this will have none. So what we're going to do is choose our private key. Now that will be the private key that we saved when we created this EC2 server. So the one that's associated to that, that's not your credentials, the Excel worksheet for your credentials. This is a PEM file. So we'll choose that and connect. Now, provided that PEM file is correct, we should be fine. And there we go, we've connected in and it's got a listing of our server. So just jumping into an editor, I've got Visual Studio. It can be anything. It can be Notepad. It could be anything, just to edit this text. So the thing that we need to change here for you will be this private IP address. So that won't be the same as yours. So we need to copy that over. Now just remember, this is the private IP address. Before we copy the public IP address, we need to copy the private IP address. So we'll just scroll down a little bit further. And on the left-hand side here will be the private IP address. And I'll just paste that in. Make sure that we've still got the commas or inverted commas around that. And I'm going to save that. Okay, so once I've saved that, I can now go back into CyberDuck, and all I need to do is just grab that file from my File Explorer and just drag that across and drop it onto CyberDuck, and that will upload it to our server. So I'm just going to grab it here and drop it onto CyberDuck. And you can see there that it's been uploaded. Let's just close out of that now. So what I want to do now is connect back in to the server. So make sure that my connection is still open. So just jumping back into Git for Windows, getting that connection, and it's still open, which is good. And what I'm going to do is I'm going to run that application. So the command to use is node and then the name of the file. So the name of the file is app.js. And just going to paste that in. So node and then the name of the file. Okay, so that worked fine. So we can see here the server is running at that private IP address, 3000. And that will be receiving traffic from, will be receiving traffic that is being redirected from port 80. So if we go into that public IP address now, so I'm just going to copy this public IP address, paste it in here. There we can see we have our application, which is Hello World from Backspace Academy. So that's great. That all worked. Okay, so it was a little bit of work in uploading that software and installing it. So if someone else wants to come along and we need to create another server for them, it would be great if we had an image of that server and we could launch directly from that image. So what we're going to do now is that we're going to create an Amazon machine image, or an AMI, of this server. And once we've done that, we're going to create or launch another EC2 instance using that image. And that way we don't have to install all that software again. So the way we do that is that we go to Instances, select our instance, go to Actions, go to Image and Create Image. We'll give that image a name. and we'll give it a description. And then we'll click on Create Image. So now we'll scroll down and we'll go to AMIs. And there we can see our AMI is being created and its status is currently pending. We'll just wait about 5 minutes or so. I'll go away and have a cup of coffee and hopefully it will be done by then. Okay, it's been about 5 minutes or so, and thanks to the magic of pre-recorded video, it's all been done. So what we can do now is that we can jump back into, or no, we'll stay where we are, sorry. We will launch directly from this page here. We can launch an EC2 instance from this AMI. So just click on Launch. And we'll select a T2 micro. So same as before, we're going to use the default VPC. Make sure our public IP is enabled for it. We'll select that IAM role so that we can access AWS, or the EC2 server can access AWS resources. And we'll scroll down here and we'll paste in. I'm just going to grab it from the lab notes. Okay, so we'll paste in our Linux firewall settings, or Linux firewall bash script. And next, add storage and add tags. We'll put in a tag there. We'll call this one Node.js new. We'll select that same security group. And review and launch. And launch. We'll use that same key pair and launch instances. So we'll let that chug away, and what we'll do in the meantime is we'll get rid of the old one here so we don't get too confused. So actions, terminate, and we'll give the other one a bit of time to do its stuff until it gets a status other than pending for us. Okay, thanks to the magic of pre-recorded video, our instance is up and running. What we need to do now is that we need to change our application because it's set up for the old instance. So what we need to do, I'll just get it up here. So we can see here that the host name, which is the private IP address, is now set to the private IP address of the old instance. So we need to change that to the new instance. So we need to go back into our EC2 management console and we'll select the private IP address. So I'm just going to copy that over and we'll paste that in there and we'll save that again. And what we'll do is we'll get CyberDuck up again and we'll drag and drop that over after we've connected to CyberDuck. So we'll get CyberDuck up now and we'll need to disconnect from the old server and we'll open a new connection. And what we need to do is we need to make sure it's still SFTP, that's fine. We need to get the new public IP address. So this is, again, it's for the old server that we've already deleted or terminated. So we need to get the new one for this one. So just copying that public IP this time, not private IP. And we'll paste that in there now. And again, it's EC2 user again, and the same PEM file as well. So that should connect in. We'll connect. Okay, we logged in successfully. We've got our app.js, so we need to replace that. Okay, we'll just drag that across now. Okay, that's done. So what we need to do now is we need to connect into our server using SSH. So again, what we do is we get Git for Windows up, but we first need to get this connection string here. Now, if you have a look at this, it's using root as the username. Now, that's not correct. For all Amazon Linux AMIs, it must be EC2-user app EC2. So we need to change that. So I'm just going to copy that and change it. And what I'll do now is I'll paste that in to our Git for Windows bash screen. So I'll just paste that in now. And there we can see I've changed it here to EC2-user. And enter, and we should be getting in. There we go. Wonderful. So now we've got our new application, or our updated application with the new private IP address. We should now just be able to do node app.js and run our application. And there we go. So it's running there fine. And we'll just grab this public IP address and go to it in our browser and see what happens. And there we go. So that's fantastic. All worked perfectly. So we created an AMI, and it took all of the hard work of creating or installing Node.js on our server and the AWS software development kit. So what we can do now is that we're just going to clean it all up. So first things first, we'll terminate this instance. We'll delete that AMI. Or deregister that AMI. And we'll go into the IAM, or we'll get rid of that security group as well. We'll go into the IAM management console. We'll delete that S3 role. And we'll delete that user as well. And finally, we'll delete that group as well of developers. Okay, so that brings us to the end of the lab. Just one more thing I want to talk about is the credentials, because we downloaded 2 sets of credentials here. And we only really used one of those, and that was the key that we needed for EC2. So we downloaded that, the PEM file, and we used that with Git for Windows to have this secure shell access. And we also used it with CyberDuck as well for SFTP access. So that is related specifically to that EC2 instance. But we also downloaded, when we created that user, we downloaded programmatic access or credentials for that user, and they were downloaded as a CSV file. So that will have the user's name, which was \lab-ec2, and it will have an access key ID and a secret access key. And what they're used for is that if that user connects into that EC2 instance, and then they want to use the command line interface, which will be already installed because it was an Amazon Linux 2 AMI, they can actually access the resources within AWS. For example, they could access EC2 service, for example, or they could access CloudWatch or something like that. And they could have that access by using these access key ID and the secret access key ID and setting that up in the command line interface in the parameters of it. Or they could also use it with the software development kit as well to access that through an application. So that's the 2 different types of credentials that we were using there. One of them we used and the other one we didn't use. But one of them you're going to be using with the command line interface or the software development kit. So that brings us to the end of a good lab. And I hope you've got something out of it and learned a little bit more about EC2. And I look forward to seeing you in the next one. Welcome back to Backspace Academy. In this lecture, we're going to be building on what we already know about CloudWatch from the Cloud Practitioner course. We know that we can use it for infrastructure monitoring, for example, to trigger an auto-scaling event that would add EC2 instances to our infrastructure when demand is high. We know we can use it to alert us when our AWS bill is going to exceed a certain level. We can also use it for application monitoring. So not only monitoring our infrastructure as working, but also looking at our application and making sure that that application is doing what we intend it to do. And it is performing exactly how we would like it to perform. We'll look at CloudWatch metrics and alerts specifically for containers in Container Insights. We'll look at CloudWatch logs and how we can filter and analyze those logs and the different services around that can integrate with CloudWatch logs. We'll look at how AWS services can subscribe to log events from multiple sources and multiple accounts and collate that in one delivered spot through the use of CloudWatch subscriptions. And finally, we'll look at securing our CloudWatch logs as well. We already know about metrics and what they can do. We know that there are default metrics for EC2 and SQS, but there are also a number of other default metrics for other AWS services. In fact, more than 70 AWS services have default metrics that are available for you to use. That includes not only EC2 and SQS, but also DynamoDB, S3, ECS, Lambda, API Gateway, and many more. And if those default metrics don't do what we want, then we can also create our own custom metrics. And the way we do that is that we can have an application deliver data directly to CloudWatch for us. And we can do that using the CloudWatch API, SDK, or the command line interface and use the put metric data command, which will send data that we have collected and send that to CloudWatch. For example, you might have an Internet of Things device, and that is acquiring data from a sensor, and you would like to put that data somewhere. So you could use the put metric data command and have your application that is using the AWS SDK, and that would send that data to the AWS CloudWatch service. And from there, you can analyze it and view it and do whatever you want with it. Now, standard custom metrics, they are a 1 minute resolution, but there are also high resolution custom metrics that can go up to 1 second resolution. One thing to consider though is that the pricing is the same regardless of resolution. So the higher resolution will of course cost you more. All metrics will expire after the defined retention period. So if you've got high resolution custom metrics and they are less than 60 seconds of resolution, then CloudWatch will hold those for up to 3 hours. And then after that, they will expire and will be removed from the system. If it's 1 minute, it will be 15 days. If it's 5 minutes, it will be 63 days. And if you have a 1 hour resolution between your sampling, then that will be 455 days or 15 months of retention period. Those metrics, you cannot delete those manually. They must expire after that defined retention period. If an instance is terminated or that monitoring is disabled, the previously connected metrics will still be available for you to view. Now, if you find that the retention period is not long enough for you, you want to archive these further, you can actually download your data points using the CloudWatch API or an SDK or the command line interface using the get metric statistics command. And that will allow you to download those data points over a defined period. And from there, you can store them somewhere else, such as Amazon S3. If you implement CloudWatch logs to store your log data, then that will store it for as long as you want. It will store it indefinitely, and you can change that period for however you want as well. Any CloudWatch metric, whether it's default or custom, doesn't matter, can have an alarm associated with it. And that alarm will be triggered when that threshold is met. An example of an alarm would be EC2 CPU utilization, and we could use that alarm to alert an auto scaling event to occur. We could use the SQS queue length to add worker EC2 instances on a processing line. We could also have a metric that alerts us, or an alarm that alerts us when our AWS bill exceeds a certain level. The alarms will be triggered when a threshold level is met. So you need to set a target value, and then you need to choose whether it is greater than or equal, less than or equal to that target value for that alarm to be triggered. If you are using high resolution custom metrics, then you can establish a high resolution alarm for periods as low as 10 seconds. The history of alarms will be retained for up to 14 days and available for you to view. Not only can we collect metric data and view that metric data, we can also apply basic statistics to that data as well. We can apply metric data aggregations over a specified period of time, and we can apply the minimum or the maximum value, the sum of values, the average of all of these data points, the sample count, or a percentile of that data within that period of time. It supports many unit types. And if you want to know what they are, you just go to the CloudWatch API documentation and look up metric datum, and that will list all of the different data types that are available. The periods for our data aggregations will be defined in seconds, and that will be 1 second or 5 seconds or 10 seconds or 30 seconds or any multiple of 60 seconds. Sub-minute periods are only available if you are using high-resolution custom monitoring. It's not available with standard monitoring. Not only can you collect data, but you can also view those metrics and alarms in the console with the AWS CloudWatch dashboards, and they are a customized auto refresh view of that data. You can also create cross-account and cross-region dashboards if you need. Live data, if it is switched on, is shown as soon as any data is published for that period. So when that period is up and it publishes the data for that specific period, that live data will appear on the dashboard. If live data is switched off, then it will be shown 1 minute later. So those dashboards, they can be created, obviously using the AWS Management Console, but they can also be created manually using the command line interface, API, or one of the many software development kits using the put dashboard command. Anyone who wants to view those dashboards will need to have an IAM permission to view that. And that could be administrator access or CloudWatch full access policy, or you could create a custom policy that would have get dashboard permissions or list dashboard or put dashboard to create a dashboard or delete dashboards permissions attached to it. CloudWatch Synthetics allows you to create configurable scripts or canaries to monitor web endpoints and APIs. So what that means is if you want to not only check that a website is up and available, you also want to check that it is performing and doing exactly what it is supposed to do, then you can create a script that can test that for you. To make life easier for you, there are blueprints available, and you can choose from a heartbeat monitor just to check that the endpoint or API is actually accessible. You can check an API canary that can send a HTTP post command or whatever to an API and check that it is responding correctly. You can also have a broken link checker that can go through a website and make sure that there are no broken links. And there is also a graphical user interface workflow blueprint that is based upon Puppeteer. Now, this is where the real power of synthetics comes in. Puppeteer, not to be confused with Puppet. Puppeteer is a Node.js package that allows you to communicate with a headless WebKit for web automation. Now, if you're not a developer, you're probably saying, what is that? Now, this is a very powerful tool, and I've been using web automation for many, many years, and it is part of my really powerful toolkit that I use quite a bit. I've used Phantom.js quite a lot, and in 2017, when Google came out with their headless Chrome browser, I've been using that with Puppeteer. Both of them are very, very good. What they do is that they allow you to interact with a website without actually having a browser, and you can do it all with code. So you can code to enter into a text box and then click on submit, and you can wait until a button appears or some CSS element appears, and you can do all this through code. And so this, from the back end, so from a website's perspective, it doesn't know whether it's communicating with a real person that is using a browser or whether it is actually just code that is sending commands to a headless browser. And that is very powerful because we can use that for testing. So we can go through as a normal user would and go through and conduct some things on a web page. We can download stuff, we can input stuff, and we can do everything that a normal user would do. So we can set up with CloudWatch Synthetics to monitor and run through this GUI test using Puppeteer, and we can write our code in Puppeteer, and Synthetics will, on a regular basis that we define, will run that test on our application. And this is great because although we may have unit testing at the design stage and development of our application, it's always great because things do change, and there may be things that we didn't pick up, and we later on pick those up when it goes live. And so that's where this really comes in and is really powerful. So those Synthetics tests can be scheduled for up to 1 minute intervals, and statistics and details of those can be viewed in the console. Another great feature is that it integrates with CloudWatch Service Lens, which we'll talk about in the next slide. CloudWatch Service Lens, it allows you to visualize and analyze the health, performance, and availability of your applications in a single place. And it does that by integrating AWS X-Ray with CloudWatch. Now, you'll learn a lot about AWS X-Ray if you're going on to do the AWS Certified Developer course with Backspace Academy. But if you're not, what it is, it's a service that allows you to insert within your application's code to send data to the AWS X-Ray service. And so what that does is the AWS X-Ray service will collect that data, those data points, and it will display those. And what that means is that you can see how long it takes for different functions within your application to operate, and allows you to pick up on any errors or bottlenecks within your application when it's running. So the way it works is that we have to integrate X-Ray with CloudWatch by deploying first off the X-Ray code on the application. And we do that using one of the software development kits. And then we also, separate from our application, we have to install the X-Ray daemon. And what the daemon does is that it communicates between our application and the AWS X-Ray service. And then the X-Ray service will collect that data. Then we need to install the CloudWatch agent on our server, and that will allow the X-Ray data points to be sent off to CloudWatch. And from there, we can monitor and view those. Container insights are metrics and logs specifically for containerized applications and microservices. Some examples of metrics could be CPU utilization, memory, storage, task count. It's available for Elastic Container Service, Elastic Kubernetes Service, and also for Kubernetes that is running on EC2. Container insights are charged as custom metrics. CloudWatch logs allow you to monitor, store, and access log files from a number of AWS services such as EC2, VPC Flow Logs, CloudTrail, API Gateway, ECS, EKS, Lambda, RDS, Route 53, and SNS, just to name a few. There are log events for CloudWatch logs that consist of a timestamp and then a message. And the log streams are a sequence of these log events that come from the same source. And then we have log groups, which are groups of these log streams that have the same retention, monitoring, and access control settings. You can apply filters to the metrics that are collected by the CloudWatch log service by assigning those metric filters to an individual log group. And by doing that, that metric filter will be applied to all of those associated group streams. Now, by default, unlike standard CloudWatch, the logs are kept indefinitely and never expire. But you can change this by modifying the retention settings. So by creating different retention settings and assigning those to a log group, any streams that are associated with that log group will have those retention settings applied to them. CloudWatch Logs Insights is a fully managed service that allows you to analyze data stored in CloudWatch logs. And it does that with a really fast and interactive querying service. And it also allows you to visualize the results of that afterwards in line and area charts as well. It uses a really simple query language with really simple commands such as display to simply limit the display of those results, to retrieve certain fields, to apply a filter on results, to apply statistics to an aggregated region of those results, to limit those results, and also to conduct parse operations on those results as well. You can apply arithmetic operations, and also you can apply regular expressions to those results as well. There are a number of built-in functions, such as string functions, date-time functions, also functions that can be based upon the IP address of those results, and also functions that can apply across aggregations of data. And again, the visualization results can be in line or area charts. CloudWatch Contributor Insights is a great tool if you're conducting a root cause analysis into problems in your infrastructure. It helps you to identify the top contributors to those results that are influencing your system performance. It does this by you creating rules in a JSON or JavaScript object notation. And those rules will allow contributor insights to evaluate for patterns in those streams of log events that are sent to CloudWatch logs. To make life easier for you, there is a wizard that can develop these JSON objects for you. You don't have to actually do it yourself as such. And there are also sample rules also available to create that JSON. So if you're not too comfortable in creating JSON scripts or JSON notation, then there is that wizard and sample rules available for you. So those results can be also sorted and filtered according to what you require. So here we've got a CloudWatch Insights of a DynamoDB table. And here we can see we've got the most accessed items, and we see a good line graph of that. And we can clearly identify at what time what items were most accessed and also the most throttled items. So again, we can see what areas of this DynamoDB table are under load as such, and we might be able to make some changes to our schema or make some changes to our infrastructure to accommodate that. CloudWatch subscriptions allow a Kinesis stream or the Kinesis data firehose or AWS Lambda to subscribe to a real-time feed of log events from CloudWatch logs. It achieves this by having you define a subscription filter which defines which events are to be delivered to that subscribed service, and then you define the ARN or the Amazon resource number for that particular resource, be it a Kinesis stream or Lambda or whatever it is. Another really good feature of subscriptions is that you can create an IAM role that will allow log data from other AWS accounts to be subscribed to as well. So you could have one account with a Kinesis stream or or a data file host delivering it to S3 or whatever it is, receiving a real-time feed from multiple AWS accounts. The data in CloudWatch logs can be encrypted at rest by simply associating an AWS Key Management Service or KMS customer master key with a particular log group. And so any logs or any log streams that are associated with that log group will be encrypted at rest with that KMS master key. Identity-based IAM policies can be used to restrict access from an IAM entity to log groups, log streams, or destinations for CloudWatch logs. So this entity could be a user or a group in your account, but it also could be someone who has permissions that has been granted to them through a role. And by doing that, they may be able to access your data securely with the permissions defined from another account. You can also have resource-based policies, and they can be attached to the actual resources of CloudWatch logs destinations that are defined in the CloudWatch subscription service. And by doing that, you're going to restrict access to that particular resource by applying that to the actual resource itself. If the service that you're collecting data from resides within a VPC or inside of a VPC, you can encrypt that data in transit between your VPC and the CloudWatch service by using a VPC endpoint. And that will allow for private communication between those resources that you're monitoring inside of your VPC and the CloudWatch service. So that brings us to the end of this lecture, and I hope you enjoyed it, and I look forward to seeing you in the next one. Okay, so I'm just now in the EC2 console. I've created an EC2 instance here, and I've just called it, what have I called it? CloudWatch test. And we can see here it's got we click on monitoring, and we've got our CloudWatch metrics set up here. So the first thing I would like to do is to enable detail monitoring. So I just click on that. And there we go. We have no alarms configured. That's fine. We already know how to create an alarm. We've already done that in the highly available and fault tolerant lab, so we won't do that again. So let's have a look at our CloudWatch metrics. So we just click on here, view all CloudWatch metrics. Okay, so we can see here we've got a number of metrics available, but it's not going to be the same as what's available in USE. So I'm in Asia Pacific Sydney here, so I'm just going to jump into US East and see what it looks like. So you can see here we've got a lot more available in the North Virginia or the US East region. So that's something to be aware of, that when you're setting up your infrastructure, one of those things you need to consider is that if you're going to take advantage of CloudWatch, make sure that the metrics that you want to monitor are available in the region you're looking at. So I'll just jump back into the Asia Pacific region. Okay, so let's have a look at some EC2 metrics. So we can see here we've got I've only got one instance set up in this account there, in this region. And so we can see here is our instance CloudWatch test. So let's have a look at CPU utilization. So if we just click on and select that, we can see our CPU utilization there. And so I had a couple of spikes here, so I did a bit of load testing on it just to see if it would work. You can see we're down quite low here. So what I'm going to do now is I'm going to go back into the EC2 console, and I'm going to grab the public IP from this. Okay, so I'm just going to jump into a web app called loadimpact.com. So they allow you to do some load testing on a server. So it's pretty quick and easy way to go. So you can create a free account there, which I've just done. Normally I wouldn't use this service, but I just think it's if you're not conversant with testing software, then it's a great thing to do. You can just jump online here and put in your URL of your server, and away you go. So I'm just going to do that. So I've already put it in there, and then I'm going to rerun that test that I've already set up. So I'll just scroll down here, and we can see that this is starting to happen. So test in progress. Okay, so just fast forward along here. The test is now finished, and we can see here that we've got our VUs. Now, VUs are virtual users. You can see here the service is continually adding on virtual users. And there we can see as our response time is getting higher and higher. So it's getting up to 2 minutes there at one stage, and then it's getting to the point where it's just not getting a response back in time. So you can see very, very quick and easy to do a very quick load test on a server. So it's and it's a free service for just one server. So if you're not conversant with testing software, have a look at this. So just jumping back into the EC2 management console, and we'll click on monitoring again. And here you can see we've got our spike and our CPU utilization here, and so that corresponds with what we're seeing over on here. So that's pretty good. So let's have a look at CloudWatch. And so here we can see, and we'll just refresh this. And there we can see we've got our big spike from the testing we've done. So that's coming in at 1 minute intervals, and so that's looking really good. So what we can do now is we can look at creating a dashboard. So we'll go into dashboards now. And they're pretty good because they allow you to put in a number of different metrics for all different resources and display them on a screen there, so which you can share with others. So let's just put a dashboard name in here. Okay, so just click create dashboard. So we'll just do a metric graph now, and then we'll look at text widgets in a sec. So we're just going to put a metric graph on there, which is going to monitor so let's have a look at our EC2 metrics. And there's our CPU utilization for our CloudWatch test. So we're going to put that on there as a widget. And there it is. So there's our widget. We can resize it. We can do whatever we want with it. It's pretty good. So we can put a number of these on here. So we can also put different types. We can put a text widget. So let's have a look at that. Okay, so what we've got here is text that has been formatted with Markdown. So Markdown is just a formatting language that you use to put your text into something nice, a little bit like HTML that puts a web page into a nice format. If you've used GitHub before and you've had to have the README for GitHub, you can the front page for your GitHub repository. Then that will be done normally in Markdown. So you'd be conversant with that if you're a developer who's used GitHub. So we're just going to use it as is. You can see here it's putting a heading and then a subheading. So the way of doing that is that hash symbol followed by 2 of those for a subheading, and so that's how you create a Markdown text. So just going to click on Create Widget, and there you can see that it's put a nicely formatted bit of text there, and so that could be anything that we want to put in there, or it could be some help screen or something like that. So it's a pretty handy thing. So we can also get rid of it. So if we look on here and we go delete, we can get rid of it, and we can also get rid of this one as well if we wanted to. So easy to put on, easy to take off, and then we can save our dashboard. So the next thing I want to look at now is events. So reasonably, it's marked here new, so reasonably new service for 2016. So again, we know that we have to create a rule for our event to occur. So this here, so we've got determine events of interest in the CloudWatch events stream, create rules to select those events of interest, and then specify our actions to take when a rule matches an event. So let's create a rule. Okay, so here we have our step 1, which is create rule. So we can select an event source. So it could be an instance state change notification. It could be on a schedule, or it could be an AWS API call. So to do that, you would have to implement CloudTrail to make that happen. Or it could be an auto-scaling event that has occurred. So auto-scaling invoking an instance, for example. So they're the kind of event sources that we can use. So if I just click on here on on API call, we can see it's not going to work because we haven't got CloudTrail logging turned on for this account. So in the CloudTrail lesson, we'll look at implementing CloudTrail and then setting up CloudWatch to monitor those CloudTrail logs. So in this one, we're just going to confine it to CloudWatch. We won't get involved in CloudTrail. We'll do that in the next lesson. So I just click on OK for that. So I'm just going to select an EC2 instance change notification. So we can select any state. Let's select a specific state, so something that happens. So when it's terminated, okay, so when something's terminated, we want to get a notification, or we want an event to occur. It doesn't have to be a notification. It could be invoking a Lambda function or something. So any instance, or we could specify a single instance. So we could specify our CloudWatch test, for example. We could put that in there. And then we look at our targets. So again, what are targets? So they can be an SNS topic, they can be an SQS queue, they can be a Kinesis stream, or they can be a built-in target. So one thing you'll notice here is that there is not a Lambda selection. Okay, so if I went into, because I'm in the Sydney region, if I went into US East, there'd be another target there for Lambda. So something again to consider if you're going to take advantage of events. Make sure that the target and everything that you need is available in your region that you're using, or else change regions. So maybe we want to put in a built-in target. So what do we want to happen? So we can create a snapshot when it's instant. So when an instance is terminated, we can create a snapshot of that volume. And we can select the volume that we're going to select, take a snapshot of. Okay, and we can add additional targets, and we can keep adding them in there. So I just delete that. Okay, so then we just give the rule a name and a description, and then permissions, so we can use a basic built-in targets role. And then we do allow, and it'll allow that to happen. So I'm not going to do that now. But that's how we can do a role, and then we can click on create rule, which will create our rule for us. So we're not going to do that. I think I've gone far enough that you get the idea of how this works. So what I want to do is jump into the US East region. So I'm just going to go back. And now if we look at Andy, and then we can see here we've got our Lambda function. So there we go. So we can actually have a function, so we need to create the function first, and then we can select that function here, and we can have it so when this particular event occurs, whatever it is, or we can have it scheduled for every 5 minutes or something, or we can have it on a cron expression we can put in here for a schedule, or we could have it, when an auto scaling event occurs, we can run this Lambda function. Okay, so that brings us to the end of our hands-on of using CloudWatch as an administration tool, and I'll see you in the next lesson. Welcome back to Backspace Academy. In this lecture on Route 53, we already know what Route 53 is. We've registered a domain name before. We've set up a public hosted zone. But we're going to go into a lot more detail into the features of Route 53. We'll look at not only public hosted zones, but private hosted zones where we can create a domain name specifically for inside of our VPCs. We'll look at different types of routing policies, which is where the true power of Route 53 comes in. And we'll look at how we can use that to reduce the latency and increase the availability of our infrastructure. And finally, we'll have a look at Route 53 traffic flow. And that is a visual interface for Route 53. Route 53, it's a highly available and scalable cloud domain name system web service. You're going to pay only for the hosted zones that you set up and the number of queries that Route 53 responds to. Route 53, it has three main functions. The first being domain name registration. So you can not only register new domains with AWS, but you can also transfer domains from AWS to outside of AWS and from outside of AWS with another registrar back into AWS if you require. You can route internet traffic to the resources that are for your domain. You can have public and private hosted zones. So not only can you have a domain name for internet traffic coming in, you can also set up an internal domain name for your private traffic within your VPCs. There are multiple routing policies that are available, and this is where the true strength of Route 53 comes in. You can route your requests based on latency to get them the quickest response to requests. It can be based on geographic location, or you could distribute requests to different resources based on a weighted round robin. And finally, we can check the health of our resources, which is very important for ensuring high availability. So if one of our resources goes down, we can have the DNS service or Route 53 to fail over to another set of resources. Now, we have already used the domain name service with AWS. We've already created or purchased a domain name in the past, so we know that it automatically creates that hosted zone for that domain name for us. We also know that once we've purchased that domain name and we've received our confirmation notification, we can start adding resource record sets to that. Privacy protection is included by AWS by default for Whois queries. And you can transfer that domain to another AWS account by simply contacting AWS support. And if you no longer want to use AWS Route 53 for your domain name, you can transfer that to another registrar other than AWS, again by simply contacting AWS support. Hosted zones are collections of resource record sets for our specific domain. Public hosted zones, which we've used before, define the domain and subdomain routing for our internet outside traffic. AWS automatically creates our name server and start of authority records for us. And we just add our other records to that, being our A or C name or MX or whatever that may be. We can also set up a private hosted zone, and that can define a domain and subdomain routing for traffic within one or more of our virtual private clouds. Private hosted zones allow you to specify a domain name that you can use for communication between your private resources within your VPC. Now that domain name, it can be anything you want. You don't have to register it, because it's only going to be used within your private resources within your VPC. Now you specify the VPCs that you want to associate with that private hosted zone. And when an EC2 application running inside of that VPC makes a request to that domain name, Route 53 will return the corresponding IP address for that domain name. To set that up, you need to set enable DNS hostnames and enable DNS support in your VPC settings. Now, before Amazon Aurora came along with its load balancing capabilities, we had no way of load balancing requests to multiple RDS instances. And so what we did in the past is that we would create a private hosted zone with a domain name for that private hosted zone that would direct traffic to our multiple RDS read replicas based on a weighted round robin policy. And that way our applications could send traffic to one endpoint, and then the RDS Route 53 service would look after distributing that to multiple RDS instances. Routing policies are where the true power of Route 53 comes in. We've used simple routing policies before, where we've just got a single resource that we're directing traffic from the wider internet to. But there are also failover routing policies that we can use to create high availability, where we can have health checks that can trigger a failover to a backup set of resources in the event that there is a problem with those resources. We can have weighted routing policies that can distribute traffic to multiple resources on a weighting. So 10% of our traffic could go to one resource and 90% could go to another. We have multi-value answer routing, where we can distribute our traffic to multiple resources. We have latency routing policies that can allow us to distribute traffic depending on the location of our end user that is going to provide the lowest latency for that response. We can have geolocation routing policies, which we can define continents and countries and direct traffic based upon the location of that request based on its location or continent. We can also have geo-proximity routing, and that is only for traffic flow service, which is a visual interface for Route 53. But that allows us to define an area within the AWS infrastructure, and if that request is located within that area, it will be directed to a certain resource for that area. A failover routing policy will check the health of our resources and fail over to a backup set of resources when they become unresponsive. The health checks can monitor an endpoint if it becomes unresponsive. They can also be triggered from CloudWatch alarms, but they can also monitor other health checks. For example, if you wanted to maintain a minimum number of resources. There are two types of failover strategy. You can have active and active, where your traffic will be routed to unhealthy or healthy resources based upon those health checks. Or you can have active and standby, where you have a standby set of resources, for example, a static site or a backup site that just sits there not being used, but is available if a health check is failed, and traffic will be routed to that standby set of resources. With a weighted routing policy, you can associate multiple resources with that single domain or subdomain name and choose how much traffic is routed to each one of those resources. The way it works is that you will select a weight from 0 to 255, and the percentage of traffic that goes to each one of those resources will be its weight divided by the sum of all of the weights. If the weight is 0 for all of the records, then that traffic is routed to all of those resources with equal probability. You can't use aliases for your records. And as we said before, it's quite useful as a simple load balancer. And for example, in the past, when we didn't have Amazon Aurora, we could use it to load balance requests to RDS read replicas. But it's also very good at reducing the risk when we're rolling out new software version releases. So for example, we might have a new software version that we want to release to our large number of end users. So to minimize the impact of that new software version, if there's any issues, we can release it to only 10% of those requests, and then we can slowly increase it to 10, 20, 30 until we're more confident that there's no issues with that new software. Multi-value answer routing is useful when you're creating more than one record of the same name and type, and when you're routing traffic to multiple resources and you would like to have a health check associated with those records. Route 53 will respond to requests with up to 8 healthy records that are selected at random and returned to your end user, and your end user's operating system will select one of those healthy records to connect with. If you don't associate a health check with a record, it will be considered to be healthy and it will direct traffic to it. If you have 8 or less healthy records, Route 53 will respond with only the healthy records. But if you have no healthy records, then it will respond with up to 8 unhealthy records. There are limitations on the values for your records. You can't use an alias. You can't use a CNAME either. So let's have a look at an example here. So we've got multiple resources there for a single domain name. So there we've got www.example.com. It's an A record, and we have multiple values for those multiple endpoints for those resources. And so we've also got multiple health checks for those endpoints there, A, B, and C. And what we do is that we give that record set an ID, Web 1, Web 2, Web 3, and with a multi-value policy or multi-value answer policy, Route 53 will distribute at random traffic to those multiple resources if they are healthy. Latency routing policies are useful if your application is hosted in multiple AWS regions and you want to get the lowest latency for your end user depending on where they're located. So the way it works is that you create latency records for your resources. Now, Route 53, it will keep data on latency from different locations for all of its regions. And then it uses that data to return the IP address in a region based on that Route 53 latency data for that request's location. And that way, the end user is going to get the best low latency response to their request. A geolocation routing policy will allow us to direct traffic to different resources based on the geographic location of that request. The way it works is that we will select a continent or a country, and we will allocate or associate a resource to that continent or country. Now, those codes are from ISO 3166 country codes. To handle requests for countries or continents that you haven't included in your routing policy, you can create a default record. But it's very important to remember that you should have a default record, because if you don't create one, Route 53 will return a no answer response for queries from those locations that aren't covered by a continent or country in your geolocation routing policy. Geo-proximity routing policies, they are similar to geolocation routing policies in that they allow you to route traffic to your resources based on the geographic location of that user. But the difference is that you can specify a bias to change the size of that specific region. You can increase it or decrease it by defining a number from 1 to 99, or decrease it from -1 to -99. To use geo-proximity routing, you need to use it with traffic flow, and we'll talk about traffic flow in the next slide. So let's have a look at how geo-proximity routing works. On the left there, we've got a geo-proximity map of different coverage areas there that have the bias unchanged. So we can see there too, we've got one that covers the majority of US East, North Virginia. And on the right there, we can see that the number 2 area in pink has been given a positive bias that has expanded that area to cover all of South America and going up north there as well. So that's how we can modify where our requests go within that AWS global infrastructure. Route 53 traffic flow is a visual interface for designing and implementing complex configurations that use a combination of multiple policies. This greatly simplifies the process of creating these very complex configurations because we can visualize them and see exactly how they work. Once you've created one, you save it as a traffic policy. Once you've done that, you can then associate it with a domain or a subdomain name. You can use it with multiple hosted zones, but those hosted zones must be public zones. It can't be used with private zones. So that brings us to an end to our discussion on Route 53. I hope you've enjoyed it, and I look forward to seeing you in the next one. Welcome back to Backspace Academy. In this lecture, we'll build on what we already know from our Cloud Practitioner course on backing up and restoring our applications and data that is on AWS. We'll start off by looking at some of the concepts and terminology around backing up, and then we'll look at the options that are available for EC2, for databases, both DynamoDB and RDS, for Amazon S3, and also for Storage Gateway. Then we'll look at the AWS backup service, which can control centrally all of these backups that we are doing across many different AWS services. And then finally, we'll look at the data transfer options to lift and shift data that has been backed up and restore it on the AWS cloud. RPO, or Recovery Point Objective, and RTO, or Recovery Time Objective, are two terms that you need to understand when assessing backup and restore options. So Recovery Point Objective, that is the maximum age of files or objects that are restored from a backup. So if you're doing a monthly backup, then the maximum age of that will be 1 month. If you're doing weekly backups, then that recovery point objective is going to be better. It's going to be smaller. So a higher backup frequency means a lower RPO cost. If you're doing monthly backups, then that obviously is going to be a high RPO because it could be up to 1 month old, some of those files. If you're doing incremental backups, and we'll talk about that in the next slide, and you're using a write event, so whenever you write or you delete something on that data source, and if you use that to trigger an incremental backup, then your recovery point objective is going to be very low. So it could even be in the order of seconds or milliseconds. Recovery time objective is the maximum length of time that the system can be down. So if you've backed up everything to tape storage, that's going to take a significant amount of time to get it from tape storage over back onto your live system. And this is something to take into consideration with Glacier. So if you're using Glacier, depending on what storage class you use, that can take hours to restore those objects. If you're using something like S3, it could be a lot quicker. There are two ways in which we can do a backup of a system. In the olden days, we would do a full backup on a regular basis. So we would just basically take a snapshot of all of our data, and then we would back that up to tape. And we'd do that on a daily basis or whatever it would be. Now this captures the entire system. And as such, if it's being done on a regular basis, this will require a large amount of disk space. The advantage of a full backup is that the recovery time objective is very fast. You're simply taking the entire system and bring it over to your live system without any modification or any reassembling of anything. It has a poor recovery point objective because this captures the entire system. It's not going to be done on a regular basis. You're probably going to do this at the most every day. The other option is an incremental backup. And what that does, when it first does a backup, it will capture the entire system. And from that point on, all of the backups from that will only capture the changes that were made since the last incremental backup. Because of that, it requires less disk space. The disadvantage is that it has a slower recovery time objective because to bring that data back, it needs to be reassembled from all of the individual incremental backups. The advantage of it is that it's going to have a good recovery point objective because you're going to be doing these incremental backups on a regular basis. The files contained will be not as old as you would expect from a full backup. When we have multiple hard drives, we can set those up as a redundant array of inexpensive disks, or RAID for short. The two main types of RAID that you need to be aware of are striping, or RAID 0, and mirroring, RAID 1. With striping on the left there, we can see that we have no duplication of the data. So there on the left-hand side there, we've got ABC on one disk and we've got DEF on the other disk. So there's no redundancy whatsoever in a RAID 0 striping setup. But the advantage of striping is that you have double the bandwidth that you would have if you are only using one disk. So you're getting a very high performance. Your rates of access are going to be significantly more over using a single disk. You're also getting high storage utilization because you're not duplicating that data in those disks. In contrast, mirroring or RAID 1 configuration, that has high redundancy because you have duplicate copies of your data on one disk and in the other, and that is regularly updated to make sure that they match, they are synced together. So that has low storage utilization because you need two disks to store the same amount of data that you would need with striping. So there's low storage utilization, but the advantage is high redundancy. The other disadvantage is that you're only going to be having one lot of bandwidth there. So you're going to have half the performance that you would get on a striping RAID 0 configuration, because all of the data will be going through to one disk, and then it will be syncing to another disk there. Amazon Machine Images, or AMIs, they provide a backup of our system image that is running on EC2. When we create an AMI, it will be registered and then saved to Amazon S3, and we can view that in the console. When we don't need it anymore, we can simply deregister it, and that will be removed from both the console view and also from Amazon S3. The AMIs, they are region specific. So if you need to have an AMI to launch instances into another region, you will need to copy that AMI over to the other region. If you create an AMI that is sellable, then you can sell it on the AWS marketplace to other people who might take advantage and use that themselves. An AMI image, it will contain EBS snapshots or instance store root volume templates. And it will also have the launch permissions of who can launch this AMI or can launch instances using this AMI. It will also have block device mapping that defines what block devices, what EBS volumes are attached to this EC2 instance after it has been launched. EBS snapshots allow us to take incremental snapshots of our Elastic Block stores that are attached to our EC2 instances and save those automatically to S3. They are created using the console or the command line interface or one of the SDKs using the EC2 create snapshot command. When you want to restore an EBS volume, what you need to do is you need to, or first of all, create a new EBS volume using that snapshot, and then unmount the existing EBS volume and then mount the new one in its place. EBS volumes are replicated by default within an availability zone, but they're not replicated within different regions. But you can copy an EBS snapshot over to a different region if you would like to do that. One advantage of using EBS snapshots is it makes it quite straightforward to set up a RAID 1 mirrored configuration. To do that, you would unmount your existing EBS volume, take a snapshot of it, and then remount it, and then mount another EBS volume from that snapshot. And from there, you could use your operating system to make sure that that RAID 1 mirroring is occurring. So here we have the MDADM command. Now, MDADM is a tool within the Linux operating system for managing RAID volume configurations. So there we can see it's MDADM. We're creating a level 1 or a RAID 1 configuration, and we're having two devices there. So we can see there we've got device name equals 1 and device name equals 2. And that will, after we've created those two volumes from those EBS snapshots, that will maintain that for us. Elastic file system volumes can be backed up using an EFS to EFS solution that is provided by AWS. And that will back up from one EFS volume to a backup volume for you. What it is a cloud formation template that is provided by AWS, and that will launch the architecture that you need to back up these volumes. And that will consist of a Node.js application running on AWS Lambda that will coordinate that continual backup and those incremental backups of that volume. And those incremental backups will be on a customer defined schedule. So that'll be on a schedule that you define. So here is an example architecture of what it would look like using this CloudFormation template. So here we have our EC2 instance, and we have our Amazon EFS volume, which is our source. And we also have next to it there in the same VPC is our Amazon EFS backup volume. And then on the left-hand side there, we can see that we have our Lambda function that will be orchestrating the backup between the two EFS volumes. There are two options available for us to back up our RDS instances. We can do automated backups where they are done on a regular basis without manual intervention from us, or we can do RDS DB snapshots, and those are user initiated. So we actually do those. So automated backups, they will be a daily snapshot of the data and our transaction logs for that RDS instance. The retention period will be 1 day by default, or it could be up to 5 days. So you can hold them for up to 5 days. So those automated backups will be automatically deleted when that RDS instance is terminated. But you can create a final DB snapshot when you delete or terminate that instance. And the AWS console will ask you as well whether you want to actually take a final DB snapshot before terminating that instance. You can define the backup window for those periodic incremental backups. If you want to have it at, for example, 3 o'clock in the morning till 5 o'clock in the morning or something like that, where your system is not being used as much. Those periodic backups and the related transaction logs allow you to recover up to last restorable time, which is normally the last 5 minutes. So there is a very good recovery point objective for these automated backups. RDS DB snapshots, they're a little bit like EBS snapshots. They're user initiated. You just basically take a snapshot of that instance. Now, one thing to consider is that they are not deleted when that DB instance is deleted. So if you want to get rid of everything, you need to make sure that you also delete those RDS snapshots as well. Otherwise, you will continue to be paid for those. If you want to find where they are or view them, you can do describe DB snapshots, the command line interface command, and that will list all of those snapshots for an instance. And you can use a delete DB snapshot command to delete any snapshots. DynamoDB data can be backed up using the DynamoDB table import and export. You access that through the console, or you can also use the command line interface or one of the many software development kits. And the command there is create backup to create that backup. You can export all of that table's data and the associated log files over to Amazon S3. One thing to consider when you're doing this is that by doing a backup, you will be taking resources from that DynamoDB table. And so that may impact the performance that your end users are seeing when they're using that table. So you can decide how much of that table's provision throughput to allocate to that export process. So for example, it could be 10% or it could be up to 100% in 5% increments. So obviously if you're going to use 100%, that's going to have a pretty massive impact on the performance of that table while you're doing that. You can set that up as a daily export job. And when you want to get it back, you can simply import it back to that table, quite straightforward, again, using the console or the CLI or SDK. Now, we already know from our Cloud Practitioner course quite a bit about S3 and Glacier and how we can set up life cycle management rules. For example, we can have an object be deleted from S3 after a specific expiry time, or we could have that object archived over to Glacier after that expiry time as well as being deleted. And we can simply restore from Glacier back to S3 very easily. But depending on what storage class we have chosen for Glacier, that time taken to restore could be quite a few hours, or it could be quite a few minutes, depending on what the storage class we have chosen for Glacier. AWS Storage Gateway enables hybrid cloud storage between on-premise data centers and the AWS cloud. It does this by creating a virtual appliance that connects directly to your local data center infrastructure. And that virtual appliance could be connected as a file server, or as a local disk volume, or as a virtual tape library as well. The first option is a file gateway, and that will interface your local data center to Amazon S3 using file protocols such as NFS. And so those objects can be accessed directly in Amazon S3. So for all intents and purposes, that will be viewed by your data center as a file server. Next, we have volume gateways, and they are iSCSI protocol access to the Amazon S3 service on the AWS cloud. And so your local data center infrastructure will see that as a local disk volume. So you can access that data in AWS as an EBS snapshot, and you can use that to create a new EBS volume as well. And finally, we have a tape gateway, which is an iSCSI virtual tape library access to Amazon S3 on the AWS cloud. And so your local infrastructure will see that as a virtual tape. There will be a virtual media changer, and there will be virtual tape drives and also virtual tapes. And so that data, once it is archived over to Glacier, can then be accessed on the AWS cloud through the Glacier service. So here we have an example of what it might look like. On the left there, we've got our customer data center. And between our application server on that customer infrastructure, we have an AWS storage gateway appliance. And that could be a file gateway, it could be a volume gateway, or a tape gateway. And that is going to connect through the AWS Direct Connect high-speed service through to the AWS cloud. It will connect to the AWS storage gateway back end. If it's a file gateway, then it will allow access from that application server through to Amazon S3 using standard file protocols such as NFS, and it will see that as a simple file server. If it's a volume gateway, then it will access Amazon, or it will create Amazon EBS snapshots, and it will view that as a simple volume that is connected to that infrastructure. And finally, if it's a tape gateway, then it will interface through Storage Gateway through to the Amazon Glacier service. AWS Backup is a fully managed centralized backup solution for many AWS resources. And this is great because instead of creating individual EBS snapshots or RDS snapshots or EFS to EFS solutions, we can use AWS Backup to do that for us and centrally manage it in one location. It is policy based. We create backup plans that define what that backup looks like and when it occurs, access policies, who can access, who cannot access, and retention policies, how long we're going to keep these backups for, and lifecycle policies. Are we going to migrate this over to, for example, Glacier or something like that? They are tag based, so you can apply a tag to resources, and then the backup service can pick up on those tags and apply those backups to those resources that have that tag. You can create a backup schedule for whatever you want. It will perform incremental backups. It can also perform cross-region backups in multiple regions. And all of these backups will be stored in Amazon S3. On the left there, we've got the AWS backup service, and we can access that through the AWS management console, or we can use the command line interface or one of the many software development kits. The way that we set this up is that we create a backup plan that will define how and when this backup is to occur. Then we define the AWS resources that we want to be backed up. And from there, on a predefined schedule, that backup will occur, and that will be backed up over to Amazon S3. And from there, we can, using the management console, we can monitor the performance and what's happening with those backups. We can modify those backups and that backup plan. And we can also restore those backups back to the assigned AWS resources. Backup plans are a policy that defines when and how to back up our resources. That could be an EFS file system, DynamoDB table, EC2 instance, EBS volume, RDS database, or a storage gateway volume. Within those backup plans, they will have rules that are defined. So we define the frequency of that backup, how often we are going to back up, the backup window, which defines when we want these backups to occur. If you are backing up EFS volumes, you can also define a lifecycle, which will copy that or back that up over to EFS infrequent access storage. You can define the backup vault where these backups are to be stored. You can also have the option to copy this backup to multiple regions. You can define the tags that this backup plan applies to. So any resources that have these tags will have that backup plan applied to it. You can also define recovery point tags to identify different recovery points within a backup. Backup vaults are containers to organize your backups that are created from a backup plan. And you need to define a backup vault when you create a backup plan. A KMS encryption key can be defined with this backup vault, and any backups within that backup vault will have that KMS key or encryption key associated to it and will be encrypted using that KMS key. Access policies can be assigned to an IAM, role, user, or group of users, and that will restrict access to the backup vault and its resources. Or you could have access only to a certain resource type, for example, S3 buckets, but not EFS volumes, for example. Recovery points are individual incremental backups that represent the resource contents at a specific point in time. And those are saved within those backup vaults. If you want to find those recovery points, they can be found using the management console or using the command line interface or one of the many software development kits using the list recovery points by backup vault or list recovery points by resource command. EC2 AMIs will be listed as image / and then the name of the AMI. EBS snapshots will be listed as snapshot / and then the name of the snapshot. Storage gateway volumes will again be listed the same as an EBS snapshot. RDS instances will be listed as AWS backup and then the job. EFS will be listed as a very long hash there, and DynamoDB will be listed as table / the name of the table, then / backup, and then a hash for that individual backup. If you have massive amounts of data on premises and you want to back that up to the AWS cloud, you're going to have some way of getting that large amount of data into AWS first, and then from that point onwards, conduct your incremental backups. So to do that initial lift and shift of that large amount of data, that is where the AWS Snowball devices come in. So an AWS Snowball device, it's a petabyte scale data transfer to the Amazon S3 service. It has enforced encryption, and you can control those jobs with the console, the command line interface, or one of the many software development kits. How it works is that AWS will send out this Snowball device. And you will have a standalone Snowball local client software, which will allow you to upload all of your data to that Snowball device. And also, if it's a large amount of data that exceeds the 50 or 80 terabyte models that are available, it will allow you to break that up into multiple Snowball devices. So the 80 terabyte models, they are only available in the US region. They're not available in all regions as such. And again, if you want to do a petabyte scale job for uploading a large amount of data to Amazon S3, you can again use that Snowball local client, break it up into smaller jobs and put that onto these 50 or 80 terabyte Snowball devices. And from there, AWS will put that back together for you, and you can manage that again using the console or the CLI or the many software development kits. AWS Snowball Edge is a Snowball device which has additional onboard storage and compute power, and also has up to a 100 gigabit per second network adapter. It is available in 3 configuration options. It can be optimized for storage, or it can be optimized for compute operations, or it can be optimized with an additional GPU installed for GPU operations. You can cluster many of these devices, say 5 to 10 devices, and that will allow you to have up to 99.999% of durability of your data. A good example of using this sort of service is that you may have a remote location, such as a mine site in the middle of the Amazon, and you don't have very good internet access or no internet access, but you need to have access to a large amount of data. So you can use this as a temporary file server, or you could also use it as a server to run workloads on that data in remote locations. AWS Snowmobile is a truck with a 45-foot long trailer on the back of it that contains a massive amount of storage. And that is used to transport 100 petabytes of data per each one of these Snowmobile trucks or trailers. And that enables exabyte scale data transfer from on-premises to the AWS cloud. It's extremely secure. Of course, we have encryption of all this data, but there are also security guards to protect this truck. It has tamper-proof devices throughout of it to make sure that nothing has been tampered with while it has been transported. It has a very sophisticated alarm with GPS tracking. It also has 24/7 video surveillance of the truck at all time. So it is a great service if you've got a very, very large enterprise that is transporting very large amounts of data that requires a lift and shift solution of that data. Applications that are running on premises as virtual machines, we can migrate those over to AWS quite simply using the AWS Server Migration Service. How it works is that we will have a server migration connector, which will be a virtual machine that will be installed at our on-premises data center. And that will take snapshots of our source virtual machines and send them over to Amazon S3. When those are on Amazon S3, the AWS Server Migration Service will then grab those and will convert those to Amazon machine images. Once they've been converted to AMIs, then the AWS SMS service will then launch the destination infrastructure by creating a CloudFormation template and then launching that using that CloudFormation template. The AWS Database Migration Service not only manages the migration of individual databases over to another database of the same type on AWS, it also allows for migrations between different database platforms. For example, if you wanted to go from Oracle to Amazon Aurora, it can achieve that. And it does that by defining how that occurs through the different schemas and the different fields within those schemas. It does that with minimum downtime as well, because it will manage everything for you and it will do that cutover for you. Not only can those sources be from the AWS cloud, we can also migrate databases that are on premises over to the AWS cloud as well. AWS Cloud Endure is a lift and shift solution for moving Windows and Linux applications and databases over to the AWS cloud. The way it works is the Cloud Endure agent will be installed on those servers that are to be migrated. And that Cloud Endure agent will communicate with the Cloud Endure service on the AWS cloud. And that allows the AWS Cloud Endure service to replicate that application or that database on the AWS cloud. If we have many migration jobs running, we may want to have a centralized view of that. And that is where the AWS Migration Hub comes in. It's a centralized monitoring of these multiple migration jobs. And they could be AWS database migrations, server migration, or Cloud Endure migrations, or there are a number of other partner services that you can monitor using the AWS Migration Hub. A great advantage of the Migration Hub is that it has no additional cost other than those services that you are using. So that brings us to the end of a very long lecture. I hope you've got a lot out of it, and I look forward to seeing you in the next one. And welcome back to Backspace Academy. In this lecture on AWS autoscaling, we're going to build on what you already know about autoscaling EC2 instances in an autoscaling group and look further into the AWS application autoscaling service and how those same autoscaling features can be applied to databases, to functions, to Lambda functions, and then finally we'll have a look at how we can implement some best practices around autoscaling. As we already know, EC2 autoscaling allows us to create autoscaling groups of EC2 instances that can scale up or down depending on what conditions you set. And that enables elasticity. And it does that by scaling horizontally, not vertically by deleting and then putting in a bigger server. It scales horizontally by adding or terminating these EC2 instances. It enables fault tolerance, and it does that through using health checks. If an EC2 instance fails a health check, it can be replaced with a healthy instance. It can span multiple availability zones, but it cannot span multiple regions. So that redundancy is across multiple availability zones, not across multiple regions. So if a region goes down, then your infrastructure will also go down. But if an availability zone goes down and you have multi-AZ for your autoscaling, then your infrastructure will still operate as it should. The basic parameters there are the minimum size and maximum size that we set, and then the desired capacity. And the desired capacity is generally what we start with when we launch an autoscaling group. The benefits: fault tolerance, availability, and much better cost management. Because we're scaling horizontally, we're going to make sure that we're getting the best out of those EC2 instances and the right amount of EC2 instances as well. On the right there, we can see that we've got an autoscaling group. We've defined the desired capacity. And what will happen is that when that autoscaling group is first launched, it will have that desired capacity, but it will scale out as needed when demand increases to its maximum size. And as demand decreases, it will scale in and terminate those instances down to the minimum size and not below that. Before we create an auto-scaling group, the first thing that we need to do is that we need to define a launch configuration or else define a launch template. Now, a launch configuration, that will describe the configuration of these EC2 instances that are going to be launched within this auto-scaling group. In particular, it will describe the AMI to be used, the instance type, the key pair to connect to these instances, and also the security groups that will be applied to these instances that are launched. You can also use a launch configuration to describe any spot instance bid pricing as well, and that will help you to reduce the costs of your instances. A launch template is similar to a launch configuration. We use it to define what these instances are going to look like that are going to be launched within an auto-scaling group in the same way that we do with a launch configuration. But the difference is that we can have version control. We can have multiple versions of the same template. And that goes in with the philosophy of AWS of having or managing all of our infrastructure in the same way that we would manage software. Another advantage of using a launch template is that you can provision the capacity within your auto-scaling group using multiple instance types and also using both on-demand and spot instances and a combination of all of these. Your existing auto-scaling groups, you can modify those to use launch templates instead, and you can do that by simply going into the console, selecting that auto-scaling group and changing from the configuration to a launch template. You can also do it using the command line interface or one of the many software development kits using the update auto-scaling group command. Launch templates are recommended by AWS over launch configurations. So if you're creating a new auto-scaling group, make sure that you use a launch template instead of a launch configuration. An auto-scaling group is a collection of EC2 instances organized within a group of instances. And that capacity of that group can expand and contract by automatically deleting or adding EC2 instances as needed. The starting point when you first create an auto-scaling group will be the desired capacity. Health checks achieve fault tolerance in your auto-scaling group, and they ensure that unhealthy instances are quickly terminated and replaced with healthy instances to maintain that desired capacity. Scaling plans define the ways that we want our auto-scaling group to scale in and out. We can first maintain a desired capacity and then have that vary to within a minimum or maximum number of instances. We can also manually scale an auto-scaling group by changing the desired capacity or the minimum or maximum number of instances in that scaling plan. So the number of instances can be increased or decreased automatically based upon the conditions that are specified within a scaling policy. And that will define the metric that we're going to be using to make those scale in and scale out decisions. If we expect in the future at a certain time and date or on a regular schedule on a certain time and date, we can base our capacity on that schedule. And we do that by putting in the time and date and the action that we want to take as a scheduled action in the auto-scaling group. And we can quite simply do that in the EC2 auto-scaling console. Our scaling policy will define how much we want to scale based upon some defined conditions. After we have defined what the CloudWatch metric that we're going to use to scale this and the conditions around that, our auto-scaling group will use CloudWatch alarms and the associated policies to determine what that scaling will be. For example, we could have this scaling in and out based upon the CPU utilization across all of these EC2 instances. The types of adjustments that we can make include change in capacity, so adding 1 or 2 or 3 instances, or we could have an exact capacity, maintaining a specific capacity, or we could have a percent change in capacity, so we could add 20% capacity, for example, to our auto-scaling group. There are a number of different scaling policy types that you can select for your auto scaling group. The first one is target tracking scaling, and that one is where AWS takes the most control around your strategy for scaling. And all you simply do is that you will define a target value, and that scaling will be based upon that target value for a specific metric that you define. And auto scaling from there will create and do the ongoing management of those CloudWatch alarms that will trigger that scaling policy, and it will calculate completely for you. You don't have to worry about this. It will calculate the scaling adjustment based upon that metric and the target value. And it will base that decision on the demand on your auto scaling group. A step scaling policy allows us to define our own scaling adjustment values based on different bands of conditions. And so it allows us to define small changes in our capacity for small changes in demand, and also large changes in capacity for large changes in that demand. And so, for example, you might want to increase your capacity by 25% if your CPU utilization falls between 25% and 50%. If you get a big demand on your auto scaling group, you can set up where the CPU utilization is between 50 and 75%, you can increase the capacity by 200%. And that way you can quickly manage that spike in demand. And the last one there is a simple scaling policy type. And that simply increases or decreases the capacity of your auto scaling group by a single scaling adjustment. So simply, if your CPU utilization goes above, say, 50%, then you would add X amount of instances. You can define a cooldown period to make sure that you don't double up on this, so that when the next check comes in, that you don't double up before the instances have had time to actually launch and be registered. And it may react very slowly to large spikes in demand because of that. You're going to have a cooldown period that you need to go through, and then you need to adjust by that single scaling adjustment. But it may also react too much if you've got too much of an adjustment. And so these are things that you really need to fine tune, that you don't have to fine tune if you use something like a target tracking strategy or scaling policy. In the same way that we can auto scale our EC2 instances, we can also auto scale our ECS service as well. So the ECS auto scaling uses the AWS application auto scaling service. And we'll talk more about that in the next slide. It allows you to increase or decrease the number of tasks as opposed to the number of instances with EC2. We can increase or decrease the number of ECS tasks based upon a scaling policy. Again, we've got target tracking where we can base it on a target value for a specific CloudWatch metric. We have step, again, where we can base it on a series of step adjustments that vary based upon the size of that alarm breach within CloudWatch. And finally, we can also set up scheduled changes in our capacity as well, based on date and time. AWS application auto scaling allows us to apply auto scaling and all of the benefits that come from auto scaling to many other services other than EC2. For example, as we've seen with ECS, but also with EC2 spot fleets as well, with EMR clusters, AppStream fleets, DynamoDB tables and global secondary indexes, Aurora replicas. So we can scale an RDS Aurora series of replicas as well. SageMaker, Comprehend, and also Lambda functions. We can automatically provision the concurrency of those multiple Lambda functions. And we can also apply auto scaling to our own custom resources as well. For the auto scaling service to automatically change the capacity of those resources, it needs to have a service linked IAM role so that it has those permissions to call those AWS services. An application auto scaling group can be created with the console, but you can also use the command line interface or one of the many software development kits as well. The commands there are register scalable target to register that target metric that you're going to be using. And then you can upload your scaling policy, generally in JSON, using put scaling policy. And then you can also define a scheduled action that you might want to increase or decrease the capacity of that group at a time in the future. When we create our application auto scaling group, we can select a number of different scaling strategies. We can optimize for availability, and that will maintain the resource utilization at 40%, or for balance availability and cost, and that will maintain 50% resource utilization, or we can optimize for cost, and that will maintain at 70%. If we like, we can also define our own custom strategy. And we do that by defining the scaling metric that we're going to be used, that is going to be measuring those individual resources. So that could be CPU utilization, for example. And then we have a target value for that scaling that we want to achieve. And we also have a load metric, which will measure the load on that entire auto scaling group. Now that load metric is normally used for predictive scaling. And so the auto scaling service will look at the history of load on that auto scaling group, and it will make adjustments to the scaling strategy based upon that. We can also use the application auto scaling service with DynamoDB, and we can use it to adjust the provisioned throughput capacity of both our tables and also of any global secondary index as well. What that does, it will reduce any throttling of those requests when demand on our DynamoDB backend gets high. By doing that, we're going to provide a better experience for our clients that are connected to this backend and reduce that latency of all those requests. We define a scaling policy, which again will consist of a scalable target. And that could be the read capacity or the write capacity of either that DynamoDB table or global secondary index, or we could have both read and write capacity as a scalable target. Then all we need to do is to define a target utilization of between 20 and 90%. If we would like to have a lot of spare capacity up our sleeve, then we would define 20%. If we want to reduce costs and maximize the utilization of these tables, then we could define anything up to 90%. Okay, so here's how it works. On the left there, we've got our clients that will be connecting into this DynamoDB table, and that demand on that DynamoDB table will vary depending on the number of clients and the types of requests. So that variation in demand will be picked up by Amazon CloudWatch as a change in a CloudWatch metric. If that change exceeds an alarm level, then Amazon CloudWatch will notify the application auto scaling service. And optionally, you could also have Amazon CloudWatch send out an SNS message to someone as well. When the application auto scaling service receives a notification from Amazon CloudWatch, then it will issue an update table operation to the DynamoDB table, and that will increase or decrease the provisioned throughput capacity of that table or global secondary index as well. We can also use the application auto scaling service to dynamically adjust the number of Aurora replicas within an Aurora provisioned DB cluster. So this is a provisioned DB cluster as opposed to Aurora serverless. So you will have a real cluster and you will have replicas within that cluster. It's available for both the MySQL and PostgreSQL database engines. Your scaling policy will consist of a target metric, for example, CPU utilization. You will define a minimum and maximum number of Aurora replicas that you would like. You can also define a cooldown period, and that way you can make sure that scaling operations are finished before you invoke another scaling operation so you don't double up on those. You can also enable or disable scale in activity. So you can leave it scaled up and permanently scaled up, or you can enable that to scale back in when the demand goes down. When an AWS Lambda function is invoked in response to a request for something to be computed, an instance will handle that request. If you get many requests coming in at the same time, then there will be concurrent instances that will be handling those multiple requests. So when we get a large initial burst of traffic, the concurrency or the concurrent instances that are available within a region can reach between 500 to 3,000, depending on which region that function is operating in. Once it's reached that initial burst of traffic, it will have to throttle those requests. But after that, it can scale an additional 500 concurrent instances every minute up to the maximum of the regional concurrency limit above that burst limit, which is 1,000. Now that 1,000, it is a limit across all accounts, but you can contact AWS support and put in a case to have that increased if you need it. Now, obviously, if you still exceed that 500 instances per minute, the capacity of those, then again, that will cause latency by throttling of those requests. Okay, so in the grey there, we've got the open requests that are needed to be handled by this Lambda function. And in the orange there, we've got the instances that have been invoked to handle that request for that compute capacity. So as we can see there, as those requests come in, they will be matched by function instances up until that burst limit. When we exceed that burst limit, we can only add up to 500 extra instances every minute up until we reach that concurrency limit of 1,000. So as we exceed that burst limit up until our concurrency limit, if we exceed any of that, then those requests will need to be throttled, and that will cause latency for your application. And then as those open requests are closed out, we can see there that the number of instances will slowly reduce down as well, back down to the minimum level. One way of reducing any throttling within your Lambda architecture is to use Lambda provision concurrency. And what that will do is it will initialize the requested number of execution environments, or those invoked instances that you specify, and that will allow you to reduce that throttling and to reduce latency. So up until the burst behavior, it will act exactly the same as standard concurrency. And then when you exceed that burst, it will scale up to that provision concurrency. And then once that provision concurrency has exceeded, then it will scale up normally above that, which will be of the order of 500 additional instances per minute. And again, here we see we've got our open requests in grey, and we've got our instances that are invoked for this function in orange. So when we first start there, we have our burst limit. And then from that point in, as more open requests come in, then more instances are invoked up until that requested provision concurrency has reached, and it will maintain that. And then at the point where those open requests exceed that requested provision concurrency, and then from that point onwards, it will be adding 500 per minute additional function instances, the same as it would in a standard concurrency arrangement. So the difference there is that above the first burst limit, we're going to have some ready available provision concurrency that's going to prevent that throttling from occurring. But that said, if we exceed that provision concurrency line and we get another big burst, then it is still possible that we would get throttling as well. In order to handle any throttling that may occur if we exceed both our burst limit and our provision concurrency limit by a significant amount, what we can do is we can implement provisioned concurrency auto scaling. And that uses the AWS application auto scaling service. And what it does, it will adjust that provisioned concurrency level automatically depending on demand on that function. And it will use a target tracking scaling policy that will be based upon a utilization metric. As the function is more utilized, then the provision concurrency level will be adjusted to accommodate that. Okay, so here we have auto scaling with provision concurrency. We've got the open requests again in grey there, and we've got our function instances in orange there. So as we can see, as the demand increases, as those open requests increases, our provision concurrency is going to change. And it's going to step up, up, up until we reach that maximum of the scaling range that we've defined. And then above that, it will be using standard concurrency. So if we want to exceed that, it'll again be going on to that 500 additional instances per minute. Then as the demand goes down and those open requests are closed out, then you will see the provision capacity will change, and then the functions will slowly come down to a level to manage that lower number of open requests. There are a number of best practices recommended by AWS. First off there is make sure that you base your scaling on a 1 minute frequency. Now with EC2, standard CloudWatch frequency is 5 minutes. So for an auto scaling, we do recommend, or AWS does recommend, a 1 minute frequency. Enable auto scaling group metrics rather than individual instances. And that way you'll be taking a metric of the entire aggregate group, not just individual instances. Use an appropriate instance type. For example, if you're using EC2 T2 type burstable instances, you may run out of those credits, and that may not behave how you expect it to behave when those credit limits are exceeded. So take that into consideration if you're going to use burstable instances in an auto scaling group. There are some additional things you may want to take into consideration as well. When you have a predictive scaling plan that, for example, a target tracking scaling plan, that is based on the forecast, which is also based upon a history of the demand. So what you can do is that when you first implement this scaling plan and when you launch your auto scaling group, you can set your scaling plan up as forecast only. And then you can view how well it's working. And then after that, you can change it to forecast and scale when you're confident that that forecast quality is what you require. Now with custom predictive scaling, you need to make sure that the scaling metric and the group load metric. So you need to define both of those. The scaling metric will be what is used to scale the auto scaling group in and out, and the group load metric will be used for that forecasting. You need to make sure that they are strongly correlated to the load that you are looking for on those instances. When you are implementing a new scaling plan for an auto scaling group, make sure that you delete any previously scheduled scaling actions when you are doing that. Otherwise, it may interfere with your new scaling plan. If you are getting an active with problems error with your predictive scaling strategy, that will mean that your scaling configuration that you have set up for those resources that are inside of that auto scaling group could not be applied. And there are a couple of reasons for that. The first reason would be that the resource has already been added to another scaling policy. So you need to make sure that it's only added to that one scaling policy. The next cause there is that the auto scaling group does not meet the minimum requirements for predictive scaling. So if you're using a target tracking strategy for this auto scaling group, there may not be enough information available to make a prediction on what that level should be. So the way around that is to wait 24 hours after creating that group to get that information. And then once the service has got that, then you will be able to configure that for predictive scaling. Okay, so that brings us to the end of the lecture. I hope you've enjoyed it, and I look forward to seeing you in the next one. Welcome back to Backspace Academy. If you've made it this far, you're well and truly on your way to getting that much prized associate certification with AWS. Now this lab, it's an absolute monster of a lab. It's a 10-part lab. So unlike the other labs where you're just learning a concept and then moving on to the next subject and then learning another concept, this lab is going to cover a great deal of concepts that you've covered more or less previously, but we're going to go into a lot more advanced detail. And it's really going to challenge you, and you're going to have quite a bit of time spent on this lab. And it's not because I don't like you. Quite the opposite. In this industry, there are two types of people: those that think they know and those that know their stuff. And I produce people that know their stuff because I take the effort to produce labs like this. So please follow this lab, download the lab notes, and make sure you get to the end, because at the end of this, you're going to be very, very confident. So we'll start off talking about the lab and what we're going to be doing, and then we'll be jumping straight in and creating this 3-tiered advanced VPC architecture that's going to have public and private subnets, and it's going to have a whole different levels of permissions within those tiers. Then we'll look at securing our VPC resources within this VPC with security groups and applying those or associating those security groups to our resources. We'll also look at how we can monitor and log IP activity in and out of our VPC to our VPC resources using VPC flow logs. We'll look at elastic network interfaces and how we can actually take one of those off a running instance and then attach them to another instance so that the IP address and all of the traffic that is going to that elastic network interface will then go over to that other instance. And that can be quite handy for us in different situations. Then we'll look at building high availability by replicating our architecture into another availability zone. We'll create an application elastic load balancer that will span those multiple availability zones in a public subnet and an auto scaling group in a private subnet that will also span those multiple availability zones. And then we'll deploy a multi-AZ Aurora serverless cluster that will span multiple availability zones in a locked down private subnet. Then, because that Aurora serverless cluster is going to be in a private subnet, we're going to also create a Bastion host using the Cloud9 service. It will allow us to remotely access our Aurora cluster without causing any security issues. And finally, we're going to create another highly secure layer using network access control lists. Okay, so this is what our architecture is going to look like. We're going to have a VPC which will be located in the US East 1 region. So make sure that you use that region so you can follow on with the lab notes quite easily. We're going to have multiple subnets, and we're going to have those subnets in multiple availability zones, obviously to take advantage of high availability. We're going to have a public subnet that is going to receive traffic from the outside world, from the internet, through an internet gateway. We're going to receive that traffic with an elastic load balancer that is going to span those multiple public subnets. The elastic load balancer will then distribute that traffic to an auto-scaling group of EC2 instances that will have a LAMP web server running on that. And those LAMP web servers will communicate with an Amazon Aurora database that will be located in a DB subnet group that will be spanning those two private subnets. Now we're using an auto scaling group, but in the future, we may want to use Elastic Beanstalk. It has a lot of advantages where we can just update our code. We can integrate it with a CI/CD pipeline and that sort of thing. But for now, we're just going to create an auto scaling group with instances in that. But we're going to make sure that our application architecture can support those requirements. Now, one of the requirements of Elastic Beanstalk is it needs to have outbound access to the wider internet. So that we need to have a route from our subnet through to the internet gateway. But by definition, a private subnet doesn't have that. So what we're going to do is that we're going to create a NAT instance in one of the public subnets. Now that instance can be used as a gateway between our EC2 instances or the Elastic Beanstalk environment and to the wider internet to receive updates and for other downloadable stuff that it needs. So we're going to launch that using the EC2 service, and we're going to use a NAT AMI to do that. Now, because our Amazon Aurora cluster is located in a private subnet, we're not going to be able to communicate to that from the outside world, which creates a bit of a problem because we might want to connect into that database and do some SQL commands. We might want to update that database manually. We might want to download some information manually. So to allow that to happen, we're going to be creating or launching a Bastion EC2 instance, again in the public subnet. And we're going to use a Cloud9 service because, as we'll see later on, it does have some advantages of using that rather than just launching an EC2 instance on our own. And that will allow us to communicate safely and securely with our database without compromising security and allowing access from outside our VPC. The other thing that we need to do is that we're going to have somewhere to store our files. There might be images, documents, whatever. So we're going to be using Amazon S3. So in this lab, we're not going to actually create a bucket because you know how to create a bucket. It's pretty straightforward to do. But when we create our VPC, we're going to create a VPC endpoint to connect to the Amazon S3 service because the S3 service and our bucket is not located in our VPC. So we need to have an endpoint to allow communication between our web services or our web servers, our LAMP web servers in our private NAT subnets to communicate with that Amazon S3 bucket and to receive images, documents and whatever and present them through to the Elastic Load Balancer to our end users. The first thing that we're going to do is that we're going to use a VPC wizard to create a VPC in the US East 1 region. And we're going to use it to create public and private subnets and also to automatically create a NAT instance for us and also a VPC endpoint for the Amazon S3 service. After we've created those public and private subnets, we're then going to create another private subnet using the VPC console. And that will be a lockdown private subnet with no inbound or outbound traffic from the wider internet. And we'll be using that to launch our database service. Okay, so starting off in the VPC management console, we need to launch the VPC wizard. If you don't see that big blue button there, it means you're not actually in the VPC dashboard. So just click on VPC dashboard and you'll get to there and you will see that launch VPC wizard button, which we're going to click. We need to select a VPC with public and private subnets. If you have a look at the diagram there on the right, we're going to have a VPC. It's going to have a public subnet with a NAT instance that's going to allow connections from or outbound connections from our private subnet through to the internet. We're also going to have a connection, an endpoint for the Amazon S3 service as well. Let's select that. We'll leave our CIDR block as 10.0.0.0/16. We're going to give this VPC a name, backspace-lab. We'll leave the public subnet there as 10.0.0.0.24. The availability zone will be US East 1A. Make sure that you are operating in US East North Virginia. And we're going to call this public subnet A because it's located in the 1A availability zone. And our private subnet, we'll leave that as 10.0.1.0/24. Availability zone, again, we're going to use US East 1A. We're going to call this private NAT subnet A because it's going to be what's going to allow connections between a NAT and this private subnet. So we're going to call it the private subnet or private NAT subnet. The next thing that we need to detail is a NAT gateway or a NAT instance. The VPC management console remembers what you used last. So last time I did this, I used a NAT gateway. For this lab, I'm going to use a NAT instance instead because of the cost. So NAT gateway is a perfect service. It's highly available, it's highly fault tolerant, and it's what you would use in a production environment for any decent sized company. Because this is only a lab, we're just going to use a NAT instance instead. So we'll just click on that, use a NAT instance instead. We'll select a T2 micro. Just select a key pair there so we can connect into it later on if we need to. Next thing we need to identify define is a service endpoint. So we've got their DynamoDB. We'll select Amazon S3. So we need to connect into a bucket. And the subnet, we've got a number of selections there. Is a public and private subnets, a public subnet, or the private subnet on its own. Now, our public subnet is just going to contain our elastic load balancer. So our web servers are going to be located in the private subnet, and they are what needs to have access to the Amazon S3 server. So we select the private subnet, give that full access, and we scroll down a little bit further and create VPC. Okay, so after a short amount of time, we've got this VPC successfully created. So we just click on OK. And there we can see backspace-lab has been created. So what I'm going to do now is just going to go into the EC2 management console and just see that NAT instance has been created. And so there we can see we've got one running instance. And there is our NAT instance there. That's another one that I created previously that I've terminated. But here is the one that we just created. So what I'm going to do now is just going to give that a name so that we know what it is. Okay, so now we know when we go and look at our list of EC2 instances, we're going to know what that is all about. So we'll jump back into the VPC management console. Okay, so there we can see we've got a network access control list allocated or created for us by the VPC wizard. We've also got a route table there, and that is the main route table that is associated with the VPC. What that means is that if there are any subnets within this VPC that don't have a route table explicitly associated to them, then the main route table will be automatically associated to those subnets. So we can see there, it ends in 6EC2 there. If we go to subnets and we select our private NAT subnet A here, which is going to be again for our backspace lab there, what we will see is it has the same route table. There it is, 6EC2 on the end of it. It has that same route table, the main route table associated to that. And our public subnet has a different one. It has a different route table associated to that. So let's have a look at these two. So let's first have a look at the private NAT subnet. So I'm just going to open that in another screen or another tab. And we'll have a look at the route entries for that. So there we can see it has a route entry there for local traffic within the VPC. So that's fine, but it also has destination to the wider internet. So if instances within this private subnet need to access the wider internet outbound, they can do that through the Elastic Network interface, which is attached to our NAT instance. And that is exactly what we are looking for. So it doesn't allow traffic coming in from the wider internet, but if instances within or services within that private subnet need to download updates or whatever, and again, the Elastic Beanstalk service does require that, it can do that through a NAT instance. So going back to our subnets, we'll have a look at the public subnet A. And we can see it's got a totally different route table. It's not the main route table. We'll open that one and have a look at that. So this will be a public route table with route table entries to allow access from the wider internet. So again, we've got local traffic, a route for that. So that is fine. But we've also got, for traffic to and from the wider internet, it allows it to go through to an internet gateway. So again, that is what defines a public subnet. So that's fine. So what we're going to do now is that we are going to create another subnet, which is going to be locked down. It's going to be a private subnet that's not going to create or allow any traffic to or from the wider internet. Now, because we're going to be creating multiple custom route tables for this VPC, I'm just going to give this one a name, backspace lab public. That'll be fine, just so that we can identify easy enough later on. And I'll just close that down. And we'll just go back into subnets. And what we want to do now is we want to create a subnet. We'll give that a name. And we'll select our backspace-lab VPC. And we'll select our availability zone again as US East 1A. And our CIDR block this time is going to be 10.0.2.0/24. And we'll create that. And there we go. So there we can see we've got our private subnet A that has just been created with the CIDR block 10.0.20/24. Now, one thing that we haven't done yet is that this has got the main route table implicitly associated to it because we didn't define a route table for this subnet. So what we need to do now is we need to go into route tables. Just open that up in another screen. And we need to create a route table for that subnet. And so that's going to be completely private. It's only going to allow local traffic and nothing else. So we'll just click on Create Route Table. We'll give this one a name. And we'll select our VPC, the backspace-lab VPC. And then we'll create that. Okay, so we scroll down here. We can see that we've got our private subnet. So what we're going to do now is we're going to have a look at the routes there. So we've got here a local route for local traffic and nothing else. And so that is all that we need. We don't need to have NAT access for this private subnet. So that is fine, but we need to have a subnet association. So there's no subnet association. So this private route table is not associated to any subnet. So what you need to do is edit subnet associations. And we need to select our private subnet that we created. And so we can see here, we've got private subnet A. It currently has the main route table implicitly associated to it. We need to change that. So we'll select that and save. And now we can see that we have that subnet. If we go back into that subnet, I'll just click on it. And we can see private subnet A now has that route table private subnet RT associated to it. Okay, coming up next, we're going to be securing this VPC by creating some security groups that we can associate to our resources inside of this VPC. Look forward to seeing you in that next one. Welcome back to Backspace Academy. In this part of the lab, we're going to be creating some security groups to associate with the resources in this VPC. So a quick recap. With security groups, traffic must be allowed by a rule. If there are no rules, then no traffic will be allowed. Security groups, they're stateful. So if the rule allows traffic from a request, the return traffic for that request is also allowed. The first two security groups that we'll be creating will have an inbound and an outbound rule that will allow traffic from other resources that have the same security group associated to them. What that means is that if we have two resources and they've both got that same security group associated to them, traffic will be allowed between those resources. So we're going to create two there, ELB Web Server Security Group for communication between the Elastic Load Balancer and the web server instances. The other one is for communication from resources to the database cluster and outbound communication as well. So that will be from the NAT, the Bastion host, and the web servers to and from the database cluster. The next two security groups will be for inbound and outbound HTTP and HTTPS traffic to and from the internet. So the first one there is going to be for the Elastic Load Balancer to receive traffic from the wider internet. The next security group will be for the NAT instance to be able to initiate outbound requests to the wider internet. Okay, let's jump into the EC2 Management Console. And we'll select Security Groups down in the Network and Security section. We'll create a security group. We'll give that security group a name. And we'll give it a description. And we'll select our Backspace-Lab VPC. Now, we're not going to be putting the inbound or outbound rules in yet because we need to first create that security group, and then we need to reference the security group ID for the inbound and outbound rules. So we just click on Create. Okay, so we can see there we've got our ELB Web Server Security Group has been created. So what we can do now is that we can put in our inbound rule that will reference this same security group. So go to inbound and edit, and we'll use HTTP. And our source is going to be our security group. So what we'll do is just type in SG, and we can select our ELB security group there. So just select that and save. Now, we're not going to be doing a rule for HTTPS because our Elastic Load Balancer is going to be receiving HTTP requests and then forwarding them on as HTTP on port 80 to these instances. So we only need port 80. We don't need port 443 or HTTPS. So go to the outbound tab, edit, and again, we'll select HTTP, port 80. And again, we'll type in SG, and there we'll see our ELB Web Server Security Group and save. So now we'll create another security group for communication between our database and the resources within our VPC. So again, create security group. We'll give this one a name again and a description. We'll select our Backspace-Lab VPC. And again, we're not going to be putting in an inbound or outbound rule yet. We'll need to create our VPC first. So click on Create. And there we can see our DB Web Server Security Group. We'll select that. We'll go to the Inbound tab and we'll edit. So we select all traffic. And again, we'll select our security group. And so this time it's going to be our DB Web Server security group. And save that. So there we can see we've got an inbound rule for this same security group. We'll do the same for an outbound rule. Outbound and edit. And again, we'll select all traffic and our security group. So just SG to get the drop down. And we'll select our DB Web Server security group and save. Our next security group is going to be for our Elastic Load Balancer to receive requests from the wider internet. So again, create security group, give our security group a name and a description. We'll select our backspace-lab VPC, and we're going to add a rule which is going to allow HTTP traffic from anywhere. Another rule which will allow HTTPS traffic from anywhere. And we click on create. Now we don't need to do an outbound rule for that because, as we know, all return requests or all returns from requests will be allowed. Our last security group will be for our NAT instance. So our NAT instance will need to be able to be connected to from our Bastion host. And also it needs to be able to have or initiate outbound requests to the wider internet. So we create security group. We'll give that security group a name and a description. We'll select our backspace-lab VPC. We'll add an inbound rule, which will allow for port 22 or SSH. And that is going to be from our local traffic, our VPC. So it'll be 10.0. There we go. So 10.0.0.0/16, which will allow traffic within that VPC for SSH. The next one, we'll go to outbound and we're going to have HTTP to anywhere, and another one which will be HTTPS to anywhere. So that allows our NAT instance to initiate requests to the wider internet. And at the same time, we've got an inbound request there that will allow traffic on port 22, but only local traffic within this VPC. So we'll create. Okay, so now that we've created our NAT security group and our DB security group, we can associate both of those to our NAT instance. So we need to go to our instances. So just scroll up here and we go to instances. We'll select our NAT instance there. We go to actions and then networking, change security groups. So we can see here that it has the default VPC security group allocated to it. So we don't need to do that anymore. So we'll take that off. We need to have access between the DB instance and the NAT instance. So we need to have that one there. And we also need to have this NAT security group, which allows access or outbound access to the wider internet through the internet gateway. So just assign security groups there. And there we can see we've got those two security groups associated there for that. So that brings us to the end of this part of the lab. Coming up next, we're going to have a look at monitoring the inbound and outbound access to our VPC using VPC flow logs. I'll see you in the next one. Welcome back to Backspace Academy. In this part of the lab, we're going to be monitoring our VPC using VPC flow logs. So that will allow us to capture information about the IP traffic going into and out of the network interfaces of our resources in this VPC. So if we've got an EC2 instance there that's being accessed, then it will record that if it's inside of our VPC. First thing that we need to do is we need to create an IAM role so that the VPC Flow Logs service can access AWS CloudWatch. To do that, we create a role, obviously, and then we create a policy to define the permissions for that, and also a trust relationship that defines the VPC Flow Log service as a trusted entity to assume that role. Once we've created that IAM role, then we can create a CloudWatch log group, which can receive that log stream that is being sent from VPC Flow Logs. Once we've done that, then we can create a VPC Flow Log and allow that to assume that IAM role. And then it can capture the traffic in and out of our VPC and send that as a stream to the CloudWatch log group. First off, we'll create this IAM role. So we go to Services and IAM, and we'll go to Roles and create that role. We'll select an AWS service. It will be an AWS service that will be accessing the CloudWatch logs. We're going to select EC2, although when we do our policy, we're going to change that to have a trusted role with, or a trusted entity of VPC Flow Logs. But for now, we select EC2 and we click on Next and Next and Next. We'll give that role a name. And we'll just change this description from EC2 instances to VPC Flow Logs and create role. Okay, so let's just search for that role, make sure it's been created. So there it is. Now what we need to do is that we need to open up this role by clicking on it. And as we can see here, there's no permissions for it. It's just a role that's been created that doesn't really do anything. So what we're going to do is that we're going to add an inline policy to that by cutting and pasting some JSON code in there. So we click on Add Inline Policy and we select JSON. Now in the lab notes, there is some JSON code there. So we're just going to copy that over from the lab notes and paste that in here. And so you can see here, we have an action. It's going to allow our VPC Flow Logs to create a log group and log streams and to actually put log events in there as well. Okay, so that looks fine there. We'll click on Review Policy. So we'll give this policy a name. And again, I'm just going to cut and paste the name from the lab notes to make sure that it all lines up with our lab notes. So there we go. So we've got a name for our policy there. And we can see that it is allowing access to CloudWatch logs. So let's create that policy. So we've created that role and given it some permissions through an inline policy, but as we remember, we selected EC2 as the service, so we need to change that trust relationship with EC2. So we go to Trust Relationship. We can see here that the trusted entity is ec2.amazon.aws.com. So this is currently set up for EC2 instances to assume that role. So what we need to do is we need to change that so that the VPC Flow Logs can use it. So we edit Trust Relationship. And what we're going to do is we're going to take this service here of ec2.amazon.aws.com and replace it with vpc-flow-logs.amazon.aws.com. So now we have a trust relationship between the VPC Flow Log service and the CloudWatch service. And so if a VPC Flow Log assumes this role, it will have access to the CloudWatch service. Let's update that trust policy. And there we can see that it's now changed as a trusted entity, VPC Flow Logs. Okay, now that we've created our role, what we can do is that we can create a CloudWatch log group, and that will receive the CloudWatch logs from the VPC Flow Logs service. So what we do is we go to Services and CloudWatch. And we click on Logs, Actions, Create Log Group, and we'll give that log group a name. And I'll just cut and paste that from the lab notes, so everything should be the same as the lab notes. Create that log group. So there we can see down the bottom here, we've got that backspace-lab.vpc flow logs-group. Okay, so we've created our IAM role. We've created our CloudWatch log group. What we can do now is that we can create our VPC flow log. So we go back to the VPC management console. We select our backspace-lab VPC. We click on the flow logs. Okay, we'll do that again. We'll click on the backspace-lab VPC. We'll click on the flow logs tab and create a flow log for this VPC. So we're just going to select all. So if a request is accepted or rejected, we'll still log that. We're going to send it to CloudWatch logs. We're not going to send it to an S3 bucket. So I'll just cut and paste from the lab notes, the log group name. And there we go. It's selected it for us. We'll click on that. And our IAM role. So just type in VPC, it should come up there, VPC-flow logs-role. So once we create that, it will start recording activity to and from the resources within our VPC. So let's create that. And close. And then we can see we've got our flow log created there. Now, it's going to take some time before activity starts to be recorded. So it does have a bit of a lag there. So what we'll do is we'll continue on with the lab, and then later on we'll have a look and see whether it has been recording these CloudWatch logs for us. Okay, that brings us to the end of this part of the lab. What we're going to do is that we're going to have a look at using elastic network interfaces, which are connected to all of our EC2 instances. So I'll look forward to seeing you in that one. Welcome back to Backspace Academy. In this part of the lab, we're going to be looking at elastic network interfaces. So what they are is that they are a virtual network card. So just the same as you've got a computer at home, which will connect to the internet or connect to your local network, it will do that through a network card. So this is a virtual network card, and it is attached to our EC2 instances. Now we can create network interfaces, and we can attach those two instances, and we can detach them from that instance and attach them to another instance if we want. Now, every instance that is created in a VPC will have a primary network interface. Because that is a primary network interface, we can't detach that from an instance. If it was a secondary network interface that we attach that ourselves, then we could detach it and attach it to another instance. So what we need to do is that we need to first terminate that instance. But if we terminate that instance, by default, it will also terminate the elastic network interface. So what we need to do is we need to change the ENI delete on termination flag to false. So that means that we can then terminate that instance, and it will leave behind the elastic network interface, ETH0. What we can then do is that we can launch a new instance, and when we're going through our launch configuration of launching that instance, we can specify that elastic network interface as the primary ENI for that new instance. When we do that, all of the traffic that was going to that old instance that is now terminated will now go through to that new instance. And any elastic IP or public IP addresses that are associated with that ENI will also be then moved over to that new instance as well. Okay, let's go to the EC2 management console and have a look for this elastic network interface. So we scroll down and we go to the network and security section and click on network interfaces. there we can see there is our network interface that has been associated to that NAT instance. And we can see here also that it's also been associated with the security groups of DB Web Server and NAT Security Group. So what we're going to do now is just give this a name, just so that we can find it easy enough later on. So just cutting and pasting from the lab notes there. Okay. So what we need to do now is select it, and we need to change the behavior of that so it doesn't get deleted on termination. So we go Actions, Change Termination Behavior, and we get rid of Delete on Termination. So what that means is that when we terminate the instances that this is attached to, it won't also delete this Elastic Network Interface also. So we just uncheck that and click on Save. So now we go into our instances. And there's our NAT instance. And what we need to do now is we'll terminate that. After 5 minutes or so, our instance has been terminated. If we have a look back at our network interfaces, we can see that although the instance has been terminated, the NAT or the ENI, the Elastic Network Interface, has been left behind. So we can now use that ENI and attach it to a new instance. So we go back to Instances, and let's launch an instance. And we're going to go to the Community AMIs, and we're going to search, and this is in the lab notes. So just cut and paste this from the lab notes to find the ID for a NAT AMI. So just search for that and you'll find it. So just get the top one there, which will be a HVM. And for Amazon Linux, that is fine. We'll select that. This time we're going to select the T2 Nano. That will be fine. Next, configure instance details. So we need to select our backspace -lab VPC. We need to select the public subnet. Now, with auto-assign public IP, we'll just use subnet settings. We'll scroll down. And the reason we don't auto-assign a public IP is because we're going to be using the Elastic Network Interface from the previous instance, which will also have a public IP already associated with that. So when we put this ENI onto this instance, that public IP will automatically be enabled as well. So let's scroll down. So for ETH0, which is our primary network interface, we're not going to create a new network interface. We're going to select the one that we've got there. So the NAT ENI. And there it says we can no longer assign a public IP address to your instance. So that's fine because this ENI already has a public IP address associated to it anyway. So we'll click on Next, Add Storage, and Add Tags. So we're just going to add a tag now, and it'll be a name tag so that we can find it again. And we're just going to call it lab-nat. That will be fine. Configure the security groups. So we need to select those existing security groups. So we need to have the one for connecting to the database and also the one for the NAT, which is there. And we'll review it and launch. And launch. We'll select a key pair and launch instances, or launch the instance. Okay, so after about 5 minutes or so, it has finished launching. I'm just going to give it the same name as the other one, so just going to copy this name from here and put it into here. And probably delete that name entry there as well. Okay, that is now up and running. We've got a NAT instance, we've got a name on it. Let's just see whether that Elastic Network Interface actually did attach properly to it. So we just scroll down to Network Interfaces. So there's our NAT ENI. And if we scroll down, before we didn't have an instance associated to it, and here we have an instance ID. If we open that up, we can see that it's going to our NAT instance. Now, one thing that we may need to make sure is that we have the source destination check on this instance disabled, otherwise it won't work properly as a NAT. So we'll select that instance, we'll go to Actions, we'll go to Networking, and we change source destination check. So it's currently disabled, so that is what we want. So we'll leave that disabled and that will be fine. We don't want to enable that, otherwise our NAT will not work properly. Okay, so that brings us to an end of this part of the lab. We're getting close to the halfway point. So what we're going to do next is we're going to replicate these subnets and put them into another availability zone so that we can take advantage of high availability. I'll look forward to seeing you in that one. Welcome back to Backspace Academy. In this part of the lab, we're going to be replicating our subnets in US East 1A availability zone and creating another set of subnets in US East 1B availability zone. That way we can launch resources in multiple availability zones and take advantage of the high availability from doing that. Okay, starting off in the VPC console, we'll go to Subnets, create the subnet. We'll give this subnet a name. We'll call this one Public Subnet B because it's going to be in the US East 1B region or availability zone. We'll select the VPC backspace-lab and we'll select that availability zone of US East 1B. Now our CIDR block, it's going to be 10.0.3.0/24. So let's create that. And close. Okay, so we can see there we've got our public subnet B that has just been created. Now the VPC service would have automatically associated the main route table to this subnet, but we want to explicitly associate a public route table to this. So again, we'll select that subnet, we'll go to Actions, we'll edit our route table association. And so here we can have our route tables, and we're going to select the Backspace Lab public route table. And so there we can see it's going to allow local traffic within our VPC, and it's also going to allow traffic from the wider internet through our internet gateway. We'll save that and close. Now we'll create our private NAT subnet, the second tier of our VPC. So create subnet. We'll give that a name, private NAT subnet B this time. And again, we'll select our Backspace-Lab VPC. Our availability zone is going to be US East 1B. And our CIDR block, it's going to be 10.0.4.0/24. And we'll create that. Now this subnet will have the main route table implicitly associated to it, and we can leave that there because that's going to be a private subnet or a private route table with a route to a NAT instance as well. So we'll leave that as it is. And what we're going to do now is we're going to create the final private subnet. So we do create subnet. We'll give that a name again. And that will just be private subnet B. We'll select our VPC, Backspace-Lab. Our availability zone, again, US East 1B. Now our CIDR block this time is going to be 10.0.5.0 /24 and create and close. Now again, this will have had the main route table associated to it, but we want to have a lockdown private subnet, so we're going to change that. So we're just going to select that private subnet B, which is here, and we're going to change or edit the route table association, and we're going to select our private subnet route table there that we created. And so all that is going to allow is local traffic from our VPC and nothing else. So we'll click on Save and close. Okay, so we've created our 3 subnets, and the first one is going to have a public route to an internet gateway. The second one is going to have the main route table implicitly associated to it, and it's going to allow access to a NAT instance. And the final one will be a private subnet that we have created, and that will be locked down with just local traffic. So that brings us to an end of this part of the lab. Coming up next, we're going to be creating an elastic load balancer and an auto scaling group and launching that into our private NAT subnet. I'll see you in the next one. Welcome back to Backspace Academy. In this part of the lab, we're going to be launching an application load balancer that is going to span the multiple public subnets across multiple availability zones. That will receive traffic from the wider internet through the internet gateway, and it will distribute that traffic to instances inside of an auto-scaling group in the 2 private NAT subnets across multiple availability zones as well. Now, the launch configuration for those EC2 instances will have an AMI for the LAMP application. Starting off in the EC2 management console, we'll scroll down to load balancers, and we'll create a load balancer. We're going to select an application load balancer. We'll give our load balancer a name, and I just copied that from the lab notes. It's going to be an internet facing. It's going to receive traffic from the internet. It's going to be IPv4, IP addressing. We're going to have a HTTP listener. Now, normally in a production environment, you would no doubt have a HTTPS as well on port 443. But for the lab, I'm not going to worry about that for now, but normally you would do that and you would associate a certificate for that load balancer. So let's select our availability zones. So first off is our VPC is going to be our backspace-lab VPC. And we've got our 2 availability zones here that we can select. So US East 1A, we'll select our public subnet A, and US East 1B, and we'll select public subnet B as well. So there we go. Public subnet A and public subnet B is going to have our load balancers spanning those 2 subnets. So we just put in a tag as well for a name. And just going to call it backspace-lab ELB. That will be fine. Okay, next, configure security settings. Don't worry about that. That warning is just saying that you don't have a listener for SSL on there, but obviously, as I explained before, if it was a production environment, we would do that. Now we need to assign 2 security groups for this. So the first one, we'll get rid of this default VPC security group. The first one we need is the ELB security group, which will allow incoming traffic from the wider internet. And the other one there will be for communication between the Elastic Load Balancer and the auto scaling group. Next, we'll configure the routing. Okay, so our Elastic Load Balancer will need to have a target group to direct the traffic to. So we haven't created one, so we'll let the service create one for us. So new target group. We'll give it the name backspace-lab-tg. It's going to be an instant, but we can also use an IP address or a Lambda function as well, but we're going to use instances in our auto scaling group. The protocol, HTTP over port 80. So now we can register targets. Now, because we don't have any instances deployed yet, we don't have any registered targets. So we'll click on Next Review and Create. Okay, so there's our Elastic Load Balancer being created. Now we need to create some instances to receive requests from our load balancer. So we're going to scroll down to Launch Configuration. So we're going to create an auto scaling group, which starts with creating a launch configuration. And create launch configuration. We'll search for a community AMI. Okay, so there's one there, a Bitnami lamp stack. That will be fine. We'll select that. We'll leave it as a T2 micro. We'll configure the details. And we'll give it the name, backspace-lab-lamp launch. We won't be creating an IAM role. So next we can add storage. And next. Okay, so we need to associate these security groups to it. So first of all, we need to get our Elastic Load Balancing security group. So there is our communicating between the Elastic Load Balancer and the web server. We also need to have communication between the web server and the database. So we'll select that one there. So we've got DB web server and ELB web server. So these web servers will be able to communicate with both the database and the Elastic Load Balancer. And we review that. And we'll create that launch configuration. Just select a key pair. Okay, so now that we've created that launch configuration, we can now create an auto scaling group using that launch configuration. So that's what we'll do here by clicking on this. And we'll give that a name. And we'll leave it at 1 instances, that's fine. Now we're going to select our backspace-lab VPC and our subnets. We'll select our 2 private NAT subnets. So there we go. So we've got those 2 private NAT subnets in US East 1A and 1B. So we're going to launch these instances in that private subnet in the second tier of our VPC, and scrolling down to advanced details. So we want to retrieve traffic from 1 or more load balancers. And we'll select our target group, which is our backspace-lab target group. We'll select the ELB health check type. And we'll click on Next for configuring our scaling policies. So we're going to use scaling policies to adjust the capacity of the group. So we're going to scale between 1 and 4 instances. And we'll scroll down. So we need to scale the auto scaling group using step or simple scaling policies. So we'll just click this link down the bottom here. So we're going to create a new alarm that will trigger a scaling operation. So we click on Add New Alarm. We'll uncheck sending notifications because we don't really need to do that. We just want it to trigger an auto scaling event. So we're going to make it greater than or equal to 75% for at least 2 consecutive periods of 5 minutes. And create the alarm. And we need to add 1 instance there. So we just select 1. And we're going to put in another step there. So we're going to have it a stepped scaling policy, not a simple one, so that if it gets hit by a lot of demand, it'll step up and create even more instances if need be. So add step. And we're going to add 2 instances this time. And our CPU utilization will be from 90 to infinity. So if we get the situation where our CPU utilization is greater than 90, then it's going to add another 2 instances. So now we need to create a scaling event or scaling alarm to decrease that group size. So we add new alarm. Again, we get rid of the send notification to DynamoDB. So when it is not greater than, it'll be less than or equal to. And we'll make this 50%. And we'll make it 4 minimum periods. So we want it to scale up very quickly, but scale down quite slowly. So if our CPU utilization goes below 50 for 4 periods of 5 minutes, then it will scale down or create an alarm to scale down. So just create that alarm. And we're going to remove 1 instance when that happens. Now we'll add another step. So if it goes really low, then it can remove even more instances. So when it gets to 25, we're going to remove 2 instances. So now we can click on Next, Configure Notifications, and Next, Configure Tags. So we're going to put in a name tag here for the instances that are being launched. So we're going to call them backspace-lab web server. And now we can review that and create our auto scaling group. So we can see here that we've got our target group is our backspace-lab target group. Our initial group size is going to be 1, and our minimum group size, our maximum group size is going to be 4. And we can see we've got our scaling policy. So we're going to increase, and then we're going to decrease that group size, again, based on alarm. So we can create that auto scaling group now. And close. Okay, so if we have a look at the activity history, we'll be able to see there that it's successfully launching a new EC2 instance. So if we go to the instances, we should be able to see those, or see one of those. Okay, so there's backspace-lab-web server, and it's up and running. So if we go to our Elastic Load Balancer, we should be able to get the DNS name. So we'll just copy that. And there we go. Okay, so we've successfully created an Elastic Load Balancer. It is receiving traffic from the wider internet, from our browser, and it's distributing that traffic to a target group, which is an auto-scaling group of instances that have the LAMP application or the Bitnami LAMP application running on those. Okay, so let's just check if our auto-scaling group is working. So we're going to go into the EC2 instances, and we'll just terminate this web server instance and see whether it gets replaced. Okay, so if we go to here now, we can see that that has been terminated, but it should repair itself and launch another EC2 instance. So we'll give it a little bit of time to do that. So what we can do is we can check by going to our load balancer and our target groups. And there we can see we've got targets. And we've got no targets. But if we keep refreshing this, we will eventually get them coming up. Okay, so after a certain amount of time, we've got some registered, or got a registered target there. So we've got a target count of 1, and we've got one of these backspace-lab web servers that has been created. It hasn't passed its initial health checks yet, but it should still receive traffic. So if we go back to our web page and open that up, and there we can see. So we deleted or we terminated an instance, and it has automatically replaced that. The same thing will happen is if we hit that load balancer with a whole heap of traffic and it gets overloaded, the instances, it will create more instances as well. So that is working perfectly. So that brings us to the end of this part of the lab. Coming up next, we're going to be deploying a multi-AZ Aurora serverless cluster. So I look forward to seeing you in that one. Welcome back to Backspace Academy. In this part of the lab, we're going to be deploying a multi-AZ Aurora serverless cluster. And we're going to deploy that across multiple availability zones. And they're going to be across our private subnet A and private subnet B within a DB subnet group that will span those 2 subnets. Being a serverless cluster, it will have one endpoint that can be accessible from the private NAT subnet and the instances inside of that. Okay, starting off in the RDS console, we'll just click on the sidebar here to expand it. First thing that we need to do is we need to create a DB subnet group to launch our Aurora cluster into. And that DB subnet group must span multiple availability zones. So let's select that, subnet groups, create DB subnet group. We'll give it a name, just backspace-lab subnet group, give it a description. We'll select the VPC, backspace-lab, scroll down. So what we need to do is that we need to select our 2 private subnets at the tier 3, the bottom of our VPC. And those subnets will be only having the database launched into them, and they will only be accessible from within the VPC. So we select our first availability zone, which will be US East 1A, and we select our private subnet within that. So it will be our 10.0.2.0. So the 1.0 or the 0.0 will be our public subnet. The 1.0 will be our private NAT subnet, and the 2.0 will be our private subnet. So we select the 10.0.2 and we add that subnet to our DB subnet group. Now we select the other availability zone of US East 1B, and we'll select the subnet for that, which will be 10.0.5.0, and add that subnet again to our DB subnet group. So that's all we need to do, and we create that. And there is our backspace-lab DB subnet group. Now we can create our database. So we go to databases and create database. We're going to select Amazon Aurora. We'll leave that as it is and click next. And we're going to be creating a serverless cluster here. We'll give our cluster an identifier. Just backspace-lab-db will be fine. Enter a username and password that we can use. And click on next. So we're going to save money. We'll reduce our maximum capacity to 2. And we're also going to add additional scaling configuration options here. And what they're going to do is to pause the compute capacity when we're not using it. So if we forget to shut it down or whatever, after 4 hours, it will shut down for us. And so we won't be getting charged for our compute capacity, but we may be getting charged for any storage that is involved with that. So we'll scroll down again and we go down to Network and Security. We'll select our backspace-lab VPC, and our subnet group that we just created has been selected there for us. Now we'll choose existing VPC security groups. So we'll get rid of the default one there, and we're going to select the DB web server security group. So the only things that will be accessing this database will be either the web server instances or the Bastion instance in the private NAT subnet. So we'll select that DB web server security group, and we'll scroll down. And we're just going to undo or uncheck enable deletion protection. This is only a lab, so we want to be able to delete this quite easy afterwards, so we don't worry about that. But of course, if it was a production environment, then you would most definitely enable deletion protection, but we're going to leave it off and we'll create our database. So there's our database, and we can see there it has a status of creating. Okay, so after about 5 or 10 minutes, the status has changed to available. So let's click on the link to the database, and we'll scroll down here. So there's our endpoint. So if we need to access a database through a Bastion, that is the endpoint that we can use. Also, with our web server instances, if they've got an application running on them, you would have that set up as the endpoint for the database. And the good thing about using Amazon Aurora is that it is a single endpoint, no matter how many instances or compute capacity within that cluster has been created. Unlike standard Amazon RDS, if you're creating read replicas, you're going to have multiple endpoints, and you need to manage that using some other method. So this is the advantage of using Amazon Aurora, one endpoint, and you can access that quite easily. So that brings us to the end of this part of the lab. Coming up next, we're going to be launching a Cloud9 Bastion host. We're going to install some software on there that it's going to allow us to connect to this database and access that database directly if we need to. So I'll look forward to seeing you in that next lab. Welcome back to Backspace Academy. In this part of the lab, we're going to be using the Cloud9 service of AWS to create a Bastion host that we can use to connect to our RDS Aurora instances in that private subnet. Now, the Cloud9 service, we use it quite extensively in the Backspace Academy AWS Certified Developer Associate course, and we use it because it creates EC2 resources and creates a really handy development environment that has a lot of tools. It has SFTP to upload files. It has SSH to communicate through terminal. And it does that really out of the box for us. But the good thing about it is that it's very good for creating Bastion hosts as well. Because when we've finished using the Bastion host, the Cloud9 service automatically shuts it down when we're not using it. So that's quite handy from a security perspective, because when we have a Bastion host, we should just use it for the purpose that we're using it. When we've finished using it, we should shut it down. So what we do is it will launch that in the public subnet A. And because it's in the public subnet A, we can access that through our browser, and we can use that to connect into that private subnet. Okay, first thing that we need to do is go to the Cloud9 console, Services, and Cloud9. Okay, so what we can do now is click on Create Environment. We'll give our environment a name and a description and click Next Step. And we leave create a new instance for the environment. We'll select the T2 micro. That will be fine. We're going to select Amazon Linux. That will be fine as well. And we're going to also have this cost saving setting so that if we're not using the Cloud9 service, it will shut down. So we'll leave that at 30 minutes. So if we don't use the service, then the EC2 instance will shut down and go into hibernation mode. So that's going to save us a little bit of money. And we expand network settings. We'll select our backspace-lab VPC. So we're going to have to find out what that is. So we'll go back into the VPC console. Okay, so it's that one there. Which is that. Okay, so we'll select our subnet. And again, we'll just have to check that in the VPC console. Okay, so that one there. Okay. And we click on the next step. Okay, so we've got our name there, Backspace Lab Bastion. That's fine. It's an EC2 T2 micro. And Amazon Linux is going to shut down after 30 minutes if we don't use it. And let's create that environment. Okay, so after about 5 or 10 minutes, we've got our Cloud9 development environment has been created. So an EC2 instance will have been created, and this is basically a connection screen to that. So what we've got here is down the bottom, we've actually got a bash console. So just the same as we will connect using SSH and using bash commands here or Linux command line. We've got that here as well. We don't have to worry about setting up anything at all. It's all done for us. Another really cool feature here is that on the left-hand side here, we've got a file manager that is connected to our instance with SFTP, just the same as we would if we were using FileZilla or something like that. So we can directly upload files from here to our EC2 instance as well, which really makes it good for, or very easy to install software. So the first thing that we need to do now is that we need to make sure that we can connect to the RDS service or through the RDS cluster. So we need to make sure that there's a security group that allows that is associated with the instance. So let's go to the EC2 dashboard or EC2 console. Go to instances. And here we can see we've got our AWS Cloud9 instance there that has been created. We're just going to select that. We'll go to Actions and Networking, change security groups. And we'll select our DB web server security group. And we don't deselect the other one, so we neither leave the one that is being created there by the Cloud9 service, so we've got 2 there, and assign security groups. Okay, so now that's done. What we can do now is that we can install the software on our Cloud9 environment that will allow us to connect to the RDS instance using the MySQL shell. We'll just open up another tab here and go to the downloads page for the MySQL shell and just scroll down. The one that we want to get is not Windows, of course, because we're going to be putting it on a Linux instance. Okay, what we want is Linux generic. So although Amazon Linux is a CentOS or Red Hat type of Linux, use the Linux generic. It makes life a lot easier. All you need to do is just download a tar archive and extract it and just run that. So there's no installation process as such, and it works perfectly. So Linux generic and the 64-bit version, download that. Once that has finished downloading, we can just go back to our Cloud9 environment. We'll go to File, upload the local file, and just drag and drop that over onto there. Okay, so that's now uploading that. We can see there it's 43%, 45%, and it'll slowly come through. So that makes life a lot easier. So just close that now. Okay, so that's finished uploading. What we can do now is just go to our shell environment here, or our command line interface environment here. Just going to paste a command in here that's going to extract that file. So the command here is in the lab notes. Just need to make sure that this file name here corresponds with the file that you actually downloaded. And so we just click on enter and it will extract that. So once it's extracted that, it will create this quite long folder here, which is going to have our shell application in it. So this is a little bit long. I'm just going to shorten that a bit and just call it MySQL-shell. So I'm just going to cd into that now and go to the bin directory as well. And just have a look at what's in there. I'm just going to now connect to this RDS Aurora serverless cluster. So the command will be in the lab notes. You just need to change the endpoint that is in the lab notes to what yours is. So I'm just going to cut and paste from the lab notes, make it a lot easier. Okay, so MySQL-H. Then we put in our endpoint. And then we put in our port details and then our username, and we do a -D there, or sorry, a -P, so -U for our username, which is admin, and then -P, which will mean that we will be actually entering a password. So we just click on enter, enter in our password that we did when we created our RDS Aurora cluster, and enter. Now this will take quite some time if the RDS instance has gone into hibernation mode. So I'm just going to check that now. So I'll just refresh the screen. Okay, so we've got one capacity unit there. So it shouldn't take too long and we'll be connected in. Okay, so after a few minutes there, we've connected into our RDS Aurora serverless cluster. So now we can do some commands. So the easiest one to do would be show databases. So show databases, and make sure that we put the semicolon on the end of that. And there we go. So we have successfully created a Bastion host. We've uploaded files to that Bastion host using SFTP through the Cloud9 environment. We've used the Linux command line to actually run the MySQL shell, and we've connected into our RDS database. So that's quite good. And coming up next, we're going to be putting in even more security around this VPC by creating network access control lists that will be additional to the security provided by security groups. And I'll see you in that one. And welcome back to Backspace Academy. In this lecture, we're going to look at increasing the security of our VPC using entries in our network access control lists. Now, our network access control lists, they are associated to a subnet, unlike security groups, which are associated to an instance. So any instances that are inside of that subnet will receive the security that comes from that network access control list. And that is additional to what is provided by your security group. So it provides another layer of defense for your instances and any other resources that may be inside of that VPC. Network access control lists are stateless. What that means is, unlike a security group where traffic that is received and is allowed to be received, the return traffic will be allowed. With network access control lists, it doesn't work like that. So just because you receive traffic doesn't mean that the return traffic is also allowed. So you need to have both inbound and outbound rules that allow that traffic to occur. Now, although a request may arrive on a certain port, for example, HTTP on port 80, the responses most probably will be back on an ephemeral or a short-term or temporary port. And there's quite a lot of those ephemeral ports that are available. Traffic will be denied unless it is specifically allowed. And there are also deny and allow rules, unlike security groups, which just have allow rules. The rules are evaluated in numeric order, from the smallest number of that rule to the largest number. And what occurs is that when traffic comes in, it will be evaluated from top to bottom until a rule matches that traffic, and then that traffic will be either allowed or denied depending on what that rule states. If we go through the entire network access control list and none of the traffic is matched, then that traffic will not be allowed. By default, the network access control list will allow all traffic. So if you want to take advantage of this additional layer of defense, then you need to modify that default network access control list. Okay, so let's have a look at an example here. What we've got there is an inbound network access control list for a public subnet that is connected to the wider internet. So just say, for example, we've got traffic coming in for HTTPS on port 443. What will happen is that the first rule of the lowest number, which is rule number 100, will be evaluated first. So obviously it doesn't match that. We go to the next one, which is 110, and it matches that. So the evaluation process stops there and that traffic is allowed. Now let's say we get traffic coming in on port 500. The rules will be evaluated from the top there with 100. It won't match that. It won't match rule 110. It also won't match rule 140. But because we've got a wildcard deny at the bottom of the list, anything that is not matched will automatically be denied. And that rule, you cannot modify it and you cannot delete it. So anything that is not matched will be denied. Now, because everything is evaluated from top to bottom or from least number to the highest number, if you have a deny after an allow, for example, if we had a deny on port 80 and we had that at rule number 105, that traffic would be allowed even though there is a deny there in our network access control list. So that's something you need to be aware of. So whatever comes first is what wins out. So if we've got an allow before a deny, the allow will prevail. If we've got a deny before an allow, then the deny will prevail. But normally you would just list what is allowed and then you would let the wildcard deny pick up what else is left over. With our public subnet network access control list, now that is going to have our elastic load balancer in it. So it needs to receive traffic from the wider internet on port 80 and port 443. It needs to allow for return traffic on those ephemeral ports. It also needs to allow for outbound port 80 and 443 traffic. It also needs to allow for inbound return traffic on ephemeral ports to the bastion. And it also needs to allow for inbound port 22 SSH from the Cloud9 service IP address. And we'll look at that more. And it also needs to allow outbound port 22 traffic from the EC2 bastion host or Cloud9 bastion host to the web servers, and also outbound MySQL to, or from the Bastion host to our Aurora cluster, and also inbound from our MySQL cluster or our Aurora cluster to our Bastion host as well. Our private NAT, network access control list, that is going to contain our web servers in our auto scaling group. So that is going to receive inbound port 80 traffic from the Elastic Load Balancer. We can also allow for port 443 if we'd like to have security all the way through later on if we want. And outbound as well. And inbound local port 22 traffic from our Cloud9 Bastion host. And return traffic on the ephemeral ports. And also outbound MySQL on port 3306 from the web server instances to our RDS Aurora cluster, and also inbound as well from the RDS Aurora cluster to those instances as well. And also inbound requests from the Elastic Load Balancer on ephemeral ports, and outbound return traffic from the ELB on those ephemeral ports as well. And our third layer, the most private layer, our private network access control list, that is going to have to allow for inbound traffic from our EC2 instances to the RDS database, and outbound traffic from the RDS database to the EC2 instances, again on port 3306. It's going to allow for inbound local traffic from, or return traffic from our Bastion instance to the RDS database, and also outbound from the RDS database back to the Bastion instance as well. And again, we're going to have inbound return traffic on our ephemeral ports. Now, one thing that I get a lot when I do labs like this is people say, oh, why didn't you put this extra rule in there? And there's a whole heap of ways of skinning a cat here. And when you look at this one here, it would be just as easy to say, well, we just do an inbound and outbound rule for access within the VPC only. And that would be good enough. I mean, that would only allow access from within the VPC, and we could get rid of all of those. Or we could go even further and maybe look into fine tuning these ephemeral ports and what ones we need to have open and what ones we don't need to have open. But again, this is another layer of security. It's kind of like a little bit of a parachute in case something goes wrong. So you can go as far or as little as you want with these. And by default, they're just completely open. Now, before we actually get into this part of the lab, what I want to do now is actually just have a quick look at the flow logs or VPC flow logs that we created and see whether that is actually working and sending IP access data to our CloudWatch log, because we've been playing around a bit with the VPC, so there should be a little bit of activity being recorded there. So what we'll do is we'll go to Services and CloudWatch. Then we'll go to Logs. And there's our Backspace Lab VPC flow log. And there we can see we've got a lot of stuff happening there. So I've been playing around with this quite a bit before and trying to get a little bit of activity up here so we can have a look at. So let's have a look at this bottom one here and see what they look like. So we've got a whole heap of entries there of activity that's occurred on our network, which is pretty good. So if we just expand one of those, we can see there that we've got an Elastic Network Interface ID that it was accessed. We've got some IP addresses there. And whether it was accepted or not accepted. So accepted, okay. So that's quite good information if you're trying to find out why your resources are not working the way they should. So I'll just get out of that now and we'll jump back into the lab. So starting off in the VPC management console, what we'll do is we'll scroll down to our subnets. So we'll have a look at our public subnet A first. So we'll just have a look at that there. And we'll click on Network Access Controllers to have a look at what is actually associated to it. So here we can see that we've got something that says deny everything and something that says allow everything. So looking at that, because a deny overrides an allow, you would think that nothing is allowed. That's not actually correct. So what we've got here is we've got an allow rule that allows everything. So this deny rule, which has got the wildcard symbol here, it's not possible to delete that. But what it means is that if something is not specifically allowed by a rule, then it will be denied. But because our allow rule here allows everything, then this doesn't interfere with that because it's got this wildcard symbol here. It only applies to traffic that is not under any allow rule, any existing allow rule that is in there. So that's what that means. So currently, everything is allowed in and out of our network access control list or our subnet. So you can see they're the same for the outbound rules as well. So what we're going to do is we'll jump into network access control list under security here. And we're going to create a network access control list. So we'll give it a name. And we'll select our backspace-lab VPC. And we'll create that. So that just created a network access control list, which doesn't really have anything in there. So it's just denying everything by default. So we can see there. So the other one had allowing everything. This is just denying everything because there's no allow entries in there. So what we need to do is we need to edit these inbound rules. But before we do that, one of these inbound rules that needs to be allowed is for the Cloud9 service. So we need to find out what the IP range of the Cloud9 service is, and then we need to put that in as an inbound rule as well. So what we do, just copying here from the lab notes, and paste it in there. So this is a JSON file that defines all of the IP ranges for all of the AWS services. So we can see here, if we scroll down a little bit, we can see maybe what. Okay, so here we've got Cloud9, and we've got EU Central, AP, Asia Pacific, Northeast. So what we need to find is the Cloud9 IP addresses, and there'll be 2 of those for US East. Scroll a little bit further down. Okay, so there it is. So we've got these 2 here. So it's for this service, Cloud9, and the region US East 1. So we've got 2 IP address ranges, and they're the IP address ranges that are used by the Cloud9 service when we're using the US East 1 region. So we just need to copy those and use them for later on. So we'll jump back into the network access control list. We'll go to the inbound rules, and we're just going to add these 2 inbound rules for that Cloud9 service. It's going to add a rule. I'll call this 100. And it's going to be for port 22. So this is for the Cloud9 service to communicate with our Bastion or EC2 Bastion host in our VPC. And the source is going to be one of those IP address ranges. So we'll just get the first one there. So US East 1, that one there. And Cloud9. So just make sure that you've got both US East 1 and Cloud9 for the service. And we'll put that in there. We'll add another rule for the next one. We'll call this 110. So these raw numbers don't really mean anything, but they are read in order by the service. And then at the end of reading all of these, it will decide whether to allow or deny a rule. So again, SSH. And we'll put that second one in there. So that was the one we just got before. So this one here, again, US East 1 and Cloud9. Now, if we didn't put those in, the Cloud9 service just wouldn't work. It'll just come up with a blank screen or something. It just won't do anything at all. So you need to have that. So it's very important. So add another rule. So what else do we need there? So we need to allow all traffic on port 80. So I'll make that 120. So port 80, and just allow all traffic in there. And we'll call the next one for 443. And that's fine. So what else have we got? Okay, so we need to also allow for the return traffic on ephemeral ports. So we'll add another one there, 140. So that's just going to be a custom TCP rule. And that's going to be from 1024 to 65535. Okay, so we can save that. Now let's do the same for our outbound rules. Edit outbound rules, add rule. First one, we will allow port 80 access or HTTP. And the next one, we'll do 110. And again, that will be for HTTPS or port 443. And the next one there, 120, will be for MySQL. So port 3306, and that is going to be outbound to the private subnet. And so that will be 10.0.2.0 and then /24. And the next one will be for the private subnet or for MySQL outbound to the private subnet in the availability zone B. So that will be MySQL. There we go. And I'll just copy that. And that will be 10.0.50/24. The next rule will be for outbound on the ephemeral ports. So it's going to be a custom TCP rule. And the port range, 1024 to 65535. The next rule is going to be for outbound access from our Bastion host to our web server instances. So that is going to be for port 22 or SSH. And that is going to be to private net subnet A. And the next one, 160, which will be again SSH. And that is going to be to private net subnet B. So that will be 10.0.4/24. And then finally, we just click on save and that should be fine. Let's have a look at that. So we've got outbound, port 80 and 443, outbound MySQL to private NAT subnet A and private NAT subnet B. Sorry, no, going to private subnet A and private subnet B. Then we've got return or outbound traffic on the ephemeral ports. And then we've got port 22 access to private NAT subnet A and private NAT subnet B. And then finally, we've got our wildcard there to deny anything else that is not specifically allowed. Okay. The next thing we need to do is to associate this to our public subnets. So we edit subnet associations. And we need to select public subnet B and public subnet A. There we go. And edit. Okay, so now because we've changed the way, or we've restricted a lot of access, it's a good idea now to check that that everything still works. So what we'll do is we'll go to our Cloud9 and we'll just refresh the screen, see if that still works. There we go. So Cloud9 still works. What we'll do also is that we will go to the EC2 management console. And we'll go to the load balancer. And we'll just check that the load balancer is still working as well. So we'll just copy the DNS record there and go to it. And there we go. So our Elastic Load Balancer, which is in the public subnet, is still working. Our Cloud9, which is also in that public subnet, is still working as well. So let's do the network access control list for the private NAT subnets. And create network access control list again. We'll give it a name. Private NAT NACL \lab. That would be fine. Select our VPC, our \lab VPC, and create. And again, we'll go to our inbound rules. Actually, first of all, we'll select it. Make sure we select the right one first. So \lab private NAT NACL. And we go to inbound rules and edit our inbound rules. Add a rule. So the first one is going to be for port 80 or HTTP. And that is going to be from public or from the actual VPC. So it's going to be 10.0.0.0/16. So it's going to allow our local HTTP port 80 traffic. And 120, we'll do the same for HTTPS. And the next one. Now there's going to be for inbound traffic from our Bastion host in public subnet A. So make that 130, and that will be SSH. And that is going to be from 10.0.0.0/24. So that's going to be public subnet A. And we'll do the same for public subnet B. So that will be 10.0.30/24. And finally, we're going to have traffic on our ephemeral port. So 150, it's a custom TCP rule. And that's from 1024 to 65535. And we'll save that. Okay, so now we'll do our outbound rules. So again, edit outbound rules and add a rule. And the first one will be for port 80 or HTTP. And that's going to be from anywhere. And the next one will be the same for port 443. And the next one. And that's going to be for on the ephemeral ports outbound to the public subnet. And there we go. So that's going to be outbound to that public subnet on the ephemeral ports. We'll do the same for public subnet number B or public subnet B. And 130. And we'll just copy this from the other one. And this time we use public subnet B, which will be 10.0.30.24. And we'll save that. So again, what we need to do now, so we've got our private NAT NACL. We need to associate that with our subnets. So there we go, private NAT subnet A and private NAT subnet B, and edit. Okay, so now that we have changed that private NAT subnet that has our web servers inside of it, we need to make sure that that is still delivering traffic. So we just go to the EC2 management console and our load balancers, And we'll just select our load balancer DNS name. And there we go. So it's still working. We haven't broken it. If it wasn't working, you'd probably come up with a bad gateway error there. If you do get that, then you'll know what the problem is. So just go back in and check your entries there in your outbound rules or your inbound rules, and you'll no doubt find what it is. So just go close that. And the final one that we've got to do is for our private NAT subnet. So we just, again, create network access control list. Okay, so we'll give it a name, backspace-lab private NACL. So this is the network access control list for the final private subnets at tier 3 that are locked down, that contain our Aurora serverless cluster. And our VPC, again, backspace-lab, and create that. So we'll select it, that one there, and we'll inbound rules and add a rule. Okay, so the first one there, 100, is going to be a MySQL there we go, port 3306. And that is going to be from public subnet A. So that'll be 10.0.0.0/24. And the next one will be the same, but for the public subnet B this time. So again, MySQL Aurora 3306, and this is going to be for public subnet A, which will be 10.0.30/24. And the next one is again going to be MySQL Aurora. And this one is going to be for the private NAT subnet. So that's going to be 10.0.10/24. And the next one is going to be, again, a MySQL Aurora. And that's going to be on the private NAT subnet B, which will be 10.0.4.0.24. And then finally, we'll have a rule that will allow for the ephemeral ports. So for the Aurora service, it just needs to be from 32,768 to 61,000. And we'll save that. And now we'll do the outbound rules. So edit outbound rules and add a rule. So the first one is going to be for MySQL, again, 3306. And that is going to be from outbound to anywhere. And the next one, which will be the ephemeral ports again. And again, going back. So for returns on those ephemeral ports or on the MySQL port 3306. And we'll save that. Okay. What we need to do is that we need to associate that again to our private subnet. So again, subnet associations and edit subnet associations. And we'll select our private subnet A and private subnet B. And edit that. Okay, so because we've changed the private subnets that have the Aurora service in it, we need to make sure that we can still access that. So the best way to do that is to use our Bastion host again. So we'll go into here and we'll just see if we can show the databases again. There we go. So that is working fine. Okay, so it's done that, not a problem. Okay, so if you made it this far, you've learnt everything that you need from the lab. So all that needs to happen now is that we just need to go through and clean everything up. That way we're not going to get a big bill at the end of the month because there's some expensive services here. We've got elastic load balancers there. We've got an Aurora service cluster. We need to clean that all up. We don't want to leave that lying around and get a bill for it at the end of the month. So I'll look forward to seeing you in the next one where we clean all this up. Welcome back to Backspace Academy. You've finished the lab. Now it's time to clean everything up. So first thing we need to do is we need to delete our auto scaling group. Otherwise, when we terminate these instances, they'll just get recreated and it'll drive you crazy. So first thing first, get rid of that auto scaling group. Then we can terminate all of our instances. Then we can delete the NAT ENI, which will be left behind, and release that elastic IP address as well. We can delete the application load balancer. After that, we'll then delete our Cloud9 environment. Then we'll delete our Aurora serverless cluster. And then finally, we'll delete those VPC flow logs as well. If you want to go further and delete the whole VPC environment, you can do that as well. But you might want to leave it there for use later on if you want to. Okay, starting off in the EC2 management console, we'll scroll down to auto scaling. And we'll go to our auto scaling group. And we'll delete that. Okay, so now that that has been done, what we can do now is we can jump into the instances and delete those instances. Now we don't want to delete the Cloud9 Bastion host because we're going to delete that through the Cloud9 service. So don't delete that. So we've got here our Backspace Lab web server running. We've also got our NAT instance. So those two there, the web server and the NAT instance, that is what we want to terminate. So instance state and terminate. Okay, so after about 5 minutes or so, those instances have terminated. The only one left there running, which we're not going to touch yet, is the Cloud9 instance. Now, because we deleted that NAT instance, it has left behind the Elastic Network Interface and also the Elastic IP that is associated to that ENI. So we need to delete the ENI. So we go to Network Interfaces, scroll down. There is our NAT ENI, and we're going to delete that. So now we still have an Elastic IP address left. So we'll scroll down or scroll up to Elastic IPs. And I've got two there, so I don't need either of those. So I'm not sure which one it is, but I'll get rid of both of them because I don't need them. Okay, so that's done. What we need to do now is to delete our Cloud9 environment. So let's go back to Cloud9 and just click on up here and go to your dashboard. So there we have the Cloud9 environment. If you can't get there, just go to services and Cloud9 will take you there as well. So that's fine. We need to select this Cloud9 environment and click delete. And we just need to type in delete and click delete. Okay, so that's gone. Quite easy. The next thing that we need to clean up is our Aurora cluster. So we go to services and RDS. Go to databases after that. So there's our database and actions, delete. We don't want to create a final snapshot, so click on no for that and just acknowledge that we're not going to be taking a backup, and delete the DB cluster. So that will have a status of available and then goes to deleting, and eventually it will disappear from there. So that's working there. The next thing that we need to do is to delete our VPC flow log. So we go to Services and then VPC. And your VPCs. We'll select our backspace-lab VPC. And we'll select our flow log and actions and delete flow log. Okay, so now that we've deleted the flow log, we now need to delete the CloudWatch log group and the logs that it has collected. So let's go to CloudWatch. And logs. And select our VPC flow log group there. And actions, delete log group. And that's it. Now that brings us to the end of a very, very long 10-part lab. Now it's up to you now to download these lab notes and do it all yourself. Very important. And I'll look forward to seeing you in the next ones. Welcome back to Backspace Academy. In this lecture, we're going to be talking about Elastic Load Balancer, in particular, the ELB Classic type, and in further lectures, we'll talk about the other types of Elastic Load Balancers as well. To start off, we'll look at how we can encrypt our traffic to and from our Elastic Load Balancer using HTTPS or Secure Sockets Layer. Then we'll look at the automated back-end administration that we can set up with our Elastic Load Balancer to make sure that everything is healthy and receiving traffic as it should. Then we'll look at the configuration settings that we can set up to have our ELB customized for our specific application. Then we'll look at proxy protocol, which can send information concerning the client that is connected to our Elastic Load Balancer and send that information over to our backend instances and why we would want to do that. Then we'll look at sticky sessions, which can stick a session between a client that is connected to our ELB and our backends to make sure that they have a seamless session while they're connected. Then we'll look at monitoring, how we can make sure that our ELB is performing as it should and is healthy. And finally, we'll look at troubleshooting steps that we can take if something goes wrong. SSL or Secure Sockets Layer, that can be implemented on your Elastic Load Balancer architecture. And the easiest way to do that is to upload an SSL certificate to that ELB and associate it with that ELB. And then that ELB will receive encrypted traffic from your connected clients. It will then decrypt that traffic and pass it on to your back-end instances. There are two ways to implement this. First of all, you can use the AWS Certificate Manager to create that certificate, and then you can associate that with your Elastic Load Balancer. Or if you want a more difficult way, and this is the way that we used to do it before the Certificate Manager came along, is that you can use your own certificate from a certificate authority, and then you can upload that to the ELB yourself manually. That's a very complicated process, and I wouldn't recommend it because it doesn't really provide any advantage at all. To use the AWS Certificate Manager, what you need to do is go to the Certificate Manager console, or else use one of the many software development kits or the command line interface to request an ACM or Certificate Manager certificate from AWS. Once that's occurred and that certificate has been approved, then what you can do is go to the Elastic Load Balancer console, or again, use one of the software development kits or the command line interface, and then provision that certificate on the Elastic Load Balancer. Now this certificate, it must be in the same region as the Elastic Load Balancer is, and the user that is implementing this must have List Certificates API permission to associate that with the load balancer. If you already have a certificate for your domain that you would like to use and you'd like to upload that, and that was a certificate that you've got outside of AWS, the process is a little bit more difficult. First thing that you would need to do is that you would need to install certificate tools, and that would be OpenSSL or something equivalent. The next step is that you would need to create a server certificate and get that signed off by a certificate authority. So that process would involve you generating an RSA private key and then creating a certificate signing request, or a CSR, handing that over to the certificate authority to have that signed off. Once that's done, you could upload that certificate to your Elastic Load Balancer and then verify that that certificate is actually working. Okay, so here we have an example of how it would normally work. We would have our client would connect into our Elastic Load Balancer, and they would do that on port 443 with HTTPS, Secure Sockets Layer. And then at the ELB, we would have SSL termination that would receive that encrypted traffic. It would decrypt it and then pass it on to the relevant instance on port 80. And that would be HTTP traffic that would be unencrypted. So the way that looks in the management console is that on the load balancer that you would select, you would add a listener to there. And we can see there that we've got a listener. The load balancer protocol is HTTPS. The load balancer port is 443. And then it will be decrypting that. And the instance protocol that is being sent back out to the instances will be HTTP on port 80 there. In order for SSL to work between the client that is connected to the ELB and the ELB, the client and that ELB need to negotiate on what ciphers and what protocols are going to be used for that connection. There is a security policy that you will associate with that Elastic Load Balancer, and that will be used to negotiate the SSL protocols that will be used. If you don't define a security policy, then the default security policy will be defined for you. The SSL protocols that are supported include Transport Layer Security 1.2, 1.1, and 1.0, and SSL 3. If you enable server order preference as an option on your ELB, that will enforce cipher ordering. So what that means is that both your load balancer and your connected client will have a list of ciphers that they can communicate with. And so the load balancer will select the first cipher in its list that will be on the client's list of ciphers. By doing that, we're going to make sure that the security policy or the cipher that is used is going to be the one that we prefer. So always make sure that you use the latest predefined security policy. And that's important. For example, with server order preference, that will not be supported with the 2011-08 security policy. So if you've got that and you're trying to implement server order preference, it's just not going to work. So make sure that you always use the latest security policy on your ELB. A great advantage of using an Elastic Load Balancer is that it automates a lot of the back-end administration on our architecture through the use of health checks. So we can implement health checks that can check whether our instances are healthy or unhealthy. And the different status for those is in service and healthy, or out of service and unhealthy. If an instance becomes unhealthy, the ELB will stop routing traffic to it and will route it to another instance. When that instance becomes healthy, it will be added to those healthy instances and it will then resume receiving traffic from the ELB. Now there is a default health check configuration, or you can define your own custom health check. To do that, you'll need to first define the protocol, port and path to that health check, the response timeout for these health checks, the interval between health checks, and also the unhealthy to healthy threshold. And that is how many consecutive failed health checks that will be required to make that or to bring that instance out of service. Or it could be how many past consecutive health checks that will need to bring it back into service. An ELB health check is additional to an auto-scaling health check that you may have implemented on your auto-scaling group to automatically scale in and scale out the size of that group. And if you like, you can also replace that auto-scaling group health check with the ELB health check instead and use the ELB health check to expand and contract that auto-scaling group of instances. You can manage the security of your ELB by using an ELB security group. Now, my original AWS account goes back to around about 2010. And back then we didn't have VPC. We had something called EC2 Classic, and we shared that cloud with other users. So it wasn't as secure as it is now with VPC. But that said, you still need to know about EC2 Classic because you may go into a company that has a very old account and you need to understand that. So if you've got an ELB operating on EC2 Classic, it will use a fixed security group for those back-end instances and the ELB. If you're using a current AWS account, which of course you most likely will be, and you're most likely putting your Elastic Load Balancer inside of a VPC, then you'll be creating your own security group and associating that with the Elastic Load Balancer. So here we can see we've got our Elastic Load Balancer that is receiving traffic from the wider internet, and it's going to have an inbound rule for that. And that traffic is coming on port 43, and that is going to allow inbound traffic coming into that load balancer listener port for HTTPS traffic. Now we also need to have an outbound rule to allow the Elastic Load Balancer to send traffic out to our instances that are behind our Elastic Load Balancer. So the first thing we need there is for port 80 to allow that traffic to go to those instances and to receive traffic to those instances. And then the next one we need to do is that we need to send out from our Elastic Load Balancer our health checks. So depending on how we've got that health check set up, and in this situation, we've got it set up on port 80. So we need to allow traffic outbound on that port for those health checks to be conducted. There are a number of configuration settings that we can define for our Elastic Load Balancer. The first one there is the idle connection timeout. If no data is received within that defined idle connection timeout period, the Elastic Load Balancer will close that connection. And so the default for that is 60 seconds. Now, one thing to really take into consideration is that if you're implementing HTTP, which of course you no doubt will be, it's recommended to have a keep alive timeout option enabled. So what that does is it enables the load balancer to reuse those existing instance connections over that period of time. And what that does is it reduces the CPU load on those back-end instances. So the recommended there is greater than 60 seconds, but you need to make sure that it is greater than the idle connection timeout period that you have defined. Connection draining allows you to keep your existing connections to your instances open even when they're about to become deregistered or they have a status of unhealthy. Now, the reason we would want to do that is that, for example, if we've got a client connected, he's communicating with an instance and has sent a request to that instance, we would like the instance to have a good opportunity to respond to that request. For example, there might be an intermittent fault that has made that instance unhealthy, or it could be responding to an auto-scaling event or something like that that could interrupt that connection. So to keep that open, that will allow us to complete those in-flight requests that have come in from our client through to that instance, and also from the other way back as well. So the ELB state, when this is occurring, when we've got connection draining in effect, it will say in service, instance deregistration, currently in progress. So the way that we do that is that we define a timeout period, and that can be anywhere from 1 to 3,600 seconds or 1 hour. Now, after those in-flight requests have been completed, or the connection draining timeout period that you have defined has been exceeded, then the ELB state will change to out of service, and then instance is not currently registered with the load balancer, and the load balancer will no longer be sending requests or waiting for return responses from that instance. Cross-zone load balancing is another great feature that you might want to consider if you've got your elastic load balancer spanning multiple availability zones. And of course, you would always want to do that anyway. It is a good practice to make sure that you have your architecture across multiple availability zones. Now, by default, requests coming into an elastic load balancer will be distributed by that load balancer across the availability zones. So that's fine. But what happens if, for example, we have one availability zone is more loaded than the other? It may have more instances in one availability zone than in another availability zone, or one availability zone might have got a lot of long running requests, and so that has taken away a lot of the instances that are available. How can we make sure that we're getting the most out of all of those instances across all of those availability zones? And so that's where cross-zone load balancing comes in. And so within our elastic load balancer, we're going to have nodes that distribute that traffic. And so looking at our diagram there on the right-hand side, that we can see that without it, or with it disabled, that traffic is going to be distributed from the nodes within that availability zone to the instances within that availability zone. But when we have cross-zone load balancing enabled, those nodes, for example, we can see here in availability zone B, if there are no available instances, then that node will then select an instance from the other availability zone. And we can see there, it's selecting an instance from availability zone A. And that way we're maximizing the utilization of those instances across both availability zones. And so cross-zone load balancing determines how the load balancer selects an instance. And when it is enabled, those nodes within that elastic load balancer will select that instance regardless of what the availability zone is. One thing to take into consideration when using elastic load balancers is that when a client connects into an elastic load balancer and it's had its traffic transmitted through to that back-end instance, that may change, that situation may change, and you might get an auto scaling event, and all of a sudden that client is no longer communicating with that particular instance, but with another instance. And so that's very important if we want to maintain connections between a client and a specific back-end instance. And that's very important when it comes to new technologies such as WebSockets, which maintain a live connection between the client and that back end for transferring of data. And you see that a lot in modern web applications, such as, for example, the Gmail application, where your inbox will be updated even though there is no page refresh going on. It's just automatically got that live connection that allows that to happen. And so proxy protocol can be used to carry connection information from that source to the destination. Now, normally, the header information that is sent over from the elastic load balancer to the instance contains the IP address of the load balancer. It doesn't provide the information of the originating client that connected to the load balancer before that information was sent over to the back end. And so what proxy protocol does, it adds a human readable header to the request header that is sent to the instance. And that provides connection information such as the source IP address of the client that is connected to the elastic load balancer, the destination IP address, and the port numbers. And proxy protocol, it is a single line that is added, and there is what it looks like. Now, one thing to take into consideration is that your back-end instances need to support proxy protocol. So if you've got for example, an Apache web server, and that's not going to support proxy protocol. And so that's going to create a problem. It just won't work because it won't be able to process that proxy protocol information. But if you've got a modern Nginx backend, then that will support proxy protocol and it will be able to communicate with that elastic load balancer. As we discussed previously, it's very important to take into consideration the session state of your application. And so what that means is that we might be connected to one instance and then all of a sudden we are connected to another instance, and that instance doesn't have the temporary information that was saved by that instance when it was connecting with that client. So sticky sessions enable the load balancer to bind a client session that is connected to that load balancer to a specific back-end instance, and it will maintain that unless the instance becomes unhealthy. And in that situation, then the stickiness moves to another healthy instance instead. There are two types of sticky sessions. We can have duration based, which is what we would normally use, and that is where the elastic load balancer itself will create a cookie named AWS ELB, and that cookie will be used to map that particular session to that particular back-end instance. If it is a new connection and no cookie is present because of that, then the load balancer will simply use the instance that has the least load. The other way that we can implement it is through application controlled. And that way, the application generates a cookie with its response, and then the elastic load balancer will insert a stickiness cookie within that. And of course, the same thing again, if the application does not generate a cookie, then that session will not be stuck to that particular instance. And the ELB will simply, again, use the instance with the least load. In the same way that we can measure the performance of our EC2 instances using CloudWatch metrics, we can also measure the performance of our elastic load balancer with a number of CloudWatch metrics. And those will be measured by the elastic load balancer and sent over to the CloudWatch service every 60 seconds. And the CloudWatch metrics include the healthy hosts and unhealthy hosts, the request count and the latency for those requests. We can also have information about how much that elastic load balancer service is actually under pressure. We can see the surge queue length and the spillover count from that elastic load balancer. We can also see the number of HTTP errors and the back-end connection errors, and we can monitor those and view those in the CloudWatch console as a dashboard. You can also enable access logs on an elastic load balancer. And when you do that, the ELB will publish a log file for each of those access connections to that load balancer. And those will be within 5 to 60-minute intervals, and they will be saved as a log file to Amazon S3. And finally, we can also look at the API calls that are going to our elastic load balancer as well, and we can log those using CloudTrail. There are a number of ways that we can troubleshoot our elastic load balancers when something goes wrong. If we're using the API or one of the many software development kits, we may get some API errors coming back. The first one there, we've got certificate not found. So what that normally means is that our certificate is not valid, is expired, or it actually does not even exist on our or associated to our elastic load balancer. The other one there could be out of service, a transient error, and that is generally a problem with your load balancer that is temporary and normally fixes itself after a short amount of time. We can also get a number of HTTP errors coming back from requests. So we can have 400, which would be a bad request. So the client that is connected to the Elastic Load Balancer has put forward a bad request. We could have a 405, method not allowed. And so again, the client has put in there a method in the request header that exceeds the maximum 127 characters. A 408 error will be a request timeout. And so that means that the client itself that is connected has, for some reason, cancelled that request, or that request was interrupted midway through making that request. 502, bad gateway. And that generally means that the instance has responded with a malformed response. 503, service unavailable. And that would normally mean that the load balancer is overloaded, or there are no available healthy instances available to respond to any requests. A 504 gateway timeout error will mean that the connection was closed because of a timeout error for a response. Now, all of these, you don't need to write them down because they are all in the troubleshoot your load balancer section of the Elastic Load Balancer developer guide. So if you go to there, there'll be a chapter there called troubleshooting your load balancer, and that will detail all of this. All I've done here is really just captured it in a more concise format for you. If you're using CloudWatch to monitor your Elastic Load Balancer, you may want to have a look at the response code metrics. So we're going to see there ELB for XX, so that is going to be request errors. So they're going to be client-side errors. A client that is connected to the Elastic Load Balancer has made a bad request, or hasn't finished that request, or has had that connection interrupted while they were making that request. We have ELB 5XX there, and they will be load balancer or instance errors. So that's back-end errors. We have back-end metrics. So we would say back-end to XX, whatever that may be. That will be that a successful response was sent back to the client from the back end. If it's a 3XX, that means that the response was redirected by the back end. If it's a back end 4XS, that means that the back end has sent a client error back to the client. If it's a 5XX, then that will be a server error response that has come back from the instance, and the ELB has forwarded that back to CloudWatch. We can also have a look at the health checks and see how they are failing as well. So the first one there is the health check target page error. So if we've got our health check to check on a certain page within our website, there might be a problem. That page may not exist, or we might have made a mistake like that. Or there may be an application error that is stopping that page from being seen. The next one there, connection to the instances has timed out. So for whatever reason, our instances are not responding to those requests. So we would again need to look at maybe our firewall settings, or maybe our application. There's a problem there. It's not responding to these instances. Next, we've got SSL, public key authentication is failing. So there is a problem there with our SSL public key. It's not the correct one, most probably. Instance is not receiving traffic from the load balancer. So you need to make sure that the security group that is associated with that instance allows that traffic from the load balancer. And also make sure that the subnet access control list also allows that traffic come in from the load balancer. We could also have ports on the instance are not open. We may have, for example, our Linux firewall settings may not be allowing access on that port. So we would need to check our firewall settings and make sure that that is correct. We may also have a situation where our instances in an auto scaling group are failing the Elastic Load Balancer health check, but they are actually not failing the auto scaling group health checks. And so that would most probably be a problem with your application. For some reason, your application is not processing those health checks properly. If you have connectivity issues, for example, you have a website and you can't access it through a browser, make sure that your Elastic Load Balancer isn't located within a private subnet. Make sure that the security group allows traffic and the access control lists also allow traffic. If you have problems with registering instances, first thing to check is make sure that the health checks are correct and make sure that your instance is not failing those health checks. Another thing that can cause instance registration issues is if there's a problem with the AMI that you're using. So make sure that you're using an AMI that you're allowed to use. So again, all of this stuff is in the Troubleshoot Your Load Balancer chapter of the Elastic Load Balancer Developer Guide. So that brings us to the end of another big lecture. Hope you got a lot out of it, and I look forward to seeing you in the next one. And welcome back to Backspace Academy. In this lecture, I'm going to talk about application load balancers, which are a new type of load balancer that have been introduced by AWS, and it provides us a number of advantages. So we'll talk about the different options that are now available for us with load balancing, and then we'll talk about how an application load balancer can provide us with some significant benefits when we're running multiple applications. We'll talk about path-based routing and how that can reduce the number of load balancers that we need within our architecture. I'll also talk about the different options that we can route our requests to. We can route to IP addresses, we can route to microservices, we can route to different containers that are on a single instance. We have multiple targets, and we'll talk about what that means and the routing rules that we can set up that define how our requests are routed back to our back end. The load balancer options that are available to us include the original classic load balancer. Now that has always operated at both layer 4 and layer 7, but it's only provided really limited functionality at layer 7. So at layer 4, it's been offering us a standard TCP support, but also at layer 7, it's giving us HTTP and HTTPS support as well. But it doesn't support WebSockets, and so that is obviously a limitation at that layer 7 functionality. It supports VPC and EC2 classic instances. And the next option there we have is the network load balancer, which is another new load balancer option for us, and that operates specifically at the lower connection level, or layer 4 of the OSI model. And so that supports TCP, and it's just grabbing packets and forwarding them straight onto our back end. It's very low level, but it also supports WebSockets. Now WebSockets, they are in fact a layer 7 functionality, but it does also support WebSockets, but it doesn't support HTTP either. So we also have it supporting VPC only. It doesn't support the older EC2 classic instances. And there is another feature there that both the network and application load balancers have, and that is that it has load balancer deletion protection in case you accidentally delete that load balancer. So the one that we're going to be looking at in this lecture is the application load balancer, and that operates at the individual request level at layer 7 of the OSI model. And it's working very closely with our application. It's doing more than just grabbing packets and forwarding it on. It's putting those packets in a format back that our application can receive them. So it's going to be supporting HTTP, HTTPS, and also the new HTTP2, which is going to provide very good page load speeds. And it's also supporting WebSockets, which the classic load balancer doesn't support. It only supports VPC instances. It doesn't support EC2 classic instances. And again, it provides load balancer deletion protection. If we're looking to run multiple applications, if we're doing it with a classic Elastic load balancer, what we would normally do is we would have our domain name service, our Route 53, and we would separate that into two separate domains. So over on the left-hand side here, you can see we've got our images domain, and over here we've got our app domain. So if we have our images domain, that will be serving our images, and our user interface functionality and all that will be served through our app. So if any requests come in for images, they're obviously going to come in through this classic load balancer here and then distributed onto one of the available instances, and likewise for any requests for the application. So that works, but the problem is that we are duplicating what we're doing here. So we basically have one Elastic load balancer over here and a second Elastic load balancer over there. Now with path-based routing, which is a feature of the application ELB, we can actually use one elastic load balancer, and the elastic load balancer will distinguish where that request has to go to depending on what the path is in that request. So if we have mydomain.com, they're all going to be coming in, and then if the path has images, the elastic load balancer will automatically know to send that through to this target group of instances over here. If it comes through with a path of app, then the application elastic load balancer will do the same for an available instance there as well. So what that means is that we're only using one application elastic load balancer as opposed to using multiple elastic load balancers for each one of those applications that we're running. So that's going to provide significant amount of a reduction in costs if you've got multiple applications that you're running. Another feature of elastic load balancers is that they can actually route to individual IP addresses. They don't actually have to have an instance. You can still register an instance with an elastic load balancer, but you can also register an IP address. So that can't be a public IP address. So you can't go and get something out in your on-premises database or whatever and route that. What you can do is that you can use one of the types of private IP addresses there that I've got listed, and you can use those to register with the load balancer. And so what will happen is that when we have our app or requests coming in for our app, they will come in through the application load balancer and go through to that IP address for that instance. Now, not only can we have multiple applications running through a single application load balancer, we can also have multiple applications running on the same instance, and we can register an instance and port combination for that application. So what that means is that if we have our app over here, so our request coming for our app, we can have that running on a microservice on an instance here, and then we can have our elastic load balancer set up so what it can do is it can receive requests for the app, and it can forward those straight through to that individual port or that application that is running on that port of that instance. And then we can do the same with another instance. So what that means is that if, for example, our images are not as busy as our app or vice versa, we are still distributing the load very evenly across these instances. So we're not going to have one side of this infrastructure that's going to be very busy and the other side not. So it's going to create some very good advantages for reliability and for efficiency as well. Another very good feature of the application load balancer is that it can actually run multiple containers on an instance and route or load balance across that as well. In a similar way that we would have multiple applications and we would register a port and an instance combination, we can do the same with a container that is running or multiple containers that are running on an individual instance. So again, we would have our application over here, and if my domain has app in its path, then those requests will be coming in through and they will go to that ECS container that is running that application and the port combination for that. If you are using the ECS service to do that, it's quite good because the ECS service will manage all that for you. It will allocate the port and it will register that with the application load balancer for you. So with elastic load balancers, we still have listeners as we have before with a classic load balancer. So we would have a port 80 listener and a port 443 listener there if we're looking for HTTP and HTTPS traffic. And so that again defines a protocol and port for those incoming connections. But we also have what we call targets and target groups. So a target can be anything. It can be any combination of an instance. It could be a microservice, so a combination of an instance and port. It could be a container, or it could be one of those private IP addresses that you can forward requests to. So what we would do, we would set up a target group with targets inside of it, and then we would register that with our application load balancer according to that path. So if we have our path here for images, that would be registered with that target group. So anything that's coming in for images will get forwarded onto that target group. If we have listeners and we have target groups that are going to receive those forwarded requests, we need to set up rules, and those rules will be defined at the listener. And so if we have, for example, there we have our port 80 listener, we can set up a rule that for any requests that come in on port 80 that have the path of images, so over here we have images, we can have that rule make a decision for the Elastic Load Balancer to send those requests or to forward those requests on to an available target within that target group. And likewise, we can have another rule set up to do the same for the app path as well. So that's about all I need to discuss for now about application load balancers. We're going to have a hands-on lesson now, and I'll see you in the next one.
Please note that this content is targeted for solutions architects and SysOps administrators. If you're a developer, you may want to skip over this one.
And welcome back to Backspace Academy. In this lab, we're going to create two EC2 servers, one of them running the WordPress application, and then another that'll be running the Magento application. Once we've done that and we've got those set up and running, we're going to put an application load balancer in front of those, and then we're going to put them inside of a target group and then implement path-based routing for requests that have to go to either that WordPress application or the Magento e-commerce application. Okay, so starting off now in the EC2 console, I'm just going to create these two instances. First one being for the WordPress application. So we just go into the AWS marketplace and we'll just search for WordPress. And we'll just grab that Bitnami one there. We'll select the T2 micro and we'll give it a public IP address. And we'll leave storage as it is. We're going to add a tag just for the name of those instances. And we'll call this one WordPress. And we'll just create a new security group there. And we'll launch that. Okay, now we'll just launch our Magento server as well. So again, we go into the marketplace and just search for a Magento AMI. That one will be fine from Bitnami. And again, a T2 micro will be okay. We'll give this one a public IP address as well. And we'll give it a name as well. So name has to be with a capital N at the start as well. And a new security group will be fine, and we'll just launch that. After a certain amount of time, those instances will be up and running and have passed their status checks. So we'll just have a look at the Magento one, and if we go to the public IP address for that one and have a look at it, we can see there that we've got the Luma standard template for Magento there. So Magento is working fine. And we'll just check that the WordPress is working as well. So just go to the public IP address for that. And there is the WordPress front page. So everything seems to be working fine. So the next thing we'll do is that we will create targets for our load balancer. So we go into target groups. And we create a target group. So the first one we'll call WordPress. And we'll just leave that as it is and create that. And we'll create another target group. And that one, of course, will be Magento. And create that. So now that we have our target groups created, we need to add targets to them. So we'll go to the Magento one and we just click on the Targets tab and we edit that. And then we can select our Magento target there, or our Magento instance. And we can add to registered. And there it is up the top there. And then we just click on Save. And we do the same for WordPress. So we select the WordPress target or target group. We click on Edit. And again, we select the WordPress instance. We add to registered. And it comes up the top there and we save that. So now when we look at our WordPress target group, we can see that there is actually a target in there, which is our WordPress instance. And the same with our Magento. We can see there that we've got that Magento instance there. So we have our target group set up, and we also have our targets inside that being the relevant instances. Now what we can do is start creating our load balancer. So we click on Load Balancers and Create Load Balancer. Now we have the three options there. So we've got our application, our network, and our classic load balancer. Of course, we're selecting here Application Load Balancer. And we'll call this one blog. We'll be fine. And we'll just leave it with a port 80 listener. And our availability zones, we'll select all of the availability zones. Even though we've only got instances in one availability zone, we'll select all of them, and the Elastic Load Balancer will look after that for us. You just click on Configure Security Settings and Configure Security Groups. We'll create a new security group and we'll leave that as it is. So now we've got to configure our default route for the Elastic Load Balancer. So when requests come in and there is no actual rule for that particular request, by default they will go to this actual route. So we want them to, by default, if there's no other rule, we would like it to go to our WordPress site. And so we'll just do there, existing target group, WordPress, and that will be fine. And register targets, and we can see we've already got an instance there that we've registered before with that target group anyway. We review, and then we can create. So now we've created our load balancer. And we've got a default route so that when something comes through, it can go straight through to that WordPress site, but we haven't got it set up to handle requests to our store, to our Magento site. So what we've got to do is we've got to do that. So what we need to do is we select our Elastic Load Balancer, we click on the Listeners tab, and we go to our existing listener that we've got there, and we need to view edit rules. Because we can see there we've got our default, which is forwarding to WordPress. So now we need to view edit rules and add another rule for that. So we click on Add Rule and Insert Rule. We select Path, and the first path will be, we'll call it Store. And that forwards to Magento. And we'll save that. Now we need to do another rule, which is for everything below store. So again, we select path, and we do store, and then we do / and then the wildcard symbol. And that again will forward to Magento. So anything that has store in its path will get forwarded through to our Magento site. So that's fine. Now we can go back to our load balancer. And what we can do now is that we can go to the DNS name for our load balancer, and we should see our WordPress site. And there we have our WordPress site, as we would expect. So now we need to do is put our path for store and see what happens. Okay, so it's directed to our Magento site. We can see there we've got the Luma template for Magento. It has said that it cannot find that actual page, and the reason for that is that the the URL for the homepage that is set up in the Magento software will not be the same as what we've got here. So if you're going to do this for real, you would go back into your Magento software and make sure that the homepage setting for Magento will be the same as what you've got up here. So that brings us to an end. What we'll do now is we'll go through and delete everything to make sure that we don't get a nasty bill at the end of the month. Now, the first thing we need to do is to first off delete our load balancer. So we go Actions, Delete. And that's gone. Now we need to delete our target groups. So we'll select our target groups there and we'll delete those as well. And they're gone. And then once we've done that, we can then delete our instances or terminate our instances. So we just select both of those and we'll terminate both of those instances. Okay, so that brings us to the end of this lab. Hope you've enjoyed it, and I'll see you in the next one. And welcome back to Backspace Academy. In this lecture, I'm going to talk about another one of the newer Elastic Load Balancer services, being the Network Elastic Load Balancer. I'll look at where it fits in and the differences between it and the application and classic Elastic Load Balancers. And then I'll look at how we're going to use a command line interface to launch one of these network elastic load balancers. Now, the network load balancer, it operates at the connection level, at the lower layer 4 of the OSI model. So it's just grabbing packets and it's forwarding those packets straight onto our back end. It's not doing much of the layer 7 at all. It supports TCP at that lower layer 4 level. But it also supports WebSockets, which is also a layer 7 functionality, but that is all that it supports at layer 7. It only supports VPC instances. It does not support EC2 Classic. Network Elastic Load Balancers can handle millions of requests per second, and they are designed to handle sudden spikes in demand. So they are the highest performing in this area of the 3 ELB options that are available to us. You can have a static IP for your Elastic Load Balancer, and you can also assign an Elastic IP address to your Elastic Load Balancer or your Network Elastic Load Balancer. It only supports TCP and WebSockets. It does not support HTTP or HTTPS. It does not support path-based routing as you have with application load balancers. It cannot have a configurable idle connection timeout. It does not do cross-zone load balancing. It does not do SSL offloading, and it does not do sticky sessions, and it doesn't do back-end server encryption. So this is a very simple Elastic Load Balancer, but because of that, it can provide you with millions of requests per second in capability. Now, there are some similarities between network and application load balancers. They both have the concept of targets and target groups. They both support microservices. They can have multiple applications running on an instance, and you can register an instant and port combination. They also can both use ECS containers and IP addresses as targets. And they both also have load balancer deletion protection. Now you can launch a network load balancer through the console or also through the command line interface using the AWS ELB v2 command. So there we have create load balancer and the command for creating a target group for that load balancer and how to register targets into that target group, and also the AWS ELB v2 create listener command to create a listener for that load balancer. So what we'll do now is we'll have a bit of a hands-on session and we'll just have a quick go over how to create one of these network load balancers. I'll see you in the next one.
Please note that this content is targeted for solutions architects and SysOps administrators. If you're a developer, you may want to skip over this one.
And welcome back to Backspace Academy. In this lab, we'll be implementing a network load balancer, and we'll also be putting it in front of an auto-scaling group of EC2 instances. So first off, we'll create a target group for that network load balancer. And then we're going to also create an auto scaling group, and that will automatically launch EC2 instances based upon demand. And then once we've done that, we'll create a network load balancer and we'll set that up so that it can forward requests to the target group and then on to the auto scaling group EC2 instances. Okay, so here I am in the EC2 console. Just scroll down to target groups, and we're just going to create a target group in the same way that we would for an application load balancer. So we create target group. We'll give that target group a name. And our protocol is going to be TCP because a network load balancer cannot support HTTP or HTTPS. We'll leave port 80 as it is there, and we'll leave target type as instance because we have a choice there of instance or IP, and we're going to be directing it to instances. And our health checks will also be on TCP as well. So we'll just create that target group now. Okay, so that's created that for us. Now what we'll do is we'll now create our auto scaling group. So the first thing we need to do is we'll go and jump into launch configurations. So what our launch configuration is, it describes how our EC2 instances are to be launched, what AMI they're going to be using, what instance type, and all that sort of thing. Just the same as you would manually launch an EC2 instance, it will do that automatically for us. So we just click on create an auto scaling group, and then we can create our launch configuration first. We're just going to use the Amazon Linux AMI. These servers are not going to be doing anything as such. We're just going to get them up and running and register them in this auto scaling group. Okay, so we'll select a T2 micro. We'll give this a name. We'll leave everything there as it is, and we'll just go to add storage. We'll leave storage as it is. Now, with our security group, we're going to create a new security group, but we need to add a rule to this one. So we need to have TCP traffic on port 80. And we'll just select anywhere for that. And now we've finished our launch configuration. We can review that. And create launch configuration. We just select a key pair. So now we have defined our launch configuration. So our auto scaling group knows now how to launch these EC2 instances, what key pair to use, what instance type to use, what AMI to use, and what security group to use. So what we're going to do now is actually create this auto scaling group now. So we'll give it a name. And we're going to start with one instance. That will be fine. And now we'll add our subnets. So we're just going to add all of the subnets in here. And we click on Advanced Details. And what we do is we're going to receive traffic from a load balancer. And our target group will be our network ELB target group that we created previously. And our health check type will be from the Elastic Load Balancer, so we select that as well. And we leave the rest as it is, and we click Configure Scaling Policies. So now we're going to use a scaling policy to adjust the capacity of the group. So what a scaling policy is going to do for us is that as demand increases on our EC2 instances, then more of these EC2 instances will be launched, and as it goes down, it will scale in and reduce the number of EC2 instances. So the metric we're going to use for that will be the average CPU utilization, and we're going to scale between 1 and, say, 6 instances. And our target value, we're going to put in there 50%, which will be 50% utilization is what we want all of our EC2 instances to be around. And we're going to give it 300 seconds or 5 minutes to warm up after a scaling event has occurred. Now we can just jump now to review and create auto scaling group. And that's successfully created that for us. Okay, so now we can see we've got our group ELB, the name for our auto-scaling group, and it's using the launch ELB launch configuration that we named launch ELB to launch EC2 instances. So we've got here our desired is 1, our minimum and maximum that we're going to have available, depending on what the demand is 6, up to 6. So we currently have no instances, so we just refresh that. And we've got one instance now being created. So if we go into instances, we should see that one has been created by the auto-scaling group. And there we can see it's running and it's still going through its initializing checks. So what we can do now is that we've got our auto-scaling group up and running. We've got our EC2 instances being launched. We can now look at creating that elastic load balancer or that network elastic load balancer and start associating that to this target group. So let's go to load balancers and create a load balancer. And this time we're going to just select the network load balancer. And we'll give our load balancer a name. We'll leave it as internet facing, and we can see there we've got our listeners. So TCP, so it's receiving traffic on port 80, and that's TCP traffic only. And we can see there that is all that is available for us. A network load balancer doesn't do HTTP or HTTPS. And the availability zones, I'm going to select all of those availability zones. And next. And now is where we select our target group that we're going to be directing our request to. So it won't be a new target group, it will be our existing target group. And that is our network ELB that we created previously. And that will be forwarding it over on TCP on port 80. And our health checks again will be on TCP as well. So next we register targets. Now there is already a target registered there. So the auto scaling group already created this instance for us, and that was already inside that target group because we've associated the auto scaling group with this target group already. So there we have an instance ready to go. We can review this and we can create it. And that's finished. Okay, so let's have a look at what's going on here. So we've got our net ELB load balancer that we created, and here's a description of it. And it's got its availability zones there. It's a network elastic load balancer. And if we click on listeners, we can see there that we've got a listener on port 80 for TCP, and all requests are going to be forwarded to the network ELB target group. So if we click on that network ELB target group, we can have a look and see how that works. And there's that network ELB target group that we created. And remember, we also associated our auto scaling group with this target group. And so if we look at the targets here, we should see a target in there. And we can see there we've got a registered target. So it has been, the auto scaling group has automatically created an EC2 instance, and it is automatically registered that instance with this target group. Now, one thing to notice here, it is saying that it is unhealthy. Now, the reason it is saying that is unhealthy is because all I've done is launched a Linux AMI. It doesn't have any application on it, so it's not responding to any TCP requests on port 80 at all. And so those health checks that are going out to check whether it's alive, they're coming back, they're not being returned. So that's why it's saying status unhealthy. But obviously in a real application, you would have an application there that would be responding to those TCP requests. Okay, so now that we've finished the lab, we need to clean it all up to make sure that we don't get a bill at the end of the month. So we work backwards. So the first thing we need to remove will be the load balancer. So we just select that and then delete that. And that's gone quick as that. The next thing we need to remove will be the auto scaling group. And we'll delete that. And the next thing we need to remove will be the target or the target group. And we'll delete that. So we'll just go and check that those instances are starting to terminate. And it still hasn't quite kicked in yet. So it's still deleting that, and so after a period of time, that instance will be removed from our instances. So that brings us to an end of the lab. There are quite detailed lab notes for this, so make sure that you download the lab notes and do it all yourself. Once you've done that, I'll see you in the next lecture. Welcome to part 1 of using AWS Elasticache Redis. In this video, we're going to go through the Elasticache service and look at some of the features of it and where we would actually use it, the common use cases for Elasticache, and we'll also look at getting some hands-on experience in creating an Elasticache cluster using the AWS console, and then later on look at connecting to that Elasticache Redis engine to read and write information to in-memory cache. So Elasticache, it provides scalable in-memory cache. So that is different to RDS or DynamoDB, which is data that will be persisted for a significant amount of times, basically for as long as you want it to be. So Elasticache is different in that it's designed for short-term storage of information, and that information to be accessed very quickly. It currently supports the Memcached and Redis open source engines. Now, the common use cases for Elasticache would be to, first of all, to reduce load on your databases. So, for example, you might have a DynamoDB database, and you want to reduce first of all, the latency on that database, so speed up your application. You also want to reduce the amount of reads and writes to that database to reduce your costs, and again, you reduce that load on that database. And the way you would do that is that just the same as in DynamoDB, you would have storage of keys and objects of keys. The same you can do with for example, Elasticache Redis, what we're going to be using in this lab. And that will enable you to have high-speed access to that data, which will be in memory, and you can put an expiry time on that data so that it doesn't cost you significantly. And then once you've finished using it, the short term, it goes back. It will be then accessed into that long-term DynamoDB storage. Another very good use case is to manage application session state. So what we mean by that is if you have a look at the diagram there on the right hand side, we can see that we've got a user who he or she is connected in through an Elastic Load Balancer, and will be connected to one of 4 EC2 instances. So in this situation, the person is connected into the first EC2 server, and they might be on a game that has high score data. They might be filling out some user profile data in a form or whatever. So that's temporary session state storage that we want to maintain, but we don't want to maintain forever, but we want to maintain that in the short term. So what happens, for example, if that EC2 instance falls over, or that EC2 instance is part of an auto-scaling group that scales down, and all of a sudden that user is taken from that first EC2 instance, and then they're rerouted into the second EC2 instance. All of a sudden that user has lost that information that would have, it might be a high score of a game, it might be form data that has been lost. So that creates a lot of problems it creates a lot of frustration for an end user, and it doesn't provide a very good user experience. So we can actually manage that session state when we've got auto-scaling instances behind a Elastic Load Balancer, or auto-scaling groups behind an Elastic Load Balancer, and that will make sure that when that back-end scaling is going on, that the user won't have a bad experience from that. So the first thing we need to do is to create a security group for our Redis cluster. And that security group needs to be set up so that it can allow our web servers to communicate with that Redis cluster. So the easiest way to do that is here. I've just gone through and created a security group. I won't go through how to create a security group. By this stage of the course, you know how to do that. I'll just be boring you to death by going through the process there. So mainly what we've got here is a custom TCP rule that is on the port range of 6379. Which will be the port range for your Elasticache, will be the port for your Elasticache Redis cluster. And the source is going to be the web server security group there. So we're just allowing inbound on that, and the same on the outbound. We're going to allow, okay, so we're going to allow everything, destination all on the outbound. And so that's all we need to do. That the details of that are in the lab notes for this video. So just make sure that you set up that security group first, that Redis SG security group. Okay, so just jumping into the Elasticache console, we can see here we've got no clusters created yet, so we just have the introduction screen. So before we create an Elasticache cluster, we need to have a cache subnet group to launch that into. So we click on here on the left hand side before we click on getting started. We click on cache subnet groups, and we click on create cache subnet group. And so I've already created one here, and I won't go through the process again. It's all detailed in the lab notes. So I've just got here is that it's in US East 1, and that's its details there. So we've created that subnet group for our cache, and then we can use that to launch our cache cluster into that. So again, the details on how to do that are very, very straightforward. I won't go into that, and it's detailed in the lab notes. So just going back to the Elasticache dashboard. Okay, so now we click on Get Started Now. And we select our Redis, not Memcache, so we select Redis and click Next. Okay, so we won't enable replication here. We'll leave that off to keep it simple, but in a real application, you would probably look at multi-AZ. So we'll leave that off there for now. And then we'll give our cluster a name. Okay, so by default, it comes up with a large instance. So for a lab, we don't want that. We don't want to get a big bill at the end of the month. So we'll jump down to a T2 micro, which seems a little bit more suitable for us. We leave S3 location of our Redis RDB file. We'll leave that empty. So click on Next. Okay, so this is where we're going to select our cache subnet group. So there it is there. And our availability zone, we'll leave that with no preference, that's fine. And our security group. So we need to select our Redis SG security group that we created previously in the VPC console. So no preference for maintenance window. We'll disable any SNS notifications. We'll click on Next. And then we have a review of what we've got there. So we'll launch that cache cluster now. Okay, it's currently being created. We'll just close out of that, and we can see where we're currently being created. So that's coming along nicely. So we'll just leave it there for now for the first part of our Elasticache lab. And in our next part, we're going to look at connecting into our Elasticache Redis cluster and read and write data to that, and see how that works, and see how we can use some of these Redis commands to get information in and out of our cluster. So I'll see you in part 2. Welcome back to Backspace Academy. AWS CloudTrail, it doesn't have a broad set of features like other AWS services, but what it does is extremely important, and it may well be your last line of defense in the event that your infrastructure is breached. Now, imagine you've had your email account compromised and an attacker has got hold of your username and password from something like an email phishing attack or something like that. In that situation, it doesn't matter how good your Linux firewall is, your security groups, your network access control is, all of that sort of thing. It's not going to really help in that situation because your attacker has access with valid credentials. And in that situation, you need to identify that an attack is occurring from within your infrastructure, not from outside of your infrastructure. And that is where CloudTrail comes in to help you identify unusual activity from inside of your account. CloudTrail, it provides a record of AWS API calls to your AWS account. So if you've got multiple AWS users that you're set up, IAM users, what it will do is it will record all of the interactions between that user and your AWS account by recording all of those API calls that are made. The record will consist of the actual user, the timestamp that the API call was made, the actual API call. It could be a call to the EC2 service or S3 service, whatever that is. The resources involved, it could be a bucket or an EC2 instance or whatever. And the region that the call was made to. Now, as we explained previously, this is really important from a security perspective, especially if you have an attack that occurs from within your account. So if someone has valid credentials that they've somehow acquired or stolen or whatever, and they have access to your account and they're inside of your AWS account. So it allows you to record what's going on there and be alerted to situations that may be unusual. It can be used for compliance to standards by making sure that you record all of the interaction between your users and your account and recording that and archiving that if needed. It's also very good for troubleshooting your infrastructure. For example, you may find a situation where a individual user has difficulty. So you can go through your CloudTrail logs and see what API calls that user is making and why that individual user is having problems with your infrastructure. The CloudTrail records are saved to Amazon S3 in JSON format, and they're encrypted using S3 server-side encryption. CloudTrail can also be integrated with CloudWatch logs, and by doing that, you'll be able to see activity inside of your account with these API calls in the CloudWatch console. And you can also have alarms set up that can trigger a message or maybe even trigger a Lambda function or something like that, some sort of quick interaction. You can also have it integrated with SNS. And you do that using the console or using the CLI create trail command. Now, because the CloudTrail records are saved to Amazon S3, you can set up an S3 event that can also trigger an AWS Lambda function. And so that Lambda function may analyze what that record entry is and just see whether that is worth alerting your administrator or whatever if there is an issue. Okay, a picture tells 1,000 words. On the left there, we've got all of the different ways that our users can interact with our AWS account. So they could use the AWS Management Console, and by doing that, the AWS Management Console application will then send an API call to AWS to do something to an AWS service. That could be IAM, it could be Amazon S3, it could be EC2, it could be DynamoDB, could be any one of a number of different services. Or the user could use an application that is running one of the many software development kits. And that again would be sending API calls in, or the user could be using the AWS command line interface as well. But any one of those three different techniques will allow the user to interact with your AWS account using these API calls. Now, those API calls will be picked up by CloudTrail, and CloudTrail will record basic information about that API call, and it will store that as a record in a CloudTrail log. And so those CloudTrail logs will be stored in a designated S3 bucket that you define. And you can also integrate an SNS topic with those CloudTrail logs. So when they come in, it can alert you with an SNS topic. You can also integrate it with CloudWatch logs. And by doing that, you've got all of those features of CloudWatch then as well. And so that will allow you to integrate a CloudWatch alarm, or you could even have your CloudWatch logs sent over to a Kinesis stream as well for live monitoring of that CloudTrail log. Now, when you open up a CloudTrail log, it will consist of a whole heap of JSON records. So here we've got an example of what one of those records for an individual API call looks like. So we've got an IAM user who is not multi-factor authenticated, who is logged into the account. They've gone to the EC2 service and they've created a new key pair for an EC2 server. Now, this is something that you may want to be alerted to. You may not want people that are not MFA authenticated to be able to create new encryption key pairs. Now, as we've seen in the previous slides, CloudTrail can integrate with some other services. It can integrate with S3 events to trigger some reactive action to be taken. It can integrate with CloudWatch logs and then integrate with Kinesis streams. So there's a whole range of different things that you can create yourself to be proactive, to actually analyze and react to this CloudTrail information. But there is also CloudTrail Insights, which is an out-of-the-box service provided by AWS. What that will do is it will track your normal patterns of API call volume. Now, that can take up to 36 hours for the first time to get that history that it needs to see what your normal pattern is. So just need to take that into consideration when you first create this CloudTrail insight. You're not going to be able to take advantage of it until that 36 hours of normal pattern time has been put in. And that will then generate an insight event if any of the volume is outside of those normal patterns. So if your infrastructure has been attacked from within using credentials, then if there's a high volume for certain types of activity that is not normally the pattern, then that will trigger a insight event. And that event will be recorded as a log entry, and that again will be stored in Amazon S3. And so those events, Insights events, can be viewed in the CloudTrail console as a graph in a similar way that you can view alarms in the CloudWatch console. And that event history, which is sent to Amazon S3 and stored in Amazon S3, that can be used to trigger an S3 event, but it can also be used to send those record information or those event information to be sent over to CloudWatch logs. From there, you've got all of the features that are available of CloudWatch as well. Okay, so here is what a CloudTrail Insights event graph looks like. So what you've got there is some normal activity there in blue, and all of a sudden it spikes at around about 13:35. It's spiked up there, and that is unusual and it's marked in red. And so that has triggered an insight event. So if you want to have more information about that, you can scroll down and go and expand the Insights event record to see exactly what occurred there. You can also go into the S3 bucket, have a look in there. And by doing that, that's going to allow you to get some better information about what's causing this spike in demand. Okay, so that brings us to the end of a pretty short lecture, but a very important one on CloudTrail. Hope you enjoyed it, and I look forward to seeing you in the next one. And welcome back to Backspace Academy. This lecture, we're going to talk about encryption on AWS, which is a very important subject. Now, I deal with a lot of senior IT managers for quite large companies, and a lot of these people just don't really understand encryption. And it's not their fault. The problem is the way that encryption is taught can be confusing. So what I do is that I will break it down into very simple building blocks. And from there, you will build and further understand how that applies to AWS. And I promise you, at the end of this lecture, you will well and truly get encryption on AWS. We'll start off by discussing the two main types of encryption, being symmetric and asymmetric encryption. We'll talk about the key management service that integrates with many AWS services. We'll talk about the cloud HSM service that can allow us to securely store and manage our encryption keys. We'll talk about the secrets manager, which can be used for storing our secrets that are in text files. For example, our username and password. We'll talk about the AWS encryption software development kit, specifically for cryptographic operations. And finally, we'll talk about how we can encrypt our data on AWS, both at rest and in transit. Symmetric encryption. Now that uses the same encryption key to both encrypt our data and to decrypt our data. So that requires our sender, who is going to be encrypting our data and sending it, and the receiver, who is going to be decrypting our data. They need to agree on the same key and keep it safe. They need to keep it secret and secure, because if that key is intercepted in transit, or it's stolen, or some other way it has been compromised, then that data can be compromised as well. Now, to understand asymmetric encryption, we need to understand the concept of a two-way lock. So the easiest way to understand this is to think about, we've got a padlock here, and that padlock has two keys. Now, one of those keys turns the lock in a clockwise direction, and it locks that lock. And if you try to turn the key in the anti-clockwise direction to unlock that lock, it won't let you do that. But if you use your other key, now that key only turns in the anti-clockwise direction. And so you can put the other key into that lock, turn it anti-clockwise, and you will unlock that two-way lock. So one key can only lock, it can only go in one direction. The other key can only unlock. And so what we have is that we have a public key, and that is used to lock that lock. It cannot be used to unlock that lock. And then we have a private key. Now that private key can be used to unlock that lock, but the private key cannot be used to lock the lock at all. So asymmetric encryption, which is also sometimes referred to as public key encryption, uses a pair of keys. A public key that is only used to encrypt your data, and a private key which is only ever used to decrypt your data. Now, the public and private key are mathematically linked, but if you have the public key, it's not possible to mathematically work out the private key. You just wouldn't have a computer with enough resources to carry out that massive algorithm to do that. So it's not possible to actually create one from the other. So you may be wondering, why do we have a public key and why do we have a private key, and what is the purpose of that? So anyone who has this public key can encrypt that data for the receiver. So if you want people to send you some data and encrypt it before they send it to you, what you can do is that you can send them out your public key, and they can use that public key to encrypt that data before it is transmitted over to you. They never receive the private key. That private key is kept with you, the receiver of that data. And you use that private key to decrypt the data. And that is great because that private key never leaves you. And so if that public key, which is sent out to the transmitter, if that is ever intercepted, it is of no use to anyone because a public key can never be used to decrypt data. Only a private key can. And that is the magic of asymmetric encryption and why it is so important. Okay, so let's have a look at a real life example. Let's just say that we've launched an EC2 instance and we want to connect to that instance using Secure Shell or SSH. So the first thing that we need to do is obviously we'll need to make sure that our security group rules allow a connection on port 22 for SSH. The other thing that we need to do is that we need to make sure that we download the PEM file for connection to that EC2 server. Once we've got that, then we can go through the process of connecting to that EC2 server. The first step is that we need to make sure that we're running our SSH client on our computer that we're connecting to from our office or home or wherever it is. And once we've got that SSH client and we've got the endpoint for our server, we can initiate a session with that EC2 server. Once we've done that, the EC2 server will provide us with a host key, and that host key will be our public encryption key. And that will occur when we attempt to connect with that EC2 server. So once we've got that public key and we've got our PEM private key, we can use asymmetric cryptography to verify the identity of that EC2 server that we're connecting to. Once that's done and once we're satisfied and the EC2 server is satisfied with our identity, then this server will generate a symmetric key, and we use that symmetric key for bidirectional encryption from that point onwards for that session. And that way, all of the traffic being sent to and from this EC2 server will be encrypted while it is in transit. One very important thing to remember is that what happens if you lose your PEM file? If that occurs, you will not be able to connect to your EC2 instance, and AWS will not be able to provide it for you because that is your private key and only you have a copy of that. AWS does not keep a copy of your private key. So in that situation, what you are going to have to do is that you will have to stop that instance. You will have to create another private key or another key pair. And then you're going to have to associate that key pair by going into the user data, quite a complex process, and associate that new key pair with that EC2 instance. And then you'll be able to use your new key pair to connect in. The AWS Key Management Service, or KMS for short, that integrates with a lot of different AWS services, and it creates and manages the encryption keys that are used with those services. It uses a single master key that is secured by AWS. So it is symmetric encryption. We don't have a public and private key. We just have a single key. Now that key always remains on AWS and you cannot download that at all. The key is rotated automatically by the KMS service every year by default if automatic key rotation is enabled. If you want to use the KMS service to encrypt any data, then you must have IAM permissions to use those keys. And so those permissions can also be granted to other AWS accounts as well if they would like to decrypt that data. Now, the list of services that integrate with the KMS is growing, but if you go to the Amazon website and go to /KMS/features, you'll get a good list of all of these services that integrate with the KMS. Because the KMS service uses symmetric encryption, you may be questioning the security of that, but there's no need to be alarmed because we have another process involved with the KMS, and that is called envelope encryption. So the way that works is that we have a data key that is used to encrypt that data, and that is our single encryption key. Now, to make sure that that data key is secure. So if someone gets hold of that key, what the KMS does is it actually encrypts that encryption key. It encrypts the data key using a KMS master key. And so those master keys are stored by AWS, and they're called your customer master keys, or CMKs for short. Now, although symmetric encryption with a single data key is being used to encrypt that data, the KMS service can actually support symmetric and asymmetric customer master keys that are going to be used to encrypt that data key. And those CMKs are stored in a FIPS 140-2 compliant hardware security module, so they are very safely kept. If for whatever reason the data key is compromised, it's not a problem because it's encrypted using that master key. The AWS Cloud HSM service is a cloud-based hardware security module, or HSM for short, and it is used to secure and store your encryption keys. And it conforms with the security requirements for cryptographic modules, Federal Information Processing Standard, or FIPS for short, 140-2 Level 3. What that means is that your encryption keys that are stored in this HSM module are extremely secure. You control and manage your keys. AWS does not have access to your keys. And it's only accessible, these keys are only accessible by users that you specify. The Cloud HSM will run inside a VPC inside of your account. The encryption keys that are stored inside of that Cloud HSM will be accessible by a HSM client application that is running on an EC2 server that you launch. And there are HSM commands within the AWS Software Development Kit. It's also multiple availability zone capable as well. Some use cases for Cloud HSM. You may want to use a Cloud HSM cluster as a custom KMS key store instead of using the default KMS key store. You may want to do that if you want to keep all of your keys in the one location using Cloud HSM. Another use case, you can use it to offload the SSL processing from your web servers over to Cloud HSM. By doing that, Cloud HSM will take all of that processing for the HTTP requests and take that load off your web servers and make sure that your web services are more available as a result of that, and reduce the latency as well. You can also use it to protect the private keys that you use with a third-party certificate authority. So if you're using another service other than AWS to issue your SSL certificates, then you can protect those private keys using a Cloud HSM as well. The AWS Secrets Manager is a cloud-based service to store our secrets. And that could be database credentials, such as a username and password for logging into a database. It could be our passwords, third-party API keys. It could also be arbitrary text that we can put in there as well that we'd like to manage as a secret. The big advantage of doing that and using the Secrets Manager is that we can replace hard code credentials that we've put in our code. For example, we may have a application that is a web application that's running on an EC2 server, and we may have put hard-coded credentials inside of that code to connect to something else. And so that's a problem. If someone manages to get hold of our code, they've also got hold of the credentials as well. So instead of doing that, we can replace that with an API call from that web server over to the AWS Secrets Manager, and then the Secrets Manager can authenticate that server and then hand over that secret to that EC2 server. It uses the AWS KMS service to encrypt the secrets so they are encrypted and secure. The secrets can be created and retrieved using the AWS console, the AWS CLI, or one of the many software development kits. To create or retrieve a secret from the secrets manager, you will need to have IAM permissions that will allow that to occur. Okay, here is how we would create a secret using the command line interface. The command there is secrets manager, and then the command there is create secret. And then we need to provide a name for this secret, a description for it, and then the actual secret itself. So we can see here we've got a secret-string, and then we define what that secret is, and it's a file. So the details of that secret will be in a file called mycreds.json. If that was successful, the command line interface will then output the ARN, or Amazon resource number, for that secret, and the name that you provided for that secret, and the version ID of that secret as well. The IAM permissions that are required will be secrets manager, create secret, and if you're using a customer managed CMK, then you'll also need to have KMS, generate data key permissions as well. Now, if we want to retrieve that secret value, we'll need to have the ARN, or the name that we provided for that secret. And we, of course, will need to have IAM permission. So we'll need to have secrets manager, get secret value. And again, if we're using a customer managed CMK with the KMS, then we'll need to have KMS decrypt permissions as well. So the command there will be AWS secrets manager, and then get secret value, and then secret ID, which will be either the ARN or the name that we provided for that secret. The AWS Encryption Software Development Kit and its associated command line interface is a client-side encryption library. So what that means is that you will install the encryption command line interface on a computer, could be an EC2 server, could be a remote computer, whatever it is, or you could install an application that is running the encryption software development kit as well. Now, this is separate from the AWS command line interface and the AWS software development kits. It stands on its own as a separate application. It supports only symmetric CMKs, but it uses envelope encryption to make sure that that encryption key is secured. Okay, let's have a look at an example using the command line interface. So the command there is AWS-encryption-CLI. And the parameters that we need to provide, first off, is encrypt, saying that we're going to be encrypting this data. We then need to define the input data, and there it is a file, hello.txt. We then need to define the ARN, or the Amazon resource number, for our master key. We then define a folder where we can store our metadata output. Now, the next one here is encryption context, and that is optional, but it is recommended by AWS. What that is a name value pair, or you could put multiple name value pairs in here. You just need to separate them with a space, and they further define this encryption job. So when we go to decrypt, we can also provide this encryption context in our decrypt command, and that will make sure that we're getting the right file to decrypt. So here we've got a name value pair of department and IT. And finally, we just need to define where this is going to be output. So we've just got there output and a dot, which will output that to the actual folder where this command is being issued from. And so that will create an encrypted file, and it will put that into the folder where that command was actually issued from. And that file will be called hello.txt.encrypted. Okay, when we want to decrypt that file, the command there again is AWS-encryption-CLI, and the parameters there are, first off, decrypt. To decrypt it, we provide what the input is, and there it will be hello.txt.encrypted, and that is the file that is encrypted that we need to decrypt. We will supply the encryption context if we supplied an encryption context previously when we encrypted it. If we don't, or if we didn't, then we don't need to worry about that. We need, again, to provide an output folder for the metadata, and then finally where we're going to output that to. When we run that command, it's going to create a decrypted file, and that will be called hello.text.encrypted. So the same name as before, but with a dot decrypted on the end of that file name. There are three main options for managing your encryption keys. The first option is where you control everything. You control the method of encryption, for example, AES, whatever, and you control the key management infrastructure, or the KMI, and that will consist of the key storage, where that key is going to be stored, and the key management. So who is going to be authorized to access that key. And you are the one that controls all of that. AWS will not be involved in the management of that key. A good example of that is using client-side encryption, where you would encrypt your files before you upload those to AWS. So you have your computer here and you run an encryption client software. It encrypts that data, and then you can upload that data to S3, and that will be uploaded as encrypted data. AWS doesn't look after any of that encryption whatsoever. All it does is it stores that encrypted file for you in S3. The next option is where you can control the method of encryption and the key management, who is authorized to access that key. And AWS will look after securely storing that key for you. A good example of that is to use the Cloud HSM service to securely store your keys inside of a VPC inside of your account. And then your applications that are running on EC2 can access the Cloud HSM and then access that key. The last option there is where AWS controls everything. So they control the method of encryption and the entire key management infrastructure, such as the storage of those keys and the authorization of who can access those keys. A good example of that is to encrypt an S3 bucket using server-side encryption and using a KMS managed key. That way, AWS will be looking after all of the encryption, and they will also be looking after who can access that key, and also looking after the storage and management of that key as well using the KMS service. We can use encryption with a lot of the AWS storage services. First up there, we can use the AWS backup service to manage all of our encrypted storage. We can also use encryption with the S3, Glacier, EBS volumes, EFS volumes, CloudWatch logs, Snowballs, Storage Gateway, CloudTrail, and also with Code Commit, Code Deploy, and Code Pipeline. But with Code Commit, we can only use it with KMS managed keys only. We can also use the AWS KMS service to encrypt our databases as well, including RDS, Aurora, DocumentDB, so those MongoDB databases, Neptune, the Graph databases, Elasticache, the database migration service jobs, and also DynamoDB. We can use it with server-side encryption for encryption at rest of that data. But we also have another option with DynamoDB, and that is to use a DynamoDB encryption client. And that allows us to encrypt that data both in transit and at rest that is residing in DynamoDB. Other AWS services that can be encrypted using the KMS, Kinesis, Streams, and also Kinesis Firehose, SNS, SQS, SES, Elastic MapReduce, and SageMaker jobs as well. Now, this is not an exhaustive list of all of the services that are available to be used with the KMS, but if you want to get the latest and complete list of all of the services, just go to the Amazon website or the AWS website /KMS/features. So that brings us to the end of the encryption lecture, and I'm sure you fully understand it by now, and I look forward to seeing you in the next one. welcome back to Backspace Academy. In this hands-on lab, we're going to be running through how to create an encryption key using the KMS service and then use that key to encrypt data. So make sure that you've downloaded the lab notes that come with the course. Now the KMS service, it's located in the IAM management console. So if you look for KMS here, you won't find it. You need to go to IAM. And from there you can scroll down and select encryption keys. So you can see here I've got some encryption keys, but they're all being created by different AWS services like Cloud9, S3 and all this sort of thing. So you can see those ones with the Amazon logo next to them. They're not ones that I have actually created myself. So what we need to do is create one ourselves that we can use to encrypt data with. So we create a key. Let's give that key a name. And we won't bother about a description with it. And we click on next step. And we won't worry about putting a tag in. We don't need that for now. Okay, so we need to select some administrators. So I'm just going to select myself as an administrator. And we also need to select some people that can use this key to encrypt data. So I'm just going to select myself again. And next step. So there's our key policy and we click on finish. And that's how easy it is to create a key to use on AWS. Okay, so now that I've created that key, I can use that key to encrypt data in Amazon S3. So what I'm going to do is jump into the S3 management console. And I'm going to create a bucket. So I'm just going to give this bucket a name. And I click on next. Okay, so now we've got some options here available. So if we scroll down, we can see automatically encrypt objects when stored in Amazon S3. So that's what we want to do. So I'm just going to click on that. And what we want to do is that we're not going to use the AWS S3 managed key. We're going to use the KMS key that we created. So we click on KMS and we select our key that we created. And there it is, test key. And we'll save. And there we can see, so we've now got that set up and we click on next. And I'm just going to leave this as private. I won't change the permissions of it. And there we go. So we can see here now, when we look at the properties of it, we can see here we've got default encryption, AWS KMS. So we'll create that bucket. So I'll just jump into that bucket now. And we're just going to upload some files. So I'm just going to grab a little file and upload it. Okay, so just going to upload one of our review PDFs. And we've got some options here for permissions. I'll just leave that all as private. Okay, so now we can select whether we want this to be encrypted or not. And so we can see here, we can select the AWS KMS. I'm going to leave it as none because I want to see what happens if I upload this and tell AWS not to encrypt it. So let's go. We'll click on next and we can see here we've got encryption. No. So let's see what happens. So I upload this. Okay, so that's been uploaded. So if I click on that and I have a look at it and we look at the properties, we can see that in fact, it has been encrypted. So even though we told the S3 service to upload this without encryption, it has automatically encrypted that for us because we have defined at the bucket level that anything that goes into this bucket must be encrypted. And if you make a mistake and don't select encryption, it doesn't matter. It will be automatically encrypted when it goes into this bucket. So what I'm going to do now is just download that. And if I click on that, what will happen is that it will be downloaded unencrypted or decrypted. So what that means is that the S3 service has managed everything for us and we don't really have to worry about that at all. And the KMS service has supplied the key and it's all quite transparent for us. So that's just how easy it is. So what we do now is we've finished up with this lab. So what I'll do is I'll just clean it all up. So I'll just go back to the main index of Amazon S3 and I'll just click on that and delete bucket. Okay, so the bucket's been deleted. So what we need to do now is just get rid of that key. So we can't just delete the key. We can delete the key, but we can't do it in one hit. So what we need to do is go to Key Actions and Schedule Key Deletion. We can't just do it instantaneously. And we just had to put a waiting period in there. So just put in 7 days and schedule that deletion. And in 7 days, that deletion will occur. So that brings us to the end of the lab. And I hope you enjoyed it, and I'll look forward to seeing you in the next one. Welcome back to Backspace Academy. In this lecture on the AWS Cognito Authentication Service, we'll start off by talking about the Cognito user pools and how we can use those to create millions of users to access our applications that are running on AWS. We'll talk about the Cognito federated ID pools and how we can use a third-party authentication service such as login with Google or login with Facebook or a SAML authentication service to again authenticate and access our applications on AWS. We'll talk about the Cognito Sync key store database and how we can store data specific for a Cognito user. We'll talk about how Cognito opens up a whole new world of modern serverless applications that we can run completely without servers on AWS. And finally, we'll talk about troubleshooting and what to do when things go wrong. Cognito, it adds user sign up, sign in and access control for your web and mobile applications. So you might have an application that has millions of users and Cognito can manage all that for you. And those users will have a username and password to access your application. You can also use a social identity third-party OAuth provider for the authentication and integrate that with Cognito, such as Facebook, Google, or Amazon. Or you could also use a third-party enterprise identity provider and use that via SAML 2. Cognito, it consists of 3 services: the user pools, which can have millions of users, federated identity pools to allow that third-party authentication through OAuth providers or SAML 2 applications, and also a Cognito Sync key store database that allows you to store information on specific users. Okay, so on the left there, we've got the different ways in which Cognito can authenticate any users that want access to our application. So we've got social identity OAuth providers such as Google, login with Facebook, login with Amazon. Any of those will be fine. We can set up a Cognito user pool, which will have a list of or a pool of users, and they can log in using a username and password. And finally, we can use an enterprise identity authentication service, provided it is SAML 2 compliant. Once that's done, a token will be issued by the Cognito, or actually be issued by the STS service, the Security Token Service, and we'll talk about that in the next slide. And that will allow your users to access through your application AWS resources, such as Amazon S3, your APIs. You could set up an API gateway service and they could access that as well securely. Also, you can set up a data synchronization service using Cognito Sync, which will be a key store database, which will hold data or information on your particular users. The Security Token Service, or STS for short, is a back-end service that provides that security, the low-level security around the IAM service. So it's a back-end service and it's accessible from the software development kit or the command line interface, but it's not accessible through the console. So if you go to the management console and you try and find Security Token Service on the list of services, you won't find it. It's just a back-end service that provides the nuts and bolts to achieve the security of IAM. So it does that by issuing temporary limited privilege credentials for IAM or federated users. For example, if you're using login with Facebook or login with Google or a SAML enterprise authentication service, they will be limited privilege credentials. It achieves this by using JSON Web Tokens, or JWT for short. And it uses those to secure and authorize the access to your APIs, such as an API gateway service or other AWS services, such as Amazon S3. And those web tokens, they will be temporary and they will have limitations on how that actual user can access your account. For example, if it's a root user, it will have full access to your account. If it's someone who's validated through an authentication service, such as login with Google, they may have the access specifically for read-only, not write, and it will be only to a certain part of your application or a certain part of that service, such as S3. It's a global service like IAM, and the endpoint for it is sts.amazonaws.com. And it integrates very well with CloudTrail. So if you want to see an audit trail of users that have been issued an STS token, then you can see that by setting up a CloudTrail log. Okay, so here we have a mobile application, and it's going to be using the third-party login with Amazon service to authenticate that mobile user. But that could also be login with Facebook. It could be login with PayPal. It could also be a Cognito user pool that we could log in with a username and password. But whatever it is, it's a service that we use to authenticate this individual. So once we've authenticated using that third-party service, login with Amazon will hand over a token to that mobile client. And that mobile client will then pass that token over to the AWS Security Token Service. And the AWS STS service will then go back to the login with Amazon service to authenticate that token. If that token is valid for that particular user, then the STS service will create an AWS temporary JWT, a JSON Web Token, and pass that back to the mobile client. Once a mobile client has that, they have limited and temporary access to AWS resources. And those AWS resources will be defined in an IAM policy. So if that mobile client has read-only access, then that will be defined in the IAM policy. If that mobile client or that end user only has access to a specific part of that database, then they will only be granted access to that specific part. So in this situation, they're being given read and write access to the game scores. So they've got a high score. The mobile application can write that back to DynamoDB, and it's completely secure and completely straightforward because we're using the STS service to manage everything for us. Cognito user pools allow us to create and maintain a directory of our users. And that could be millions of users. It could be 10 users. It could be it could be anything, but it scales to hundreds of millions of users. And those users will simply be authenticated by signing up and then signing in for your applications. When it is associated with a Cognito ID pool, it can provide secure access to your AWS resources. So you may have an application that requires access to some images on Amazon S3. So if that person signs in to a Cognito user pool and they're on that user pool, then they will be granted specific access to that S3 bucket, depending on what is written into that IAM policy that defines all this. Web Identity Federation pools, they allow you to create unique identifiers for your end users, and those will be kept consistent across your devices and platforms. So if you log in with a different device, it will be using the same unique identifier despite what device or platform you log in. If you log in with Mac and then Windows, or if you log in on a mobile device, it will still authenticate you as that unique identifier. So the users can use an identity provider such as Facebook to log in, and then they will attain security token service or STS temporary credentials. Now, one thing I need to say about this is that before Cognito came along, and still now is the case, that we don't need to have Amazon Cognito to have federated access to AWS resources. Where the Cognito federation pools come in, or identity federation pools come in, is that they will link that login to a specific Cognito identifier. And that can be used with Cognito user pools or a Cognito sync database, as well as for temporary access to AWS resources. So if you just wanted to have the access to AWS resources, such as an Amazon S3 bucket, then you can actually do a federated login using Google and using the STS service on its own. But you won't have all of the other features of integrating with Cognito. Okay, so here we've got one example of how we can use the federated ID process. So we've got a device there, and it has an application running on it that uses one of the AWS software development kits. And we use login with Facebook, for example. And so once we've logged in using that OAuth process to log into Facebook, Facebook will give us details of, or will give our application the details of that user, such as their account ID for Facebook or whatever it is, and also a security token for Facebook as well. Once we've got that information, we can then use Get ID with Amazon Cognito, do a call to Amazon Cognito to get the Amazon Cognito ID of that person that is logging in with that Facebook account. Once we've got that, we can then get the credentials for that Cognito ID and get that from the AWS STS service. So we will grab that Facebook token, we will grab the Amazon Cognito ID details, and we will pass that over to Cognito, which will then also pass that over to the AWS security token service. And from there, we will be issued, or your application running on that device will be issued with a temporary AWS STS JSON web token. And from there, we use that token to access or have limited access to our AWS resources. The difference being to the last process that we saw is that we've got Amazon Cognito here as well. So we can also now, with that Cognito ID, access a Cognito sync database or a Cognito user pool as well. Cognito Sync is a key store database that provides cross-device syncing of all of your application-related user data. And that will be synchronized across your multiple devices, multiple platforms, be it Windows or Mac or whatever. And it also has offline storage. So if your internet connection gets cut, you will still have access to that user data. There are two ways of achieving or accessing this Sync key store database. The first one is to use the Cognito Sync Manager JavaScript SDK. So that's another SDK that you'll need to load into your JavaScript application. And there is a synchronize command. And what that will do, it will update the records on the key store database on the server side, and it will synchronize it with browser local storage on the device side. Now, before the Sync Manager came along, the way we did it is that we would do that manually. So we would use the JavaScript SDK, which is another way, and use the update records command to update the records on the key store database, and or also to create records if there is no record there. And then we would manually use the browser local storage to secure that in local storage on your browser. But either way, both works, but one of them requires an additional SDK to be loaded into your application, which may reduce the startup time for your application in the browser. So something to take into consideration, but certainly the Sync Manager is a quick and easy way of doing it. A great thing about using Cognito is that it opens up a world of really powerful serverless single page applications that are very reactive, provide very quick feedback to your end users, and use very limited resources because they're shifting a lot of those resources that you would normally have on the server side over to the client side. So looking at this example here, we've got a desktop or mobile application, and it's a React.js application. So it's going to be a single page application, a bit like your Gmail app in your browser. So it's not going to be doing page refreshes. So anything that needs to be updated will be updated individually based on what the latest information that application is getting, and only those components of that user interface will be updated. So that's going to provide some really good speed for your application. It's also going to shift that work that would normally be done on the server side over to the client side. And that's going to save you a lot of money. So we already know how to create a single page application on uploading it to Amazon S3 and using Amazon S3 web hosting and fronting that with CloudFront. So we already know how to do that. But in our application, we can make calls to Cognito Federated ID. We can use a Cognito user pool, or we can use a SAML or OAuth authentication service. And that will allow us to access a Cognito user pool, which will keep details on our users. So that's a great authentication service that is very quick and easy to set up, and you don't have to do that yourself. Now let's say that we want this end user to be able to access some data from a DynamoDB database. And let's also say that because React from Facebook goes hand in hand with GraphQL, which was also developed by Facebook, we might want to have a GraphQL client running on our application. Now, if you don't know what GraphQL is, just Google it, because it's another way of thinking about data, and it is certainly revolutionizing the way that we think about integration of data with our applications. So certainly go and Google that. And if you are a developer, make sure you know GraphQL, because it's going to be here to stay. So once we've got our client set up that can issue GraphQL queries to AWS, we can set up AWS AppSync, which is a GraphQL server. And it will provide the glue between our application and our back-end database. And that will be completely serverless. So here, all of a sudden, we've got a React.js front end. We've got GraphQL on the client side as a GraphQL client. And we've also got federated identity access to a GraphQL server, which will also integrate nicely with Amazon DynamoDB. We don't have to write any sort of interface between AppSync and DynamoDB. It simply connects directly to DynamoDB. If that DynamoDB database is very popular, we can also have a DynamoDB accelerator, which is a cache of our regularly accessed content in a similar way to CloudFront is a cache for Amazon S3. Now let's just say we want to have e-commerce capabilities for our application. And so to do that, we're going to use the PayPal API. So we need some way of communicating with the PayPal API and organizing those payments, and at the same time, updating our database with those payment details and what it was actually paid for. So the way we can do that is that we could implement a Lambda function. And so that could communicate with PayPal API so that whenever a payment is made, by a user that is using this application, the PayPal API will notify that Lambda function, or will call an endpoint that will trigger that Lambda function. And then that Lambda function can go back to the Cognito ID service, identify that user, and then update the DynamoDB table with the payment details for that end user. Okay, so let's have a look at some troubleshooting steps that we can look at in case we run into some problems. The first one there is that if we're hosting our website on Amazon S3, using an Amazon S3 bucket and the web hosting service of S3, we need to make sure that we establish cross-origin resource sharing, or CORS, on that bucket. Otherwise, any calls from that application that's running on that S3 bucket or running on the client's browser, they will not be allowed by the browser to access that endpoint for Cognito. So you need to make sure that cross-origin resource sharing is set up. Otherwise, you're not going to be able to access Cognito. You need to make sure that you've got an IAM role set up for Cognito ID, and that there is an allow rule that allows anyone that assumes that role through Cognito that they have access to that resource, be it, for example, DynamoDB. So if you're finding that you're not going to be, or you're not able to access that resource after signing in, make sure that you check that IAM role and make sure that there is an allow for that service. Now, when you set up Cognito ID, you need to establish or define a trust relationship between the Cognito service and that other service that you're using to authenticate. So if you're going to be using an OAuth service such as Facebook, or you're going to be using a Cognito user pool to authenticate those people, or you might be using a SAML enterprise service, you need to define that when you're setting up Cognito ID, and that will allow that trust relationship to be set up by Cognito. Finally, you need to make sure that you're using the correct software development kit for the code. So there are multiple JavaScript SDKs for this Cognito service. There's ones for the sync manager. There's one just specifically for the low-level stuff with the SDK. There's a whole heap of them. And you need to make sure that you're using the right one. So you'll probably start off with the JavaScript SDK, and then you may add the Cognito Sync Manager SDK to that as well. But you just need to make sure that if you're going to be using those commands, that you have loaded the SDK into your application before you start using those commands. So that brings us to the end of a very broad overview of the Cognito service. And I look forward to seeing you in the next one. And welcome back to Backspace Academy. In this lecture, we're going to extend our knowledge of API Gateway and have a look at ways that we can improve the performance and reliability of our APIs. We're going to look at throttling. So what happens when our API service gets too many requests that it cannot handle, and what we can do about making that better. We'll look at API caching and how we can get our regularly used content and cache that so that we get very low latency response to our requests, and also so that we can reduce the costs associated with our API Gateway service. We'll also look at usage plans that we can set up for individual users of our service, and we'll also look at some of the known issues around API Gateway. When your API service receives too many requests that it cannot handle, that's when throttling occurs. And so any further requests will receive a 429 too many requests error. The throttling and what actually gets throttled is based upon a token bucket algorithm. And that has two components. So first off, there is a steady state rate of requests per second limit. So what that means is that over a 1 second period, you're only allowed to submit or receive so many requests over that period. If you exceed that, number of requests over that 1 second period, any additional requests will be throttled and they will be sent back with a 429 error. The other component is a burst total number of concurrent requests limit. What that means is that at a specific time, if your API gets hit by a large amount of requests, concurrent requests, and it exceeds a certain limit, any additional requests over that limit will again be throttled and will receive a 429 error message back. The default account level throttling limit is 10,000 for steady state. So over a period of 1 second, you can receive 10,000 requests, or at any one point in time, your limit will be 5,000 requests or concurrent requests, and that is your burst limit. Now, this can be increased by applying to AWS if you find that that is not enough for you. Now, you can also define a custom default throttling limit, and that can be applied to a specific stage or API method. Now, those default throttling limits cannot exceed the account level limit. So if you've got 10,000 for your steady state, you can only go up to 10,000. You can't go to 11,000. You can put in 8,000, and the same with your burst. You can put in a 4,000 burst for an API, but you can't put in a 6,000 unless your account level throttling has been changed from the default. So let's have a look at how that works. On the vertical axis here, we've got the number of requests, and our dotted red line there defines our 5,000 requests burst limit. And our blue line there shows the number of outstanding requests that have been received by our API. So initially we get a burst of 5,000 requests come in. Anything above that 5,000 will be limited. And so at that point there, we are burst limited. We can only take in 5,000. And then over a certain amount of time there, that number of requests will be reduced as our API gets through those requests. And here we see it at 0.5 seconds. We have got through all of our requests. And then we receive another burst of requests. And again, we can go up to 5,000, but we can't go above that. So we can only receive 5,000, and then that again goes down. We get through it. So it is burst limited, but it's not steady state limited. And that is because we've received 5,000 here, and then we've received another 5,000 requests in one specific time there. So the total number of requests that we've received over that 1 second period is 10,000, and that is below our steady state rate of 10,000 requests per second. And we haven't exceeded our burst limit of 5,000 there either. Okay, so let's have a look at another example here. So at 1 second here, we've got another burst of requests that have come in, of concurrent requests. So we can only take 5,000 of those, and anything above 5,000 will be burst limited. Now, over a period of time, we're getting through, or our API is getting through those requests, and we receive another lot of requests that come in concurrently. Now, we can only go up to 5,000 here, so we can only receive another 2,500 to bring us up to here. So we've already received 5,000 plus 2,500, which is 7,500. Now we're going to get through that 5,000 over this period of time here. And then at this point here, we receive another lot of requests. Now, we're not going to be burst limited here. We're going to be steady state rate limited, because over a 1 second period, we cannot exceed 10,000 requests. So the average number of requests over that 1 second period cannot exceed 10,000. So we've got here, we received 5,000, then we received another 2,500, which is 7,500, which leaves us only 2,500 left. So we can only receive another 2,500 requests. Above that, it will be steady state rate limited. in order to reduce the possibility of throttling occurring on your API service, you can implement API caching. What that does is it caches your popular requests to your endpoint, and that will reduce the number of calls to that endpoint because it will be delivering the requests from the API cache. That will reduce the latency of those responses, and it will obviously reduce the costs. You'll be charged per hour for using the API cache, although this is not on the AWS free tier. But it will reduce those number of calls to your endpoint that are already in your API cache. The default time to live for that cache is 300 seconds or 5 minutes, and the maximum is 3,600 seconds or 1 hour. Usage plans can allow a deployed API to be used as a product offering. The way it does that, it uses an API key that identifies the individual client that is connected to the API, and it will have throttling and quota limits that will be enforced on that client and specific to that client or group of clients. They'll be generated in the console or imported as a file in an API key file format. The request will require that API key whenever a usage plan is enacted. So you will not be able to access that API unless you are using an API key when a usage plan is in place. A good feature of this is that not only can it be used as a product offering, it can also be sold as a service on the AWS marketplace. There is a significant list of known issues with the AWS API Gateway service. One of those being that Nginx may not fully support SSL client authentication. I think that's a significant one. Not all of the Swagger specification is implemented, although that's not such a big deal because pretty well everything you need has been implemented. But there is certainly a significant list of issues, and I'm not going to list them all here because that list is changing quite regularly as AWS improves this service. But for the latest information on that, please go to known issues in the AWS API Gateway Developer Guide. So that brings us to the end of this lecture. I hope you've enjoyed it, and I'll see you in the next one. And welcome back to Backspace Academy. We're currently at the AWS Certified SysOps Administrator Associate, part of the pathway. Now, this will build upon the Cloud Practitioner, the Associate Essentials, and the Architect SysOps Administrator Essentials parts of the pathway. So if you haven't already done those 3 parts, please make sure that you go away and do those before coming back, because you will need that knowledge to proceed any further. So this will be final preparation for the AWS certification exam, and it will finish up with a practice exam, which will test your preparation for the real AWS certification exam. Let's get into it.
Please note that this content is targeted for SysOps administrators. If you're a solutions architect or a developer, you may want to skip over this one.
And welcome back to Backspace Academy. One thing that a SysOps administrator will be doing a lot of, and that is troubleshooting of services. And one of those services, which you will no doubt be involved in troubleshooting, will be Amazon EC2. So this lecture is going to run through all of the different issues that may arise with the EC2 service and how to troubleshoot those. So we'll look at launching issues. We'll look at issues with failed status checks. We'll also look at where you are unable to terminate or stop an instance, and then we'll finally look at connection issues with the Linux instances and also with Windows instances as well. There are a range of probable causes that can lead to your EC2 instance failing to launch. The first one, and probably the most significant one, would be that you've exceeded the EC2 service limits, and that can be a range of things, For example, a lot of instances you may only be able to launch 1 or 2 of those, others you may be able to launch 20 of. So if you exceed that limit, then AWS is not going to let you launch any more instances. And the same with the EBS volume limits. If you exceed those, then you are also going to run into problems when you go to launch your instance. There are other issues. You could have a corrupt EBS snapshot that you are trying to launch your instance with. You could also have a problem with an instance store backed AMI. And with those, they will be, and this is only for instance store backed AMIs, that they will be stored to Amazon S3 in parts. And the AWS service, when it goes to launch, it will piece those parts back together to create that AMI that is going to be used to launch that instance. So if you're missing one of those part files, then you're not going to be able to launch that instance. If you have insufficient instance capacity to run your application, for example, if you have a very compute intensive application or memory intensive application, and your instance that you're selected might be a T2 Nano or something like that, it may not have enough capacity to actually run that application. And finally, you may encounter account issues. If you haven't paid your bill, then you're not going to be able to launch instances. So any one of those can fail to launch or cause you to fail to launch your EC2 instances. So the action that we can take, the first thing we should do is to look at the instance or the state transition reason, which will be in the instance description. So when we go to the console, we click on our instance and we'll be able to get that state transition reason. We can also get similar information by using the CLI describe instances command. And if we find that it is something around limits, then we can check our limits in the EC2 console. So there will be a menu option there on the left-hand side that we can click on to have a look at our available limits. If we find that we're exceeding those limits, for example, the number of instances that we may be able to launch, we can request an increase from AWS to correct that problem. If an EC2 instance fails its status checks, there are a number of probable causes for that. It can be memory issues. It can be problems with EBS with an IO device. It could be kernel issues. It could be file system issues, and it could be other issues with the operating system. So the action that we would want to take is that, first of all, we'd like to wait for it to resolve itself, obviously. If we find that it's not resolving itself, then we can, if it's an EBS-based instance or EBS-backed instance, we can restart it by stopping and then starting it, or we can relaunch it. So with an instance store, you can't stop that. You'll have to terminate it and then relaunch it to see if it fixes it. You can also retrieve the system log, which is basically the console output for that instance. So if it's a Linux operating system, you can actually retrieve all of the output from the console, or from the Linux console, that is. And we can also look at creating an instance recovery alarm with CloudWatch. And so if there is an issue, then we can have CloudWatch take an action to recover that instance automatically for us. If we have problems with terminating or stopping our instance, it's most likely going to be a problem with the underlying host computer, or the underlying host computer is processing scripts that haven't been finished before you can actually stop or terminate that instance. Another common problem is that you might have that instance inside of an auto-scaling group, or it might be part of Elastic Beanstalk. And every time you terminate that instance, it's actually replaced with another instance. So quite a common problem that you can encounter. So the action that you can take is that you can use the CLI stop instance command with the force option on it, or you can actually create an AMI of that instance and then terminate it and replace it with another instance. If you find that you just cannot terminate that EC2 instance, then you're going to have to contact AWS support and they can terminate that instance for you. If you are having trouble connecting to your EC2 Linux instance, it may be that the instance is overloaded and just doesn't have the resources available to do that connection. It could, and most probably would be, a problem with your VPC setup. It could be a problem with your private key that you're using to connect to that instance. If you're looking to ping that instance, then it could be a problem with setting up ICMP. So the action available, if it's a VPC issue, make sure that you have your security group rules set up and your network access control list set up to allow inbound traffic on that port. Make sure that you have an internet gateway or a virtual private gateway and that you have a route from your subnet through to that internet gateway. Also make sure that you have a public IP address. If you don't have a public IP, then your instance will not be visible on the wider internet. If you find you've got a problem with your private key and it's not recognized, you need to check the format of that private key. So if you're using PuTTY, make sure that you're using the PPK format. It could be that you're using the wrong username to connect. So if you're looking at a AWS AMI or an Amazon AMI, the user will be EC2-user. If it's an Ubuntu instance, it will be Ubuntu as the user. You also need to make sure that you've got permission to access that private key, and also make sure that it is not a completely unprotected file, because either of those will prevent you on your side from connecting to that EC2 Linux instance. The issues with failing to connect with Windows instances are similar to Linux instances. So you still have problems that may arise from the instance being overloaded, or VPC issues, or problems with the credentials. But we also have a Windows firewall that may also be giving us issues. And we also have a maximum number of RDB sessions that we can concurrently have connecting to that instance. So if we exceed that, we're going to run into issues. So with our credentials, we need to make sure that our username and password is correct, and also make sure that that password has not expired. If we find that we've found Windows firewall issues on our Windows server, we need to disable that Windows firewall and use our security group rules to control access via RDP for our instance. So that's all I'm going to talk to now about troubleshooting. Coming up next, we'll have a hands-on lesson on how to actually use this. So I'll see you in the next one.
Please note that this content is targeted for SysOps administrators. If you're a solutions architect or a developer, you may want to skip over this one.
And welcome back to Backspace Academy. In this hands-on lecture, I'm just going to run through some of the techniques that are available for us for troubleshooting our EC2 instances. So I'm just starting off here in the EC2 dashboard. What I'm going to look at here is on the left-hand side, we can see we have our limits. And so if we click on that, it's going to provide us with all of the available limits that we have. So we can see here on this account that I've got here, I can run 5 C1 medium instances, but I can only run one C3 4 extra large instances. So just one of those. So if I try and run more than that, it's not going to let me. So I would have to go through and request a limit increase. So what I'll do now is I'm just going to try and launch 2 of these instances. Now, I don't recommend that you do this yourself because they're very expensive instances. And if you forget to delete them, you're going to end up with a pretty nasty bill at the end of the month. So I just go back to the EC2 dashboard, launch instance. Just going to grab a Linux AMI will be fine. Let's scroll down to a C4 extra large. Okay, C4, 4 by extra large. And it's going to review and launch that. So it's allowed me to launch that instance. It's quite a big one. And I'm just going to try and launch another one of those. So again, we'll just use the Linux AMI. And C4, 4 extra large. And we'll just review and launch, Select our key pair and launch. Okay, so the launch has failed. So we've exceeded our limits and it's stopped us from launching that second instance. So I'll just cancel that before I get a big bill, and I'll just terminate the one that I've created there. Okay, so what I'll do now is just launch a smaller instance, and we'll just see what tools are available for us to troubleshoot that instance. So we'll just launch another instance. Again, we'll just use the Amazon Linux will be fine, and a T2 Micro will be fine. And I'm just going to review and launch. So we'll just wait for that to finish being launched and finish all its status checks. Okay, so after a certain amount of time, we have our instance up and running and its status checks have passed. Now, if we select that instance and we click on the status checks tab, we can see there that, yes, it has passed its system status checks and its instance status checks. Now, if you want to understand the difference between the two, just hover over the information icon there. And the system status check verifies that your instance is reachable. Whereas we look at the instance status check, that verifies that your instance's operating system is accepting traffic. Also, it tells you what to do if there is a problem that you fail that check. So you can see there that if you fail an instance status check, that's an operating system is not operating correctly, then you are best off to reboot that instance. Whereas if you look at the system status check, if something goes wrong with that, then it's obviously at a system level and there is a problem with the underlying host that is running that instance. And so the best thing to do is to stop and start it or else replace that instance. Now, the next thing we can look at are the system logs for the instance. So we go to instance settings and then get system log. So what that is, it's an output of the console of our Linux operating system. So that is, if we were connected to this Linux instance, this is what we would see from the console. And so that gives you a lot of information as to what is going on. And so we can scroll down here to the latest. And we can see it's at the login stage there, waiting for a login to the instance. So just close that. And what we can also do is that we can go into instance settings, and we can get a screenshot of the console of that instance as it is right now. And so there we can see it's waiting for a login, and we can refresh that if we want as well and get a later one. And so these are quite good because it allows you to see exactly what is going on from a historical perspective through the booting up stage, and also what the console is telling you right at this point in time. So just close out of that. Now, if we find that we have a problem with an instance status check, what we can do is we can implement a CloudWatch action or a CloudWatch alarm. So we just go into CloudWatch monitoring and add edit alarms, and we create alarm. So what we can do is we can send a notification, as we can do with most CloudWatch alarms, but we can also take an action on that instance. So if we click on take action, we can actually recover that instance. So if it's failed a status check, then we can automatically repair this instance in the event of that. But you can only recover certain types. Not all EC2 instance types you can, but you can recover T2 and most of the common types of EC2 instance. You can also take an action to stop the instance. Now, if you want to stop the instance as opposed to recover the instance, the CloudWatch service needs to have an IAM role to do that. So you need to select here, create IAM role. And you can only stop an instance if it's an EBS volume-backed instance. So you can't stop an instance that is instant store back. It will just need to be terminated. So then we've got terminate instance as well, and we can also reboot that instance. But again, we need to have an IAM role created for that. So what we can do is, if we would like to have different stages that kick in, we can first off try and recover the instance if it's failed for so many consecutive periods, and we can create an alarm for that. And then we can look at rebooting the instance. And we can do that after, say, 10 consecutive periods, say. And then we can create another alarm to terminate that instance, which would be very handy if it's in an auto-scaling group. So you can terminate that, and then another instance can be created quite quickly for you. So I'll just get out of that now. So just back here in our status checks tab, we can see here there is also a link to create a status check alarm. And that is the same alarm that we were talking before. And so we can take an action to recover the instance. Now, if we want to terminate an instance, one thing I didn't mention before is that we need to make sure that termination protection on that instance is disabled. Otherwise, CloudWatch won't be able to terminate that instance. So that's about all I need to tell you about troubleshooting of EC2. Coming up next, we'll have the same for troubleshooting RDS. I'll see you in the next lesson.
Please note that this content is targeted for SysOps administrators. If you're a solutions architect or a developer, you may want to skip over this one.
And welcome back to Backspace Academy. In this troubleshooting lesson, this time it'll be on the RDS service. We'll again look at issues around failing to connect to our instances, and we'll also look at those specifically around SQL Server as well. We'll also look at the probable causes of a service outage and also the causes of a MySQL read replica lag as well. If you're having trouble connecting to your RDS instance, the most probable cause would be, first off, your security group rules. So make sure that you have an appropriate ingress rule for the instance that you are connecting into. Could be a wrong password. And it could also be problems on your side of the connection. So you could have local firewall restrictions on your side that are preventing you from connecting. It could be something as simple as you haven't given enough time for the instance to be created yet. So the action that you can take is, first off, test that connection using netcac if you're in the Unix environment or Mac OS X, or else use telnet if you're in a Windows environment. The netcac command there will be nc-zv and then the endpoint followed by the port. And Windows will be similar. It will be telnet and then the endpoint and the port. You can also try and reset your master password as well. Additional to the general failing to connect issues, there are also SQL Server specific issues. So you may get a message from SQL Server saying could not open a connection to SQL Server. That would most probably be you're using a wrong connection string. So it might have the wrong endpoint that you're using, or you could have the wrong port number or the missing port number from that connection string that you're trying to connect with. It could also be that you're using the incorrect username and password, and if that occurs, then you would have a message similar to no connection could be made because the target machine actively refused it. So that is the credentials have been refused, and so you would need to go back and have a look and make sure that your password hasn't expired or you're not using the correct username. If your RDS instance goes down and you experience a service outage, the most probable causes, first off there, would be that the instance has rebooted for whatever reason. And you may have changed a setting that requires the instance to reboot immediately. For example, if you change the backup retention period or the instance class of that DB instance, and if you select apply immediately, it will immediately reboot that instance. If you change the storage type, it will also reboot that instance. It could also be that you've just run out of storage, and if that occurs, then your RDS instance will go down. So the action that you can take is, first off, check the instance status by looking in the console, or you can also use the command line interface as well. Also, if you're making a setting that requires a reboot, you can select apply immediately and set that to false, and that will make sure that the reboot occurs during a maintenance window that will produce less disruption for you. If you find that you are running out of storage, then make sure that you monitor the free storage space metric in CloudWatch and set up a CloudWatch alert for that as well. Sometimes with MySQL, we may find that there is a lag between the data that is in our master database and what is in our read replica if we've got a read replica set up. So that lag between that in seconds is what we call the replica lag. So if we're experiencing a high level of replica lag, there are a number of causes that could be behind that. First off, we could find that there is a difference in the capability of our master database and our read replica. For example, it may have a different storage class, or the master database might have a high provisioned IOPS and the read replica only has a low provisioned IOPS and is not taking advantage of that. It could be that the DB parameter group settings are incompatible with between the read replica and the master database. It could also be that we are experiencing a high write rate, and that is causing the MySQL query cache to be refreshed too often, and it can't keep up with that appropriately. So the action that we can take is, first of all, we can monitor replica lag in seconds using the CloudWatch replica lag metric. And that will return in seconds what that replica lag is. If they are identical, then it will return 0. If we have our instance is experiencing an outage, then that will return a -1. We should make sure that we use the same instance and storage class for our read replica as we've got with our master database. And if we find that we're having a high write rate, we can look at disabling that query cache. Another thing we can do is that we can warm the InnoDB if it's MySQL, or ExtraDB if it's MariaDB. We can warm the buffer pool on that read replica. The way we do that is that we can copy data from our master database over to our read replica, and that will update the buffer pool on that read replica and will set that replica lag back to 0 for us. So that's all I need to discuss now on troubleshooting RDS. The best way to learn this stuff is to get hands-on with it, and that's what we'll be doing in the next lecture. So I'll see you in that one.
Please note that this content is targeted for SysOps administrators. If you're a solutions architect or a developer, you may want to skip over this one.
And welcome back to Backspace Academy. In this lecture, we'll have a look at some of the tools that are available for troubleshooting our RDS instances. We're also going to have a look at ways that we can troubleshoot and correct issues with excessive read replica lag. Okay, so here I am in the RDS console. We already know how to create an RDS instance, so I'm just going to run through this quite quickly. So get started now, free tier eligible only. We'll select MySQL, Community Edition. We'll leave everything as it is there. We'll use a T2 micro. It's on the free tier. We'll give our instance an identifier. We'll just call it test, and a username and a password. And next. So we'll leave the RDS instance to create a new security group for us. We'll just launch this into the default subnets. We'll give the database a name, just use test again, we'll be fine. And we'll leave everything else as it is. We'll do a backup, that will be fine. What we also will do actually is we'll put a maintenance window in there as well. So I'm just going to select a maintenance window. So what that means is that when we do any major updates that require a reboot, they will occur during this maintenance window. So if you don't want an interruption to your service, it's a good idea to pick a maintenance window that corresponds with the lowest time that you've got usage on your database. So here we've got here Monday at midnight for half an hour. That will be fine. We'll launch that DB instance. So after a certain amount of time, again, our DB instance will go from creating through to available for us. And after a certain amount of time, our MySQL RDS instance is up and running and status is available. Now, if we found that it didn't, for whatever reason, become available, there are some things that we can do. We can go into instance actions and we can have a look at the details, and we can have a look at the recent events and logs. And that will give us a running view of what has happened to our instance and all the events that have occurred. And also, additional to that, we have here the MySQL error running log. And so we can actually download that, or we can just view it from here. And there we can see that there are a number of notes. There is a warning here, but there are no errors as such that have been in the log. So there's nothing particularly alarming there. But if you found something in there, that would be certainly a very good troubleshooting tool to find where the problem exists. Now, we'll just jump back into our DB instances, and we'll have a look at some of the issues that can arise with connecting to our RDS instance and what we can do about it. So we've got here our endpoint, so we're just going to copy that over, and we'll jump into the MySQL workbench. And let's have a look at connecting into that. So let's just test that connection now. So there we can see our connection has been successful. So let's just say we had the wrong username. Let's see what happens there. And there we can see that we have an access denied. So we have been able to establish a connection as such, but we haven't been able to authorize that user. And the same would happen if we use a wrong password as well. Now, another thing that can occur is if we use the wrong port. So just say we try to connect in on port 22. That will basically just hang for quite some time before it gives any message. So nothing is happening, it's just hanging there. But over time, it will eventually give a message. So I'm not going to wait for that. So I'm just going to get out of that and jump into Telnet. So I've just now jumped into the command line, and I'm just going to run a Telnet command to do a low-level connection to our RDS instance. Now, Telnet is not by default enabled in Windows, but you need to go into your control panel and then go into turning Windows features on and off and select Telnet and turn that on, and that will install the Windows Telnet client for you. So the command that we use after we've installed Telnet is Telnet and simply the endpoint and the port. So a space and then the port, and we'll connect in. And that has actually connected in. It's returned something that doesn't really make any sense. The reason for that is that although that we are able to physically connect to our RDS instance, we cannot actually do anything from there. So we cannot actually SSH into an RDS instance, and we can't connect in through Telnet or anything like that. It doesn't let us to do that. But if we get a message back like this, it means that the low-level physical connection is okay. So it means that our security groups are okay, our VPC is okay, our endpoint is okay, and our port is okay. So if we try and connect in with a bad URL, let's see, or bad endpoint, but let's see what happens. Put a D in there. And straight away, it comes back and could not connect to that host. So this is a really good tool that if you can't really find out what's going on in the MySQL workbench, just jump into Telnet and just see if you can do a quick connection through to Telnet. If you can't, start having a look at your port number, start having a look at your endpoint URL, and start looking at your security groups in your VPC as well, or that are associated to that RDS instance. Now, just jumping back into the RDS console again, what I want to have a look at now is just looking at some of the issues that can arise around read replicas or MySQL read replicas, and what we can do, some of the troubleshooting tools that are available for us to identify what's going on and causing that read replica lag, and then also some of the corrective actions that we can take. So first off, let's look at launching a read replica. So we go into Instance Actions, Create Read Replica. We'll give that a name. And we'll leave everything there as it is and create that read replica. Okay, so we can see there that the master database is being modified and we are currently creating that read replica. So after a certain amount of time, that will be available for us. Okay, so after a certain amount of time, we've got our MySQL replica database up and running. I'm just going to expand those details and I'm going to click on the replication tab here on the left. And there we can see the replication details. We've got our master database called test. We've got our replica database, test2. We can also see that we've got our replica lag of 0 milliseconds, which is what you'd expect because there's no database in the database. Now, if we found that we're having excessive replica lag, the first thing we would do is that we would have a look at our CloudWatch metrics and our CloudWatch graphs, and we would see if there's anything that coincides with that increase in replica lag. For example, if you had significant write operations to your database at that time, then that would obviously cause it because the replication is not keeping up with the speed of with which you are changing your data. If that's a one-off situation, you can look at pre-warming that replica by copying data from your master database over to your replica database. Now, the problem with that is that a replica instance is read-only. So what you need to do is that you need to temporarily change that to be writable and then change it back to being read-only. If you find that it's not a one-off situation, you find that it's an ongoing situation, then the next thing you would do is that you would disable your query cache. And we'll have a look at how we do that soon. And if you still have problems, then you're going to have to look at upgrading your master database and your replica database to a larger instance type with more memory or more capacity, whatever. Now, to make these changes to the query cache or to make our replica writable temporarily, we need to change the DB parameter groups for that instance. So again, what a parameter group is, it defines the parameters around that database application. And so it doesn't go into anything low level as far as a networking layer, and it doesn't go anything about the operating system behind that database application. It's about the parameters around the MySQL database application. So just click on parameter groups here on the left, and we can see there that we've got our default MySQL parameter group. Now that is applied by default to all of these, including the read replica, to all of our RDS instance or MySQL RDS instances that are launched. Now, one thing you'll notice from this is that if you select it, you cannot edit the parameter. Everything is grayed out, so you cannot copy them. You cannot change them in any way. If you go to delete them, it'll come up with a message saying, do you really want to delete that? And we obviously don't want to do that. So what we do is we create a new parameter group and we select MySQL parameter group family for that. We'll give it a name. We'll just call it test again. We leave the description just test, that will be fine. And we'll create that parameter group. So that's been created. So we'll just select it and we'll edit the parameters. So we can see there's a lot of parameters that we can edit for our database. So the ones that we are concerned with will be the query, which I'll just go down to, and read as well. Okay, so we can see here we've got query cache size and there's nothing in there. So by default, the query cache is empty and not being utilized. So if it is, you can disable it here, but by default, it is actually disabled. So with our replica, we can see here read only. It is currently, if it is actually a replica, so we can see true if replica. So if this instance is a replica, it will be read only. So what we can do is we can select that and we can change that to 0. And so that means that it is not read-only, it's writable. And then we can go back and we can save that. Save the changes. So now that we've got a parameter group that allows us to write, we can now associate this with our replica database. So we'll go back into instances. We'll select our replica database and we go to instance actions and we go to modify. So we scroll down, we'll leave everything as it is there, and we select DB parameter group. So we can change this to our new test. So it'll provide you with a list of all of the MySQL parameter groups that we have available, and because we just created a new one, test is available. We can go through there and we can continue, and we can modify that DB instance. And there we can see that's done. So that brings us to the end of the troubleshooting section for RDS. And by all means, go ahead and have a play around with it yourself. Try and connect into an instance. Try and play around with different port numbers. See what happens. See if you can create a new parameter group and have a play around with it yourself, because that's going to be the best way to learn. And I'll see you in the next one.
Please note that this content is targeted for SysOps administrators. If you're a solutions architect or a developer, you may want to skip over this one.
And welcome back to Backspace Academy. If you're a SysOps administrator, you're not only going to be heavily involved in troubleshooting services when they go wrong, you're also going to be expected to implement systems that can alert you to problems, and also not only alert you to problems, but also invoke other services that may be able to correct that problem. So we'll go through and have a look at one of the most important of those services, being the EC2 service. And we'll look at the CloudWatch metrics that are available. We'll also look at the custom metrics, different metrics that we can implement that are not standard within CloudWatch. We can look at CloudWatch statistics, and that will provide us aggregate data of those metrics that are being recorded. We'll look at the different types of actions that are available from a CloudWatch alarm. And then finally, we'll look at elastic load balancer monitoring as well. The standard EC2 CloudWatch metrics that are available to us. For our T2 burstable instances, we can keep track of our credit usage and credit balance to make sure that we still always have available that ability to burst when required. For general instance metrics, we have CPU utilization, we have disk I/O and network information that we can monitor as metrics. And we also have our status checks that we can monitor as a metric as well. CloudWatch metrics, they can be filtered using a dimension. So for example, if you wanted to just get the metrics for all of the instances within a specific auto scaling group, you can use the auto scaling group name, or you can use the image ID, the instance ID, or the instance type. And the available metrics, they will be listed in the CloudWatch console, but you can also use a command line interface by using the CloudWatch list metrics command to list those as well. Detailed monitoring, that can be enabled, and that will enable 1 minute interval of your CloudWatch metrics. And you can do that at launch, or you can do it with existing instances also using the EC2 console. But you can also use the command line interface. So when you're doing an EC2 run instances command, you can have monitoring enabled equals true for detailed monitoring. Or if you're doing the EC2 monitor instances command on an existing instance, that can be done as well. It is possible to create your own custom metrics, and they can be collected and published to CloudWatch from your EC2 instances. And you can do that using the CloudWatch put metric data command in the CLI. Or if you're using an SDK and you can have an application running on your EC2 instance, you can use put metric data, and that will enable you to publish that information to CloudWatch, and CloudWatch will collect and monitor that for you. You can have that at standard resolution of 1 minute or up to high resolution of 1 second. There are also available CloudWatch monitoring scripts, and they are again custom metrics, and they will run Perl scripts on your EC2 instances, and they can collect memory, swap, and disk space utilization data. If you would like to have that monitored on a regular basis, you can create a cron job, and that will publish that at regular intervals to the CloudWatch service. And from there, you can view that information as you would any other CloudWatch metric. A lot of times it is not really beneficial to look at instantaneous metrics and see what's going on there, but we might want to look at what the aggregation of that data is over a specific period of time. So we can look at the minimum or maximum levels that have occurred over that period of time. We can look at the sum of all of the values that were submitted during that period from all of the samples that were taken. And we can also look at the number of counts, or the sample accounts, which is the number of samples that were received over that period. And the average, which will of course be the sum, the total of all those values divided by the number of samples, so all that's divided by the sample count. Also, we can have a look at the specified percentile. So if we've got there a percentile of 95.45, that means that 95.45% of all of the data collected will be lower than this value. If we did 94, it would be 94% of that data is below this value. So we can select a specific percentile and report our metrics based upon that. One of the great features of using CloudWatch with the EC2 service is being able to use alarm actions, and they can automatically stop, terminate, reboot, or recover our instances for us. We don't need to intervene in any way. It will automatically happen once it's set up. So they can be created using either the EC2 or the CloudWatch console. And there are a number of use cases that are very good that we could use for this feature. We could use it to stop idle instances that are not really being used. We can use it to stop web servers that are getting unusually high traffic. For example, if they're getting attacked. We can look at the network out, and then we can also look at stopping an instance that is experiencing a memory leak. We can stop impaired systems that have failed their status checks, and we can terminate an instance when a job has been finished. For example, you might have a batch job to process a video, and then you can terminate that instance when it is completed. So additional to monitoring our EC2 instances, we can also monitor our elastic load balancers. Out of the box, we have CloudWatch metrics, and they will be reported at, or monitored and reported at 60-second or 1-minute intervals. Additional to that, we have access logs. So the elastic load balancer can publish a log file when it is enabled, and that will record log information from anywhere from 5 to 60-minute intervals. And those logs will be saved to Amazon S3, and we can access those if we need to. Additional to access logs, when they are enabled, a feature of application ELBs, not classic ELBs, but just application ELBs, is that we can look at request tracing, and that enables us to track our HTTP requests from our clients to our targets or other services. And it does that by adding or updating the trace ID header before sending it back. And that is integrated again with the ELB access logs. And finally, we can look at implementing CloudTrail on our Elastic Load Balancer to log any API calls to our load balancer. So that's all I need to discuss now from a high level around monitoring of EC2 and ELB. Coming up next, we'll have a hands-on session to apply this stuff. So I'll see you in that one.
Please note that this content is targeted for SysOps administrators. If you're a solutions architect or a developer, you may want to skip over this one.
And welcome back to Backspace Academy. In this practical lab on implementing CloudWatch monitoring scripts on EC2, we're going to start off by creating an EC2 server and then associating an IAM role to give it permission to access the CloudWatch service. And then we're going to use that EC2 server to push metrics or custom metrics over to the CloudWatch service, and then we'll be able to view those metrics in CloudWatch as well. So the first thing we need to do is to create a role for our EC2 instance to access the CloudWatch service. So we go to Roles, Create Role, and we're selecting an AWS service, so we select EC2, and then Use Case EC2 to allow EC2 instances to call AWS services, which is what we want, so we'll select that, and Next Permissions. So what we need to do now is we need to create a custom policy. So create policy. And create your own policy. We'll give it a name. And I'll just paste in the policy document that I've created that will give the EC2 instance access to that CloudWatch services that we need. Okay, so we just have a look at this policy document here. So we've got an allow to allow our EC2 instance to get metrics statistics, to list the metrics, and to, most importantly, to put metric data there. And we've just got that for all resources. And we've also got another one that is required for EC2 described tags as well, which is required for that, that script. So we'll create that policy now. Now, what we need to do is that we need to go back to our role. So now that we've created that policy, we need to associate that policy with this role. So we'll just search that policy now. And there it is, the one that we created. So we select that one and we click on Next Review. We'll give the role a name. We won't worry about a description there. And we'll create that role. And there we can see there is our role that we just created. We'll just have a look and make sure it's okay. And there's a policy that's attached to it. And we can see that it's got CloudWatch permissions. So that seems to be fine there. So now we can go into the EC2 management console and start creating this EC2 instance that can collect these CloudWatch metrics. So we'll go into the EC2 dashboard, click on Launch Instance. We'll select an Amazon Linux AMI and a T2 micro. Now what we want to do is that we want to assign that IAM role to this EC2 instance. So we select on IAM role and we'll select that EC2 monitoring role that we created. The next thing that we want to do is we want to expand advanced details because we want to put in a bash script in here. And what that is going to do, it's going to pull in the required files to run the Perl script. So it'll have the Perl language environment which will be downloaded and installed, and then it will also download and unzip the actual Perl scripts that are going to be run. So just jumping back into the lab notes, and I'll just grab that script. Okay, so I've just put that in there, and I'll just expand it out a bit and show you what it looks like. Okay, so we can see there we're doing a yum update, so just making sure that the Linux operating system is up to date. And then we're installing our Perl requirements that we need. Then we're doing a curl to download that zip file, and then we're just unzipping it into that CloudWatch monitoring scripts directory that we'll have. So that looks fine. We'll just review and launch. And what I would like to do now is just to give it a name, just so we can find it easy enough. So we'll just edit tags, add a tag, and put a name in there for it. And just call it monitoring, that'll be fine. So we review and launch, select a key pair, and we'll launch that instance. So of course, after a certain amount of time, that will be up and running, and then we can start to use our CloudWatch monitoring scripts. Okay, so our EC2 instance is up and running. It's passed its status checks. It's ready to go. So what we can do now is connect to it. So I'll just click on connect, grab that connection string that I need, and jump into Commander. So I've just navigated to where my key pair for this instance is and just connect in. And now I'll navigate to where the monitoring scripts are. So there we can see we've got our mon get instance stats and mon put instance data. So we can test that out now without actually publishing anything to CloudWatch, just with a simple command. So there we've got mon put instance data, and we're going to get the memory utilization metric. So let's just run that. So there we can see it's memory utilization is 8.13%. It's tried to look for credentials. It hasn't found it, so it's trying the default IAM role, and it's found our EC2 monitoring IAM role, which is fine. And then it's delivered as JSON our payload there. And so there we can see the value is 8.13. The unit is percent, and the metric is memory utilization. So what we'll do now is that we'll try and publish or push this out to the CloudWatch service and see if we can pick it up in CloudWatch in the CloudWatch console. Okay, so this command now will actually push it out to CloudWatch, so we'll see if that works. And then we can see it's successfully reported metrics to CloudWatch. So we can now jump into CloudWatch and have a look and see if it's actually picked it up. Okay, so let's just go to Services and CloudWatch, and we'll see if we can find that metric that's been pushed out to CloudWatch. So we're going to Browse Metrics, and we're looking for Linux System Metrics. And we select Instance ID. And there we can see we've got some for some instances. And this is the one we're looking for, as our instance name was monitoring. And so that's what we're looking for. So we did actually publish memory utilization. So I'm just going to select that one. And we can see there we've got 1 point there of 27.6 for memory utilization. So let's just jump back into the command line interface and see if we can send another data point and see where that gets picked up as well. Okay, so now jumping back into the command line interface, we've seen how we can publish or push a metric information out to CloudWatch manually. So what we want to do now is to set up a cron job that can do that on a regular basis. So we'll set it up so that it does it on every minute. We'll give the instance 10 minutes or so, and we'll just see what happens and whether it actually gets picked up. So the first thing we need to do is to go into cron tab or a cron table and edit that. So I'll just go and grab the command that we need. Okay, so I just press the insert button, and that will bring me into insert. I'll paste that in, and we can see there that we've got the cron schedule, which is just all stars, which means every minute it will be running, and it's going to run that mon put instance data and going to publish some metrics out to CloudWatch for us. So I'll just get out of that by pressing escape, and then the colon and WQ exclamation mark, and that will quit and save that for us. And it's probably a good idea just to check that it worked okay. So just do Ctrl Tab E and we can see that's fine. So I can just get out of that again. Okay, so if we leave that for a while now, I'm just going to go away and have a cup of coffee. I'll come back And then we'll have a look at CloudWatch through the console, and we'll see if any of these metrics are being published every minute as they should be. Okay, so it's been about 20 minutes or so, and we should have a good amount of data that is coming in from our cron job that we created. So just back here in the CloudWatch console, I'll select the monitoring instance and memory utilization. We'll see what we've got. And there we can see they've got quite a bit of data from 11:45 up to 12:05. It's gone from 27.6 up to 27.85, down and up again. So that's working great. So what we've done is that we've created an EC2 instance and installed a Perl script. Now that Perl script was created by AWS, and it's collecting system information and publishing that to CloudWatch for us. And we're now here able to see it. So it's something that not only do you need to use AWS scripts, you can actually do this yourself. And I'll give you a good example is that you may have, for example, an Internet of Things device that is collecting data, and you want to push that data out to somewhere to be stored. So a great way to do it is to really push it out as a metric. If you're recording a metric, push it out to CloudWatch, and you can view it in CloudWatch, and you can also use CloudWatch logs to archive that information as well. So there's some great opportunities to do that. And all you need to do is, if you're using an SDK, if you're using the Node.js SDK or the PHP or Java or whatever SDK it is, they will have a feature there in CloudWatch to put metrics out. So just as an example, I can jump into the AWS SDK for JavaScript documentation, go into the API reference, select CloudWatch, and if I scroll down here, we can see that we've got put metric data. And so that publishes metric data points to Amazon CloudWatch, and it'll do that as a custom metric, just the same as our Perl script has done. So if you've got any use cases for that, that's great. And you don't need to use the AWS scripts. If you've got your own scripts that you want to use to collect whatever data you want to use, by all means, go ahead and do that. So I think we've learned quite a lot there, and I'll see you in the next lesson.
Please note that this content is targeted for SysOps administrators. If you're a solutions architect or a developer, you may want to skip over this one.
And welcome back to Backspace Academy. In this lecture on monitoring RDS, we'll go through the monitoring options that are available for the RDS service. We'll also look at the enhanced monitoring that is available that provides real-time monitoring of our instances. We'll look at RDS events that provide us with a unique service for RDS to alert us to issues. And we'll also look at the downloading of database log files that are produced from the actual database engine. The monitoring options that are available for us with RDS, as with most services, we have CloudWatch alarms that can alert us to an issue. We have CloudWatch logs that we can use for archiving of this information from CloudWatch. And we can also have CloudWatch events that we can use to invoke other services that we can subscribe to and get messages from. We also have the enhanced monitoring. Now that is specific to RDS, and it provides real-time operating system metrics for RDS. And again, specific to RDS, we have the RDS events. Now we can subscribe to these RDS events, and we can have an SNS message sent out to us if something occurs that is unusual. We also have database log files, and they are produced by the specific database engine. So if you've got MySQL, it will produce a certain set of log files. If you have SQL Server, it will produce its own set of log files as well. So we'll look into how we can actually access those and view those. Another new service that we've got there is the Amazon Performance Insights, and that provides a lot more visualization and some further metrics that we can use for monitoring our instances. And finally, we can look at implementing CloudTrail on our RDS instances, and that will enable us to record API action to our RDS instances and to store that with Amazon CloudWatch logs. So RDS Enhanced Monitoring, when it is enabled on an instance, it will provide real-time operating system metrics for that instance. They can be viewed in the console, or you can actually view and download your CloudWatch logs for those metrics. It's not available for T1 micro and M1 small instances, and the costs will vary. There is a free tier usage level, but if you exceed that, then you are going to be charged. And so that depends on what your monitoring interval is, so how frequently you are actually getting this information and logging that information, the number of instances that you'll be monitoring, and the amount of activity that needs to be reported. So for example, if you're doing compute metrics and you've got a compute intensive instance, a large instance that's doing a lot of compute operations, then there may be more activity to report. So you need to take that into consideration if you're looking to stay under the free tier. RDS events, we can subscribe to those and they will trigger an SNS notification for us. There are multiple event types, and within the event types, there are multiple types as well within that. So there's a very broad range of events that we can subscribe to, and it provides very good granularity if we're looking for certain out of the ordinary events that we want to be alerted to. So we can view those events, again, not only via the SNS notification service, but we also can view them with the RDS console and the command line interface or the API or SDK. So database log files, they are produced by the specific database engine that we are using. And that varies depending on what engine we are using. For example, MySQL, you can see there, we've got error, slow query, and general logs, whereas Oracle, it doesn't have error logs available. So the logs that are available, or the log files that are available to us, depends on what database engine we're using. So those log files, they can be downloaded and viewed using the RDS console, the command line interface, or the API tools. And transaction logs are not supported. So we're looking about error logs and general logs, but we're not looking at actual transaction logs. They're not supported. So that brings us to the end of this lecture. And the best way to really understand this is to start to use it. So we'll have a hands-on lesson coming up next, and I'll see you in that one.
Please note that this content is targeted for SysOps administrators. If you're a solutions architect or a developer, you may want to skip over this one.
And welcome back to Backspace Academy. In this hands-on lecture on monitoring RDS, we're just going to run through some of the tools that are available for monitoring our RDS instances. Okay, so our instance is now available, and what we can do now is start to have a look at some of the metrics that are being produced from it. So we click on Show Monitoring, and there we can see our standard CloudWatch metrics. So we've got CPU utilization, free storage space, and this is coming from the hypervisor information. So what we can also look at is our enhanced monitoring, and that is coming from an agent that is running on that actual EC2 instance in a similar way that you would have a monitoring script on an EC2 instance, for example. So we can actually go into here and look at enhanced monitoring, and we can see there's a lot more lower level operating system level information available for us around memory and file system information and load on the system, which is very important as well. So this is quite a good one to monitor. Number of tasks that are running and the average load as well. So what we can do is that we can actually create CloudWatch alarms around this as well. So if I just go back to instances now, and we can also see in here under the information, we can go to logs, and there we can see that the logs for our error running log are being recorded, and our MySQL upgrade log as well, so we can download and view those as well. We've also got RDS events, so just on the left hand side here we've got events. And there are a number of things that we can look at subscribing to. So we've got some events here that have occurred. So the DB instance was restarted, it was created, it was backed up, and then it's finished backing up that instance. And so we can actually go into here into event subscriptions, and we can create an event subscription. Just give it a name. And we'll create a topic there, a new topic. And we'll just call that test again. We'll just put in anything. I'll just copy this user at domain, that will do. And we'll select source type of instances. And so we just select, say, whenever an instance fails over or we have a failure of an instance, we can subscribe to that. And we just create that. Okay, so the final thing I'd like to show is a new feature to RDS. At the time of this video, it is only in preview. So if you're looking at your RDS console and you don't see this tab on or this menu option on the left-hand side here called Performance Insights, don't be too concerned about it, as it will be coming to you eventually. And also we've got here an option to launch an Aurora PostgreSQL preview. So Aurora has always been a MySQL database engine database, but it's now also going to be a Postgre compatible as well. So what we'll do is we'll launch a PostgreSQL Aurora instance, because that is what we can use now with Performance Insights. So I'll just click on that. So I'll just use the smallest class that is available. Just give it a simple name. Now we can't use admin for a Postgre database. We'll use something else. Just give the cluster a simple name as well and the database a simple name. Now I'm just going to enable enhanced monitoring as well. And I'll give the granularity of 15 seconds. And we can see here we've got an option for enabling Performance Insights. So that's a new feature that is currently, at the time of writing, or at the time of this video being created, is only available for Aurora PostgreSQL instances. So we'll just go and launch that DB instance now. And after a certain amount of time, that will be up and running. Okay, so our Aurora PostgreSQL database is up and running. So what I'm going to do now is just connect into it. So I'll just grab that endpoint and jump into pgadmin, create a new server, put the connection in there, take the 5432 off the end of it. And if you don't remember how to do this, just go back to the RDS section and do the lab on PostgreSQL databases. And I'll put my username and password. Save the password. Just give it a name, test2, that will be fine. And save. Okay. So now I've connected in there. If I have a look at my database, I should see my test2 database. I'll just connect into that. And that is good. Go to the dashboard. Okay, so I'm connected in as a user there, so I should be able to now go back into the RDS console. And now if I click on Performance Insights, which is that new feature, and now if I select, I can see here I've got my master database and my replica here. If I select that master database, I can see that there's information there of my activity of connecting into that instance. So we can see we've got a little bit more information here from the performance insights, in particular around load on the database. So what we've got here is that we can have a look at users as well. So load by user, and it gives us a lot more granularity around what is actually happening with our RDS Aurora instance. So that's about all I need to show you about monitoring of RDS, and I'll look forward to seeing you in the next lecture.